Hello, welcome to this full course of electrostatics. In this course, we'll teach you everything from the basics to the advanced topics such as Gauss Law and electric dipoles. This course is designed to meet the exam requirements for most A-level curricula including JEE, Cambridge and others. The topics covered include electric charge, types of materials, electrostatic charging, polarization, corona discharge, Coulomb's law, Gauss law and many others, plus hundreds of numerical examples. As you see, it takes time to compile such a long course, so I would appreciate if you support my hard work by subscribing to this channel and giving me a like. So without further ado, let's get started. Hello everyone, my name is Dennis and I welcome you to this course of electrostatics. In this lesson, I'm going to go through the course outline that we'll be following throughout the course. So we'll have our course outline for this course. Let me have more space. Okay, so this is how we are going to run the course. We have our course of electrostatics. So the first part that we are going to be looking at is going to be about the types of materials as we classify them in terms of electrostatic behavior. So we'll begin by looking at the types of materials. This is going to be our first topic in this course. We'll go ahead and look at the term charge. This is very important because electrostatics is mainly about the study of charge. So we'll look at charge, we'll look at what charge is, we'll define the term charge. We'll go ahead and look at the properties of charge. We will also look at the types of charge and we'll look at the experimental verification. We'll look at the experimental verification of the two types of charges that we'll look at. Our third chapter in electrostatics is going to be about a very important phenomenon called electrostatic charging. Electrostatic charging. And under here we are going to look at the methods used to charge things in electrostatics. Here we'll look at how to charge things by induction or electrostatic induction. We'll look at how to charge by friction or by rubbing. We'll go ahead and see how to charge things by contact or by conduction. Conduction. Okay, this is going to be our third subtopic. Subtopic number 4, we are going to look at the gold leaf electroscope. The gold leaf electroscope. This is a very important device that we use in many experiments, and we are going to be looking at its use frequently throughout this topic. So we'll dedicate some time to look at the gold leaf electroscope. The gold leaf electroscope, we'll look at how it works. We'll look at how it works and what are its uses. Okay, we'll try to also look at Coulomb's law, which is basically a quantitative analysis of charges. So under Coulomb's law, we'll look at the force between charges, basically how to calculate it. Okay, and this is going to be the first part of the course of electrostatics. We'll begin by looking at the types of materials. We'll look at conductors, insulators, semiconductors and superconductors. We'll go ahead and look at the types of charge, their properties and how to experiment this. Our third subtopic, we are going to look at electrostatic charging. Number 4, we are going to look at the gold leaf electroscope, which is a very important device in electrostatics. And we'll conclude this first part by looking at Coulomb's law, which is a quantitative analysis of the force between electrostatic charges. And from here we'll move on to the second video where we'll be talking about electric fields. So thank you for watching. Next, we now start to look at the types of materials. Before we look at the types of materials, let us first understand the word electrostatics. The word electrostatics comes from two words, or we can break it down into two parts: electro and statics. These two words give us a broad sense of what we are going to be covering in this course. Electro is a short for electricity or electric charge. I'll call this electric charge, and you know very well from mechanics, which is a branch of physics, we know very well that statics means the study of particles at rest, or objects. I think that's better, the study of objects at rest. So in electrostatics, we combine the electric charge behavior with the study of objects at rest to bring together what we call electrostatics. Essentially, electrostatics is a branch of physics, that deals with the behavior. By behavior, we mean the characteristics, the behavior of charges at rest. Charges have very interesting properties when they are at rest than when they are in motion. When charges are in motion, they constitute an electric current, which is not the case here when the charges are at rest. So in this course, we will not concern ourselves with electric current, so we will not study what happens when charges are in motion. We will study what happens when charges are at rest. That's electrostatics, the study of, or the branch of physics that deals with the behavior of charges that are at rest. Let's go back to our course outline. What did we say? We begin with the types of materials. That's going to be our first lesson. Types of materials. Now, with reference to electrostatic behavior, materials are broadly categorized into two types. That is to say, we have conductors and we have insulators. However, there are some materials that we cannot call totally conductors or totally insulators. They somehow lie between the two groups, conductors and insulators. So they form the third category, and we call them semiconductors. Also, there are some materials that are conductors, but their degree or level of conductivity is too high to be compared with normal conductors. So they also take a separate part, and we call them superconductors. We'll be looking at these in a while. Superconductors. Okay, to understand the difference between all these four types of materials, but to be specific, to understand the difference between conductors and insulators, we'll have to look at the atomic view of these materials. So the modern picture of an atom is as follows. So the modern picture, oops, this is looking not good. Okay, the modern picture of an atom is as follows. In the modern picture of an atom, to begin with, we have a nucleus, which is having positive charges, protons in it, and the nucleus is surrounded by a cloud of electrons around it, an electron cloud like that. So this is the nucleus, and these are energy levels surrounding the nucleus in which we find electrons. These electrons combined together form an electric cloud. Now in a neutral atom, of course, the number of electrons, which are the negative charges, must be equal to the number of protons. And in that case, we say the atom is neutral. We'll look at this later. Neutral means the state in which the net charge on an object is zero. It does not necessarily mean absence of charge, but it means the total charge, the total net charge is zero. Okay, let's use this to understand the difference between conductors and insulators. Well, in both materials, conductors and insulators, the atoms look the same. They have a positive nucleus and an electron cloud around them. However, the main difference between conductors and insulators is the force with which these electrons are bound to the atom. You see, in conductors, the forces on the outermost electrons, of the atom are somehow weak. So the forces are weak. That means some of these electrons can escape from the atom. So you have an atom, but the forces that are keeping these electrons around the nucleus, when they become weak, especially if you supply some heat energy or some other physical condition, these electrons can gain some energy and perhaps one of them could escape. So in a typical conducting material, in a typical conductor, we have some fraction of the electrons that are not bound to the atom, and so these unbound electrons are free to travel throughout the material, and because they are able to travel throughout the material, that makes the material to conduct. So ideally, when we say conductor, we mean a material that allows the movement, sometimes we can say transfer, of charge through it. The movement or transfer of charge through it. We have just seen why conductors allow the movement, because some of their electrons are not bound. So some of these electrons can escape. In other words, they can become unbound. So they are free to move within the material. Let me give you a picture of how this looks like. Consider this to be our conducting material. Inside our conducting material, we have many atoms. These atoms are packed together. As a matter of fact, on average, the interatomic distance is about 10 to power negative 10 meters. This is a very small distance between the atoms, closely packed. But inside, so this is a conducting material. Inside this material, there are some electrons that are free and they are not bound to the atoms. These are the atoms. So some electrons are not bound to the atoms, so they are free to move. These are free, unbound electrons. They are free to move in any part of the conductor, of all of the material, so they give it the ability to become a conductor because they can move through it. They enable charge to be transferred throughout the material. This constitutes what we call a conductor. Some common examples, we get another color of conductors. Common examples of conductors include most metals. In fact, all metals conduct. We also have some materials like salty water, and believe it or not, the human body is also a conductor, and also ionic chemical solutions also conduct electricity, because ionic means the presence of ions, positive and negative ions. Those ions make the solution to be a conductor. Okay, let's have a quick recap of what conductors are before we move to the next part. So in our picture of an atom, we said all materials are made up of this basic atom. Inside the atom there is a positive nucleus surrounded by a cloud of electrons. The classification of the material as a conductor or insulator depends on the nature of this atom here. Some atoms have weak forces that are binding these electrons to the atom. So because of those weak forces, the electron, especially the outermost electrons, can easily escape from the atom and become free within the material. Like we see here, these electrons are free to move throughout the material, and when they become free to move throughout the material, it means the material is able to transfer charges through it, and by the way, also transfer heat, but we are not concerned about the transfer of heat in this topic. Okay, so in conductors, the forces on the outermost electrons are weak, and some of these electrons escape from the atom and they become free or unbound. So a conductor is a material that allows the movement of charge through it, since it has free electrons that can move throughout. And here we have an enlarged view of what looks like inside the conductor of a material. Typically, not each of these atoms will donate an electron. About 1 in 10th of these atoms will have free electrons escaped from them, and those electrons will contribute to the conductivity of the material. Let us now look at the next type of materials, and that is the insulators. Having understood conductors, it is very easy to understand what insulators are. And these are basically materials in which, okay, I should say materials which do not permit, or materials which do not allow transfer or the movement of charge through them. Some of the characteristics of insulators is that all the electrons are tightly bound. All the electrons are tightly bound to individual atoms. So you don't have any free electrons that can move throughout the material to contribute to its conductivity. And that's all we have to say about insulators. Maybe some examples of insulators. We have a couple of them here. All plastics are insulators. Wood is an insulator. Rubber is a good example of an insulator, and many other things. And by the way, each of these materials has its advantages for practical usage. For example, these materials are used to insulate electric cables. These materials are also used to handle hot objects, since they do not also conduct heat, and many other uses, whereas the conductors are used also in real life to make electric cables and most kitchenware is made from conductors. Kitchenware mainly saucepans and some dishes. Okay, these are the two main types of materials in classification according to their electrostatic behavior. However, we looked at some in our introduction. We looked at some two special types of materials, that is the semiconductors and the superconductors. We will not go into their deep details, but we'll talk about them briefly. So let's begin with semiconductors. Semiconductors. So semiconductors are materials whose properties lie between those of conductors and insulators. What this means basically is that semiconductors have properties of both conductors and insulators, so they can conduct at some conditions and they can become insulators at some conditions. The main condition here is temperature. When the temperature is low, these materials are basically insulators. When the temperature is high, most of them become conductors. Okay, let's look at some common types of some common examples of semiconductors. Mostly, if you look at group 4 elements in the periodic table, like silicon, tin, germanium, selenium, and others are some examples of semiconductors. Well, the atomic theory behind conduction or the atomic theory behind the properties of semiconductors will not be discussed in this topic, but just to have a simple clue of how semiconductors work, semiconductors have two types of charge carriers. They have what we call the electrons, which are the negative charges, as we have seen, but they also have the holes, which are the positive charge carriers. As we shall see, I will make a separate video and leave a link in the description or a YouTube card to show you how these work. Mainly we'll look at them under current electricity. They have very interesting properties. They have two charge carriers, electrons and holes, so this gives them priority for use in the electronics industry because their conductivity can be modified by mixing them with other elements to increase their conductivity or to reduce it. Lastly, we'll look at superconductors. So superconductors, as the name suggests, are materials with very high degree or extent of conduction, and this is basically because they have very low resistance. Now, at least as of this recording, we do not have materials that are naturally occurring semiconductors, but some special materials at very low temperatures, can have very low resistance, and so we can consider them to be superconductors. So superconductors is a new type of material in the research industry, and it's already in use, especially in the field of electromagnetism, in making magnetic levitation trains. We need materials which can become magnetized to a very high extent of carrying a big mass. So this is how a picture looks like. We have an electric train and the electric train is moving on rails, these rails have to be made of a superconductor. Because of this superconduction, you have very high current going through the rails. That means you have a great magnetic force. A great magnetic force that can lift the train up. Okay, also in this topic we are not so much concerned about the magnetic properties of superconductors, but that's the field in which they are commonly used, and we will continue to explore it in other videos about electromagnetism. That's it for this video about the types of materials. In the next video we'll look at electrostatic charge, how to define it, its types, and the units for measuring electrostatic charge. Thank you. Let us look at electric charge. Electric charge, we commonly represent this with letter Q. So electric charge is the property of a material. Electric charge is the property of a material responsible for electrical phenomena. As you know very well, electrical phenomena in materials includes properties such as the ability to conduct electricity and many other phenomena that are associated with electricity. In other terms, we can say electric charge is the property of a material, or is the property of matter that works to the property of matter that causes it, to experience a force when placed in an electromagnetic field. The property of matter that makes it to experience a force when placed in an electromagnetic field. By electromagnetic field we mean either an electric field, which we will study later in the course, or a magnetic field. So because of electric charge, if matter or a material is placed in one of these fields or a combination of both, it experiences what we call a Lorentz force. And this Lorentz force basically is a force that acts on a material because of the existence of charge in that material. So it is charge that causes a material to experience a force when placed in an electromagnetic field. We will explore electric fields in more details later on. Let us proceed now by looking at the types of charge. Okay, create more space here. We will now look at the types of charge. To explore the types of charge, let us perform a simple experiment. In this experiment, we are going to need a glass rod. We are also going to need a piece of rubber. We're also going to have silk and wool. Basically, we will need silk for the glass rod, and we'll also need wool to rub it with the piece of rubber to make it charged. So here goes our experiment. In the first part of the experiment, we are going to hang a piece of charged rubber. So this is charged rubber. In the next part, we are going to see how we can charge materials by rubbing them. Even though we have not looked at that yet, even though we have not studied it yet, let's just talk about it as charged rubber. Basically, this rubber was charged by rubbing the piece of rubber against a piece of wool, so that gives it a charge. Okay, now in this experiment, after charging our piece of rubber and suspending it on a silk thread, if we bring a piece of charged glass rod, this is a charged glass rod, we notice that the charged glass rod and the charged piece of rubber move towards each other. Okay, this is going to be the first part of the experiment. We have a silk thread which is supporting our charged rubber, and we bring a charged piece of glass rod. If we bring it near, we see a force of attraction because the charged rubber wants to come to the glass rod. In the second part of the experiment, still we have our silk thread and we have our charged rubber, and then we have, this time round, another charged rubber. So this is charged rubber, and so is this. Okay, let me label it here, charged rubber. So if we bring a piece of charged rubber towards another piece of charged rubber, we see a force of repulsion. This piece of charged rubber does not want to come near the other piece of charged rubber, so this force here is a force of repulsion. So this is a very important experiment because it gives us two things. So let's see the conclusions from this experiment. The conclusions from this experiment are that there are two types of charge. There are two types of charge. Okay. There are two types of charge. By convention, the charge on the glass rod is the positive charge. That is by convention, and the charge on the piece of rubber is the negative charge. This convention was brought by Benjamin Franklin in the 18th century, and later on it was proved using atomic theory. So that's one important conclusion that we make for now. Another conclusion also very important here is that like charges, another conclusion is that like charges repel each other. Like charges repel each other. That is very evident when the charged piece of rubber was repelling the other piece of rubber, and unlike charges attract each other. That was also very evident when the piece of charged glass and the piece of charged rubber attracted each other, and yet they had different charges. So we conclude that there are two types of charges, positive charges and negative charges, and we conclude that positive and positive repel each other. That is positive and positive. Negative and negative repel each other, but positive and negative attract each other. This is called the fundamental law of electrostatics, or the fundamental law of charge. The fact that like charges repel each other and unlike charges attract each other. Let us now talk about the units of charge. let us talk about the units of charge. In principle, charge is measured in a unit called coulombs, named after Augustine de Coulomb. So charge is measured in coulombs. We denote that with a capital C, and charge is given by current times time. We haven't looked at electric current yet, but electric current is measured in amperes. So 1 coulomb basically is given by 1 ampere times time of 1 second. Essentially what this means is that 1 coulomb is the amount of charge transferred. It's the amount of charge transferred by 1 ampere of current in 1 second. Current is simply the flow of charge. We will explore that further when we look at current electricity in further videos. So the unit of charge is the coulomb, and 1 coulomb is the amount of charge transferred by a current of 1 ampere in 1 second. Typically 1 coulomb of charge, 1 coulomb is very large. It's a very large amount of charge. So essentially it's very difficult to have 1 coulomb of charge. So in most calculations we will have submultiples of the coulomb. For example, we'll have 1 microcoulomb being equivalent to 10 to the minus 3 coulomb. 1 microcoulomb, that's 10 to the minus 6 coulombs. 1 picocoulomb, that's 10 to the minus 12 coulombs, and many others. I have attached a table here which gives us a detailed description of some of the subunits of the coulomb. We have the decicoulomb, centicoulomb, millicoulomb, and their respective equivalences in coulomb. The common ones, however, are the microcoulomb and the picocoulomb. These are the 2 common ones that we'll be referring to. Okay, this is the same. So the microcoulomb is here, and the microcoulomb, 10 to the minus 12. They are very important. They are the most commonly used subunits of the coulomb. Let us now proceed and look at the types of charge. Not types of charge, properties. Let's look at the properties of charge. So charge has 3 main properties. The first property of charge is that charge is conserved. Just like mass and energy, charge also follows the universal law of conservation. For example, if I have a piece of silk and I have a piece of glass rod, if I rub the 2 together, if I get the glass rod and I rub it with the piece of silk, essentially after rubbing, the glass rod is going to become positive and the piece of silk is going to become negative. However, I have not created any new charge. I have simply redistributed the charge between the silk and the glass rod. And essentially, if I add up this charge, plus this charge, the objects will end up neutral again. So I haven't created any new charge. I have simply redistributed the charges. So charge is conserved, and we say charge cannot be created. Charge cannot be created or destroyed, but is simply transferred from one object to another. Okay, there we go. That's our first property of charge. Charge is conserved. The total amount of charge in the universe is constant. We cannot create charge, and we cannot destroy charge. We simply transfer it from one object to the other. The second property of charge is that charge has additive nature. By the way, charge is a scalar quantity. So when we are adding charge, we do not need to take the effect of direction into consideration because it is a scalar quantity. For example, if I have a perfectly conducting sphere with 1, 2, 3 negative charges, and I bring it into contact, I bring it to contact with another sphere of 5 positive charges, the resultant charge is going to be -3 plus +5, which gives me +2. So this is going to be the resultant charge. As a matter of fact, at the end of this process, we'll have positive charge here and a positive charge here. The charges will redistribute themselves equally in the spheres to follow the additive property of charge. That's the second property. The third property of charge, is that charge, this is very important, charge is quantized. Charge is quantized. The term quantized means that charge exists in discrete quantities. Discrete means countable. For example, 1, 2, 3, and so on. These are discrete quantities, and it is also known that the smallest possible charge that can be attained, the smallest possible charge which we also call the elementary charge, is that of an electron. Sometimes we call it electronic charge, and basically an electron has charge of 1.6 exponent -19 coulombs negative. So this is the basic charge, and all charge has to be a multiple of this, an integral multiple. So charge equals a submultiple or a multiple of the electronic charge, where n equals 1, 2, 3, and so on. This basic equation here is very important in as far as charge is conserved, because it tells us that charge is quantized. Charge can only exist as integral multiples of the electronic charge. By the way, the charge on the proton is positive 1.6 exponent -19 coulombs. So we don't care about the magnitude here. What is important is the figure 1.6 exponent -19, because that is the smallest elementary charge that we can ever have. We cannot have something like charge equals 2/3 of E. This is impossible because charge is quantized. We cannot have 2/3 of the electron charge. Charge is always quantized. It can only exist as integral multiples of E, the electronic charge. For more information on this, you can read about millicans. Okay, I need to get another color here. If you read about millicans oil drop experiment, Millikan did a very nice experiment to show that charge is quantized, and his results were exactly this. Amazing. So you should definitely check that out. That's the third property of charge, a very important property, that charge is quantized. Okay, so let's end this by looking at the ways of testing for the polarity of charge. So I will erase this. Testing for the polarity of charge. Testing for the polarity of charge. The word polarity here means positive or negative. So at the beginning, or in the lesson, we saw how Benjamin Franklin conventionally assigned a positive charge to the glass rod, and he assigned a negative charge to the piece of rubber. But we have many other materials that exist in nature. What if we are given a test object and we want to know its polarity? We want to know whether it is positive or negative. What do we do in that case? So let's look at a simple experiment to test for the polarity of charge. In this experiment, we will need the following requirements. The first requirement we'll need is obviously the test charge or the test body. Then we will need a negatively charged body. We'll need a negatively charged body. Essentially, this will be a piece of wood rubbed with cat fur. That works well, just like rubber that has been rubbed with cotton wool or wool. We'll also need a positively charged body, and for this experiment we'll stick with the glass rod that has been rubbed with silk. That will work for us. Okay, so let's begin carrying out the experiment. I'll create more space here. So the first step in carrying out our experiment, we are going to hang the body or suspend the test charge with a silk thread. So there we go, just to make it look nice. So this is our test charge. We don't know whether it's positive or negative or neutral. That's our test charge. We hang it on a silk thread, just making sure it is flexible. Okay, have more space here. Look at the second step. So in our second step, we bring the negatively charged bring the negatively charged body. In this case, our negatively charged body is going to be the piece of wood towards the test charge. So there we go. Oops, let me draw this better. So this is our test object, and this is our piece of wood. So this is the test charge, this is the negatively charged piece of wood. Okay, I'll just say negatively charged body, could be anything, but in this case it's a piece of wood, so it's a negatively charged body. Now if we bring the negatively charged body towards the test charge, one of these things could happen. Number one, if there is repulsion, then that means the test charge, is negative, and in that case we terminate the experiment because we have already known that the test charge is negative. Why do we conclude so quickly when there is repulsion? Because we know that like charges repel. We know that like charges repel each other. However, the second possible observation is attraction. And this is quite an interesting one. So if there is attraction, it means the test charge is either positive or neutral. It's quite interesting that neutral objects are also attracted by a charged body. We'll look at this later when we look at polarization, but very important here that attraction does not necessarily prove that the test charge is positive. It can mean that the test charge is positive or is neutral. So in order for us to distinguish between the two possibilities, we have to go ahead and look at number 3. Of course, if it was repulsion, then we terminate the experiment, but if it was attraction, then we cannot conclude yet. So we'll go to the third step, where we have to, okay, so I bring the positively charged body. In this case it is our glass rod towards the test charge. So again, there we have our test charge, and there we have our positively charged glass rod. So one of these things could still happen. If there is repulsion, that means the test charge is positive, in which case we terminate the experiment. If there is attraction, then depending on the results of step 2, if there is attraction at this step, then it means that the test charge is neutral, because there can't have been attraction for the negative body and for the positive body, for the wood and for the glass rod. So essentially, if there is attraction on the second stage, then that proves that the test body is neutral. So this gives us a very important conclusion here, that repulsion is the only, should put this in capital letters, repulsion is the only sure test for the polarity of a charge. So every time we see repulsion, that's good because it tells us that the charges are similar, but attraction can mean one of the two things. And every time we see attraction, then we have to go ahead and carry out the second step to see if the repulsion or if the attraction is consistent. We conclude it's neutral. If there is repulsion, we conclude that the object and the test body are of the same charge. Let me conclude this by summarizing all the steps of testing for the polarity of an object. So I'll make a simple flow chart here. The first step to do here is to hang the test body. So here we have the test charge. After hanging the test charge, you bring the negative body, the negatively charged body, and if you bring the negatively charged body, one of these things could happen. So let us create an if statement. So if repulsion okay, so here we ask, I think let's do this. Two things could happen here. If it is repulsion, then we conclude that the test charge is negative. Test charge is negative. If there is attraction, then that means it is either positive or neutral. So we have to go ahead and ask more questions in order to find out what the reality is. So we, not this, think at this stage we have to be bringing the positive body now. So we'll bring the positively charged body. In our case, it is the piece of glass. And after bringing the positively charged body, once more we ask what happens. And two things could happen. If repulsion happens, we've got to make this better. So if this is repulsion, then we conclude that the test charge is positive. If there is attraction, we conclude that the test charge is neutral. Also remember, it's very important to note here that neutral does not mean absence of charge. It means the existence of unequal but opposite charges in the same object, so that makes it electrically neutral. Okay, in the next part we are going to see electrostatic charging or electrification, the methods of electrifying an object. Okay, in this video we'll look at electrostatic charging, also known as electrification. So electrostatic charging or electrification is the process of making a material to obtain charges. The process of making a material to become charged is what we call electrostatic charging or electrification of an object. Now, it is important to understand where charges originate from before we proceed to look at further concepts of electrostatic charging and the methods of doing so. In our previous videos, we have looked at the modern picture of an atom. This is how it looks like. You have a nucleus, and inside the nucleus there are protons and neutrons. Neutrons have no charge, protons have a positive charge, so the net charge of the nucleus is positive. Then you have the energy levels. The energy levels, these are the energy levels, and so on these energy levels there are electrons. In fact, in the second picture you can see that these electrons form sort of an electron cloud around the nucleus, so the net charge here is negative because the electrons are negatively charged. Okay, so it's important to understand the atom before we proceed to understand how electrification takes place. So let's talk about the atom, or to be more specific, let's talk about atoms and ions. And basically an ion, I hope we all know what an atom is. An ion is a charged atom, and this is basically obtained by adding. Is this obtained? I should say this is formed after an atom has lost or gained electrons. So if an atom gains or loses electrons, then it becomes charged, and in that case we don't call it an atom, we call it an ion. We shall see under which case we call it a positive ion or a negative ion. Okay, let's move further. Just need to create more space here. Let's begin with what an atom looks like. So in a neutral atom, we know very well that inside our neutral atom here we have protons, and then we have electrons surrounding the proton. In a neutral atom, it is known that the number of protons is equivalent to the number of electrons. So since protons and electrons have an equal charge, if the number of protons is equal to the number of electrons, that basically means that the atom is electrically neutral. However, let us impose some conditions here. If the number of protons is greater than the number of electrons, then the atom has excess positive charge, and in that case we say it is positively charged, or we say it is a positive ion. So when does an atom become a positive ion? Basically an atom becomes a positive ion after losing some of its electrons. If it loses some of its electrons, then the number of protons inside the nucleus will remain unaffected, so it does not counterbalance the now few remaining electrons. That makes the net charge on the atom to be positive, and so we call that a positive ion. Okay, let's look at the second scenario. If the number of protons is less than the number of electrons, that means the atom has excess negative charge. So in this case, it is called a negative ion, and this happens when, so this happens when an atom gains excess electrons, most probably from another atom. So if an atom gains excess electrons, it becomes a negative ion, and if it loses electrons, it becomes a positive ion. It's important to remember here, this is important, it's important here that ions are created or formed only by adding or subtracting electrons from an atom. The bottom line here is that the nucleus cannot be altered, at least with ease. So it cannot be altered because the nuclear forces that bind these protons inside the nucleus are very strong. It is almost impossible to alter the nucleus, but it's very easy to take off some of these electrons or to add more electrons to the atom to make it an ion. And so with this background in mind, we are now ready to understand what happens during electrification, because it all happens at atomic scales and it is manifested at a micro scale where the whole object becomes charged. So we have the methods of electrification. Methods of electrification that we'll be looking at. The first method is going to be charging by rubbing, sometimes called by friction. Another method is going to be charging by contact, sometimes we say by conduction. And lastly, we are going to look at charging by induction. So let's begin with charging by rubbing. Let's create more space here. Charging by rubbing. So if we have two materials, and suppose two unlike, let me use a better word, if two dissimilar, that means the materials should not be the same. If two dissimilar materials are rubbed together, obviously if you rub two materials together, then there is going to be some heat energy generated. So heat energy is generated. Heat energy is generated due to friction. And because of the heat energy that is generated due to friction, the energy provides, or the energy enhances, the removal of electrons. The energy enhances the removal of electrons from one material to the other material. And basically what happens here is that the material that gains electrons, becomes, as we have seen for the case of the atoms, the material that gains electrons becomes negatively charged, since it has an excess negative charge, and the material that gains, the material that loses or donates electrons becomes positively charged, because it has few electrons remaining to counterbalance the positive nucleus, so it has a net positive charge and it remains positively charged. Let's illustrate this with the case of a glass rod. So assuming we have a glass rod which is originally neutral, and we have a piece of silk which is also neutral. If we bring these two objects together and try to rub them, if the piece of glass and the piece of silk, let me indicate the silk like this, if the piece of glass and the piece of silk are rubbed together, in the end the glass rod is going to lose electrons, so it becomes positively charged, while the silk is going to gain the electrons, so it becomes negatively charged. It's important to note here that the electrons lost by the glass are acquired by the silk. So once again, the law of conservation of charge is obeyed here, because we have not created any new charge. We have simply transferred charge from the glass rod to the piece of silk. So this one here, we say it has lost electrons. It remains with a net positive charge. This one here, the piece of silk, has gained electrons, so it has an excess number of electrons, therefore it is negatively charged. Now, the exact factors that lead or that determine which material loses or gains electrons are rather important to discuss. So we have about 3 factors that influence the loss of electrons, and these factors are basically the electronegativity, of the material or of the atom. Basically, electronegativity is the ability of an atom, to attract shared electrons towards itself. So in the previous example of the glass and silk, it turns out that the silk is more electronegative, so it attracts all the electrons to itself, while the glass rod is more electropositive. Another factor here is electron affinity. The electron affinity, so this is, I could say, the love of electrons. Basically, objects with a high electron affinity tend to take all the electrons, so they become negatively charged, while the opponent becomes positively charged. And lastly, the work function. Maybe not last, but also we have the work function. So the work function is the energy required to remove a free electron from the surface, of a metal. Work function is mainly defined for metals, although we can also talk about work function for other materials. But in terms of electrostatics, work function could be a general term for all materials. In photoelectric theory, work function is very specific to metals. Okay, lastly we have ionization energy. And basically ionization energy is very similar to work function, only that with ionization energy we are not taking free electrons, but we are taking the loosely bound electron from an atom. So basically with these two, work function and ionization energy, the smaller the work function or ionization energy, the easier it is for the material to lose electrons. So this method, the method of, let me clear the screen, the method of charging by rubbing is ideal or very common, is ideal for insulating materials. However, conductors can also be charged by this method. Conductors can also be charged by this method, provided they are well insulated and isolated from the earth, which may take away or add electrons to them. Okay, I'll finish this by showing you a simple table here. This table here shows something called, okay, so in this table shows something called the triboelectric series. And basically this is a series that determines who loses electrons and who gains electrons. In this table, as we go up, we can see that there is more tendency to gain positive charge. So these guys lose electrons as we go up, and as we go down, these guys tend to gain electrons because they have a high electronegativity. So if you take an example like silicon rubber, which is at the bottom of the group, and you rub it with asbestos, it is most likely that the silicon rubber will become negative and the asbestos will become positive. Ideally, we always rub materials on top of this list with materials at the bottom of the list to get a better experience of what charging looks like. We always get a combination of materials on top with materials at the bottom. That gives us a better experience when charging. The word triboelectric comes from, it's actually another word to mean frictional electricity. Frictional electricity. And by the way, the method of charging by rubbing is also called the triboelectric method. So this term shouldn't be that bad. So be sure to pause the video and look through this list. Perhaps I need to make it bigger. Look through this list to determine which materials should be rubbed with other materials and which kinds of charges are generated. Okay, let us now proceed to another method. Before we proceed to another method of charging, it is important to note here, that when insulators are charged by rubbing, the charges only exist at the surface, because these materials basically are insulators. They cannot transmit charge inside. For example, if a piece of glass is rubbed against human hair, let's assume the piece of glass gains positive charges. These positive charges will only reside on the surface, not inside the material of the glass, but rather outside the surface, because this is an insulator. The charges cannot distribute themselves inside. Okay, basically also the negative charges on the hair will reside on the surface. So that's very important to note for charging by rubbing, especially for insulators. Let us now look at another method of electrification, and that is charging by contact. So this basically is a method. This is a method commonly used. It's a method commonly used to charge conductors. And the way this method works is that it works by simply bringing two conductors to contact, and they will get charged immediately. Let's look at an example here. If I have a piece of aluminum, so let's say I have an aluminum foil previously charged with a negative charge. If I bring it towards a neutral sphere, this sphere should be put on an insulating stand. So this is a neutral sphere. This is an insulating stand. if I do this, then I bring the two objects in contact. Okay. So if I bring the two objects in contact, basically what will happen is that at the end of the experiment, oops, let me draw this here. So I have the aluminum foil and the neutral sphere in contact. The charges are going to distribute themselves between the aluminum foil and the neutral sphere, and in the end I'll have the aluminum foil and the neutral sphere independently, each of them having negative charges in it. So this method is called charging by contact. It is a very quick and easy method for charging conducting materials. Obviously, this method cannot be used to charge insulators because insulators cannot transmit the charge even after contact. Let me go ahead and look at the third method of charging, and that's going to be charging by induction. Charging by induction. So the method of charging by induction is used, I should say this method is used to charge conductors without physical contact between these two conductors like it is in the previous method. So the method of charging by induction is used to charge two conductors without their physical contact. Let us look at some examples of charging by induction. Samples of charging by induction. The first example we'll look at is charging a sphere conducting sphere. Let's charge it positively by induction. Charging a conducting sphere positively by induction. Remember, this method does not involve any physical contact. So the first step, okay, use a better color. The first step is to have our insulator, our conducting sphere, put perfectly on an insulating stand. Put it on an insulating stand for obvious reasons. If this sphere is made to touch the earth, then it will always be at zero potential and it cannot be charged. So here we have our neutral sphere. It's a conducting sphere, it does not have any charge. In the next step, since we want to charge the sphere positively, we are going to bring a negative charge towards it. So there is my conducting sphere. So I bring a negatively charged body It could be a piece of wood or a piece of rubber. I bring it near here. So remember, for a neutral sphere, this basically means there is an equal number of opposite charges, so an equal number of positive and negative charges. So basically, these charges that were initially neutralizing each other will now redistribute themselves due to the presence of a negative charge. So positive charges will align themselves close to the negative charges because of the fundamental law of charges, that like charges attract, unlike charges attract. So negative attracts the positive, while the negative charges will be repelled. It's important to note here that the inducing charge, is equal to the induced, the inducing charge is equal to the induced charge. So I have the same number of charges here as they are in the inducing charge. Basically, there will be almost an infinite number of charges here, so we only have to make sure that the inducing charge is equal to the induced charge. That's my second step in the process. The third step in the process, while keeping the negatively charged object in place, so I'm going to earth the sphere. So I'm going to connect the sphere to the earth. This symbol here means earth or ground. Basically, the earth or the ground has plenty of charges. It has both positive and negative charges. We say it is at zero potential, so it can contribute any charge that we need. In this case, all the electrons are going to be drawn because they are not being held by any charge here, while the positive charge is bound to stay here as long as the negative body is still in place. And lastly, the negative body is then removed, and after it is removed, the positive charge will redistribute itself in the sphere, and now the sphere has a net positive charge. These steps are very critical. If we take away the negative body while connecting the sphere to the earth, then the sphere will not be charged. We have to make sure this body remains in place while we are earthing our sphere. Let's make this more interesting by charging two spheres oppositely. So our second exploration here, let us charge two spheres, charging two spheres oppositely at the same time. So the first step is to have our two spheres. We have to make sure they are insulated from the ground. They are metallic spheres because they are conducting. The second part, while these spheres are in contact, we bring a charged body here. It could be positive or negative. Let's suppose that this body is positively charged. If this body is positively charged, because the two spheres are in contact, they will behave as though they are all a single metallic sphere. So negative charges will be attracted to this end, and positive charges will be repelled to the other end, because positive attracts negative, but positive repels positive. So this is a positively charged body. Positively charged body. We could also do this with a negatively charged body. This would be positive, this would be negative. Same thing. Okay. The third step, we have to make sure that this remains in place, and while it remains in place, we separate the two spheres so we separate the two spheres. This one remains with a negative charge, this one remains with a positive charge, and lastly we take away the charged body, and our spheres will not lose their charge in this case because they were separated while the inducing charge was still in place. Still, step number C is very important, because if we take away the charged body before separating the spheres, then we will not have the process work very well. In fact, the spheres will not get charged. If the charged body is taken, these charges will immediately cancel out quickly, and so we will not have any charge on them, and they will become neutral again. Okay, let's have another interesting example of charging spheres by induction. In this example, we are going to charge two spheres, charging two spheres. Okay, the previous example, we charged them oppositely. One became positive and another became negative. In this example, let's charge the two spheres simultaneously at the same time so that they obtain the same charge. Let's say they obtain a negative charge. Okay, let's just take this for exploration. So the first step is to have our spheres well insulated and separated. Okay, very important. Then we bring, since we want to charge them so that they get a negative charge, we have to bring a positively charged body. Positively charged body. For example, a glass rod that is rubbed with silk. The second step, okay, shouldn't have done this at this step. So we have our two spheres that are insulated from the earth. Since we want to have them become negatively charged, at the second step, I will introduce the charged object. So there we go with our positively charged object. When I bring the positively charged object, this part will become negative. This part will also become negative because the positive charge attracts the negative charges in every sphere, and the positives are going to be repelled to the far end. In the third step, I keep the positive body in place. Keep the positive body in place. I only do a simple modification here. This is negative, positive, negative, positive. So with the positively charged body still in place, I connect the spheres to the earth, and basically electrons will move upwards to neutralize. Electrons are negatively charged, so they would move upwards to neutralize the positive charges. Remember, protons do not move, only electrons can move. So electrons would move to neutralize the positive charges. And lastly, I can remove the earthing and the positively charged body, and I will end up with two spheres that are negatively charged. And there we go. So we can do a lot of other interesting stuff with charging by induction. You can try playing around with others. You can try doing all these examples again, but with opposite charges. Okay, let us conclude this part by looking at polarization. And this mainly happens in insulators. So let's say polarization in insulators. So polarization is the displacement of the centers of positive and negative charges, the displacement of the positive and negative charges in an atom when placed in an electric field. We'll see what that is in a moment. When placed in an electric field. So we all know that for a normal atom, the protons are at the center and the electrons are in a cloud around the nucleus. So this is a normal atom, but for a polarized atom, if I have my atom and I place it in an electric field, okay, so we have an electric field. This means there is an electric force acting in this direction. The positive charges are moving in this direction. This is what happens. The nucleus will remain at the center because it does not usually move, or at least it will be slightly displaced, but in most cases it will remain at the center only with a slight displacement, and most of the electrons are going to be shifted to this side. So as you can compare the two atoms, in the polarized atom, the center of the negative charges has shifted towards this side because there's an electric field acting in that direction. Also, you can see the shape changes from being a regular circular shape, from a regular shape to an oval shape that illustrates polarization. The negative charges have shifted to one side and the positive charges have shifted to the other side, and in that case we say the atom is polarized. So let's look at a broad view of polarization in insulators. Let's look at polarization in a broad sense in insulators. Suppose we have, suppose we place an insulator in an electric field. Suppose we place an insulator in an electric field. So the electric field is in this direction. This is our insulator. This is the electric field. This is the insulator. Basically, this insulator has many atoms in it. Maybe I could show a before and after picture here. This is what our insulator looks like originally. So without field. This is no electric field. In this case, all the atoms are well aligned. So these are the atoms in our insulating material. These atoms are unpolarized. This is our insulating material. So the positive charge is at the center originally, and the electron cloud is surrounding the atom as it should for a normal atom. But what happens after an electric field has been applied is that the shape of the atoms is going to change. So these are polarized atoms now. As you can notice, their shape changes. I'll only draw a few. Their shape changes. Since the electric field is in this direction, the negatives will all go to this side and the positives will go to the other side. Okay. Positive, minus, positive, minus, positive, negative, positive, negative, negative, positive, negative, positive. So as you can see, these are now polarized atoms. These are polarized atoms. Also, notice from this diagram that the positives and the negatives in this case are going to neutralize. Also here, the positives and the negatives here are going to neutralize. So the final effect will look like this. Okay. Finally, our insulating material would look like this. This side is going to be negatively charged and this side is going to be positively charged. So it is as if induction has occurred inside the insulating material. So virtually this is not induction, it is called polarization, and this would be what we would somehow call induction in insulators, but it has a specific name called polarization. So this one here is now a polarized insulator, and because this insulator is polarized, if we bring a charged object, so if we bring, let's suppose, if we bring a charged object towards a polarized insulator, this polarized insulator, it's very important to see here that it was originally neutral. So if we bring a charged object towards a polarized insulator, then there will be attraction. And this explains why neutral bodies are attracted by charged bodies because of the process of polarization. I'll show you an example in a moment. As you can see in this diagram, in this picture, okay, now, so in this picture, as you can see, the pieces of paper are being attracted by the comb, These pieces of paper are insulators and they are originally uncharged, but when a positively charged comb, after rubbing it with hair, when it is brought to the papers, they are able to be attracted. Let's see how this happens. So we have a comb. Okay, hope that works. My comb is bad. Okay, this comb is having positive charges on it. Let's say it has positive charges on it. And then this is the piece of paper. This is the piece of paper. So what happens is that because of the positively charged comb, this part is going to become negative and this part is going to become positive. That is something called polarization. We have just seen how this happens. And because the positive charges and the negative charges attract each other, because these two charges are near than the distance between the positive and positive, there is going to be greater attraction. And so the neutral paper is going to be attracted by the positively charged comb by this process of polarization. So this is a very important phenomenon, and you should also perhaps read about more interesting stuff in polarization, like polar molecules. Molecules such as those of water and hydrogen chloride have some natural degree of polarity, so they can easily be polarized to a higher extent. Thanks for watching this episode. Next we'll look at the gold leaf electroscope. The gold leaf electroscope. The gold leaf electroscope is a device we use in the physics laboratory to investigate the behavior of charges. So let's look at the structure of the gold leaf electroscope. The gold leaf electroscope consists of a brass cap, highly conducting brass cap, and a stem which extends all the way down. This whole system is enclosed in a metallic casing to prevent wind and other external effects. The lower part of the gold leaf electroscope is insulated from the earth. Also, the point where the metallic casing touches the brass cap and the stem is also insulated. So we have a brass cap here. Then we have a stem also made of brass. It is superconducting to allow charges move to and from the brass cap. So this is the stem. This is the metallic casing. The metallic case. To finish up the diagram, on this brass stem that extends down here is attached a very thin foil of aluminum or gold, and that is what we call the gold leaf. It is very flexible at this joint, so it can diverge to this direction and to this direction, and that is the most important part of the gold leaf electroscope, as we shall see later. So this is the gold leaf. It is a thin foil of gold or aluminum. To prevent the effect of the metallic case getting charged, the metallic case is often connected to the earth. So there we have our metallic case connected to the earth. Okay, one more thing. This whole gold leaf electroscope, in order for us to observe what is taking place inside, it is enclosed in a glass window. So we have a glass window, this point. This allows us to see the activity of the gold leaf, the divergence of the gold leaf. Before we proceed, let's first see what we can do with the gold leaf electroscope, just in form of highlights. So let's look at the uses of the gold leaf electroscope. Uses of the gold leaf electroscope, we abbreviate this as GLE. I'll use this most commonly for the next chapters. So we can use the gold leaf electroscope to detect the presence of charge. Detect the presence of charge. We'll see in a moment how that can be done, how we can use the gold leaf electroscope to detect the presence of charge. We can also use the gold leaf electroscope to compare the strength of charges or the magnitude of charge on a material. We can use the gold leaf electroscope to distinguish or to identify conductors and insulators. Conductors and insulators. We can also use the gold leaf electroscope to test for the polarity of charge. Test for the polarity of charge. In our previous lessons, we saw how we can test for the polarity of charge using a simple experiment, but that simple experiment has many external factors that make it difficult, so we'll look at a better method of testing the polarity using a gold leaf electroscope. Now, before we look at all these uses of the gold leaf electroscope in details, it is necessary to understand how this gold leaf electroscope can be charged, because before we can use it to do some of these things, we need to have the gold leaf electroscope charged. So let's see how we can charge the gold leaf electroscope. Basically, we can charge the gold leaf electroscope using two methods. We can charge it by contact or by induction. So we'll first look at the method of charging the gold leaf electroscope by contact. So let's charge the gold leaf electroscope. Let's charge the gold leaf electroscope negatively by contact. So we have our gold leaf electroscope. This is the brass cap. This is the conducting stem. All this is enclosed in a metallic case. The bottom part is insulated. Shouldn't forget that. And there we have our gold leaf. For an uncharged electroscope, the gold leaf has no divergence, it is straight. Let me illustrate that. So this is how the gold leaf looks like for an uncharged electroscope. I connect the metal case to the earthing so that we don't get problems while charging the gold leaf electroscope. So here we have the uncharged gold leaf electroscope. Okay, in order for us to charge the gold leaf electroscope negatively by contact, let's bring a negatively charged object and make it to touch the brass cap. So before the negatively charged object touches the brass cap, let's see what happens. So we have our gold leaf electroscope. Once more, we have the stem extending down. Oops. Okay. So there's our gold leaf electroscope. This is insulated. And then let us bring a negatively charged object towards the gold leaf. So this is a negatively charged object. We bring it towards the gold leaf. Since the gold leaf, oops, didn't indicate the gold leaf. There is our gold leaf. So since the gold leaf is made up of a brass cap which is highly conducting, that means since it is a conductor, it has quite a number of charges that are delocalized in it. The negatively charged body will induce positive charges on the brass cap, and it will repel negative charges. Negative charges will be repelled down to the gold leaf and the stem. Because negative charges will repel the other negative charges, the effect will be a force of repulsion. So let me indicate the force of repulsion. Go to draw this better. Okay, so there we have our gold leaf is going to diverge because of the repulsion caused by like charges. There we have the gold leaf. It diverges because the object, the negatively charged object, attracts positive charges to the brass cap and it repels negative charges down. Negative charges and negative charges repel each other. The gold leaf is flexible at this joint, so it can be easily repelled, and we see the divergence of the gold leaf. There it is. Let's see the final steps of charging the gold leaf negatively by contact. Okay, have the gold leaf again, step number 3. Okay, good, to create more space. Step number 3. There's our gold leaf. Okay, it's insulated. Remember, our gold leaf was repelled because of negative charges on the stem and the leaf. We had positive charges here in the previous illustration, and we had a negatively charged body. So in step number 3, we make the negatively charged body to touch the gold leaf like this. So when the negatively charged body touches the gold leaf, there is going to be charge exchange between the negatively charged body and the brass cap. All these are perfect conductors, so charge exchange can easily occur. So at this point there is charge exchange, and these charges are going to neutralize each other, the positive and the negative charges. And finally, charge exchange. This charge exchange leads to neutralization, and so finally there's our gold leaf electroscope. Oops. Okay. And there we have our gold leaf. Now, because these charges have neutralized, the negative charges that were under here, since the negatively charged body is now removed or neutralized, the charges will redistribute themselves throughout the whole gold leaf electroscope, and so this leaf is going to stay diverged as it is. So this divergence tells us that the gold leaf has been charged. That means the charge on the stem is the same as the charge on the gold leaf, so the gold leaf is showing a divergence. Now our gold leaf has been charged negatively, so this is a negatively charged gold leaf electroscope. Let's recap the steps that we've taken to charge the gold leaf electroscope negatively. We started off with an uncharged gold leaf electroscope, then we brought a negatively charged body and we made the negatively charged body to come close to the brass cap of the gold leaf electroscope. Positive charges were induced on the brass cap due to the negative charges, while negative charges were repelled down the stem and the gold leaf, causing a divergence due to like charges. On step number 3, we made the negatively charged body to touch the brass cap, and because this body and the brass cap are perfect conductors or conductors in general, there was charge exchange leading to neutralization of these positive charges on the brass cap. Finally, we took off the negatively charged body, or the neutralized body at this point, and the negative charges at step number 3 redistributed themselves throughout the gold leaf, the brass cap, the stem, and the gold leaf. And the gold leaf maintains a divergence because the negative charges are still here, and they are repelling each other. So our gold leaf has been charged negatively. I'm pretty sure you can follow the same steps 1, 2, 3, and 4 to charge the gold leaf positively by contact. It's quite an easy exercise, so be sure to pause the video and try to charge the gold leaf positively by induction. Next, we'll look at method 2, where we'll charge the gold leaf electroscope by the method of induction. So let's do that. Let's charge the gold leaf electroscope by induction. Remember from our prior videos, induction is a method of charging objects without directly bringing them to contact. So let's charge our gold leaf. Let's charge the gold leaf electroscope. Let's charge the gold leaf electroscope negatively. Perhaps this will work. Okay, let's charge it positively. In the previous video we have charged it negatively, so let's charge it positively. Let's give the gold leaf electroscope a positive charge. We could do that using the method of contact as we have just seen, but we want to explore how we can do that by the method of electrostatic induction. So step number 1, we begin out with our uncharged gold leaf electroscope. There we have it. The brass cap, the conducting stem. There we go, the casing or the glass window, the insulation down here. And by the way, the earthing on the metallic case is optional, so I'll leave it out for this case. Okay, just to make sure this case does not affect our experiment. The contact here of the metallic casing with the rest of the gold leaf electroscope are actually insulators. Also, for an uncharged gold leaf electroscope, there is no divergence on the gold leaf, so there is the gold leaf. Let's proceed to the second step. We are charging the gold leaf electroscope positively by induction. Let's go to step number 2. In step number 2, we have our gold leaf electroscope. Nice. The brass cap, the stem, okay, the glass window. Okay, there we have it. The bottom insulator. In this case, since we want to charge the gold leaf electroscope positively, remember how the method of induction works. We'll have to bring a negatively charged object. So I bring a negatively charged object. The negatively charged object is going to attract positive charges. It's going to attract positive charges to the brass cap, and it will repel negative charges down the stem and the gold leaf. So let me indicate the gold leaf. Because the negative charges will be both on the stem and the gold leaf will show a divergence. Oops, let me use a uniform color. So there is going to be a divergence because of the negative charges on the stem and on the gold leaf. That's step number 2. Let's go to step number 3. See how we can charge the gold leaf electroscope positively by induction. Step number 3. Have my gold leaf electroscope. The stem. There we go. The casing. Have to make sure this is correct. Remember, the earthing is optional, so I have not indicated the earthing on the metal case in this experiment, but you can do that. It's no problem with that. So with my negatively charged body still in place, remember, these are positive charges at this point, positive charges all the way down. Oops, negative charges repelled down. Also, the gold leaf is still diverged. So I'm going to connect the brass cap of the gold leaf electroscope, not the metal casing, but the brass cap. I connect it to the earth. Because these positive charges are bound, important here, these charges here are bound. As long as this body is still in place, they cannot be removed. The positive charges are bound to remain here as long as the negatively charged body is still in place, so they cannot move, but rather these electrons are going to flow out through the earthing. So the electrons are going to flow out and only the positives are going to remain. And when these negatives flow out, so I now draw this accurately, when the negative charges flow out, essentially the gold leaf, so these charges will all flow out. We don't have anything there. Essentially what will remain, the gold leaf is going to remain with no divergence. So the gold leaf comes back to the normal state. And then finally, step number 4, have the gold leaf electroscope here. Have this. Okay, I have the positive charges that were here. In the last step, I remove the negatively charged body. I also disconnect the earthing. So the charges, the positive charges, will now redistribute themselves on the whole brass cap and the stem, and the gold leaf is going to diverge again because of the positive charges on either side, the stem and the gold leaf. So the gold leaf is going to diverge again. Okay, let's have a quick recap through the steps of charging the gold leaf electroscope positively by induction. Step number 1, we began with an uncharged gold leaf electroscope. Step number 2, we introduced a negatively charged body. This negatively charged body induced positive charges on the brass cap. Negative charges were repelled down, causing the gold leaf to diverge. On step number 3, with the negatively charged body still in place, we connected the earthing to the brass cap. When we connect the earthing to the brass cap, the negative charges from step number 2, the negative charges down here, the electrons, will flow out. Electrons cannot flow in to neutralize this positive charge because the positive charge is bound to remain here as long as the charging body is still in place, the inducing body, sorry. As long as this body is still in place, you cannot take away these positive charges. So only these electrons flew out, and afterwards we disconnected the earthing. We also removed the negatively charged body, so the positive charge redistributes itself and the gold leaf diverges. Once again, this shows that the gold leaf is now charged positively. Okay, I'm also pretty sure you can follow the same steps to charge the gold leaf electroscope negatively by induction. The only thing you will do is to swap this with a positively charged body. So also when you connect the earthing, notice what will happen will be the opposite. So be sure to pause the video and try it out. If you have any challenges, leave a link in the leave a comment in the video below. I'll try to respond. Okay, let's now look at how to detect the presence of charge using a gold leaf electroscope. So detecting the presence of charge using a gold leaf electroscope. Suppose we have a test body and we are not sure whether the test body is charged or not. The gold leaf electroscope can help us to tell if there is charge present in that body or not. So let's have a gold leaf electroscope, uncharged gold leaf electroscope to be more specific. So there we have our uncharged gold leaf electroscope. Uncharged gold leaf electroscope. This is our gold leaf. In our second step, let's bring the test body. So let's say this is our test body. We are not sure whether there is charge on this body or not. So we bring the test body near the brass cap of the gold leaf electroscope. So there we go. Oops. Okay. There we go. I'm of course drawing the gold leaf electroscope roughly, but be sure to make this better. So if we bring the test body, one of these things could happen. Let's look at the possible observations in this experiment. So the possible observations are as follows. If we bring the test body, the possible observations are as follows. Just to be clear, I didn't mean to show divergence here. We don't actually know what happens. Anything could happen at this point. So just want it to be normal. Anything could still happen at this point. Now the possible observations here are, if the gold leaf diverges, then the test body has charge in it, or I should say the test body is charged. Another possibility is if there is no change on the gold leaf. In other words, if the gold leaf remains constant, then the test body is uncharged. So let us justify the first observation. Let's assume that the test body is positively charged. From what we've seen previously, if the test body is positively charged, negative charges will be attracted here, while positive charges will be repelled downwards, which will cause the gold leaf to diverge because of like charges down here. This would also happen if the test body was negative. Positive charges would be induced here and negative charges would be repelled down, causing the gold leaf to diverge. So whether the test body is positively charged or negatively charged, as long as there is a divergence, if the gold leaf diverges, that's enough to tell us that the test body has charge in it. But if there is no change in the divergence, if we don't see any observation, so we conclude that the test body is uncharged. And that's how we can use the gold leaf to detect the presence of charge in an object. At this point, we are not yet sure what type of charge is it, whether positive or negative, but at least it's good that the gold leaf electroscope can help us determine what type of charge, can help us determine whether the object has charge in it or it does not have charge in it. Okay, let us now look at how to compare the strength or the size of charge on different objects. Now let's begin with an assumption. Suppose we have two positively charged glass rods. Suppose we have two positively charged glass rods and we need to compare the magnitude of charge on each. How do we do that? So this is what we do. Let's assume we have two gold leaf electroscopes for this experiment. So there's my first gold leaf electroscope. And let me have another one here. Of course, I could do this with one gold leaf electroscope, but just to make my experiment easier, I will use two gold leaf electroscopes. Okay, so I bring the test bodies. So let this be test body 1. Then test body 2 or B. Now since both bodies A and B are charged, that means there is going to be a divergence on the gold leaf. Because both A and B are charged, I'm very sure there's going to be a divergence. We have just seen how the gold leaf can help us detect the presence of charge. If you bring a test body and there is divergence, it means the body is charged. So in this experiment, we already made a supposition that we have two positively charged glass rods. Of course, they could be negative, it doesn't matter. If you bring them near the brass cap, you will notice a divergence. This divergence here is measured in terms of the angle of divergence. So let me assume the angle here is θ1 and the angle here is θ2. So we are interested in the divergence of these two gold leaves. So if the divergence θ1 is greater than θ2, then the charge on A is greater than the charge on B, and if theta 2 is greater than theta 1, we conclude that the charge on B is greater than the charge on A. So the divergence tells us how much the charge is. In fact, I'll make this end by making a small note here. The degree of divergence, of the gold leaf is directly proportional to the magnitude of charge. So if the charge on A is greater than the charge on B, then the divergence theta 1 will be bigger than the divergence theta 2. If the charge on B is greater than the charge on A, the divergence theta 2 will be greater than the divergence theta 1. Let us now look at another use of the gold leaf electroscope. We'll see how to distinguish between conductors and insulators using a gold leaf electroscope. So the gold leaf electroscope can help us to determine the difference between, or can help us to determine conductors or good conductors and insulators. This is very important if we are looking for materials to use for different purposes where the conducting or insulating properties are very paramount. Okay, so let's begin out with a gold leaf electroscope. Choose to begin out with a gold leaf electroscope. A charged gold leaf electroscope this time round. So I have a charged gold leaf electroscope. Whether I charge it positively or negatively, it doesn't matter. What matters here is that it is charged. So for any charged gold leaf electroscope, we know that the leaf is going to be diverged. So there we go. Our gold leaf is already diverged since our gold leaf electroscope is charged. So that's step number 1. We charge the gold leaf electroscope either positively or negatively. Step number 2. We bring the test objects or the test bodies and make them touch the brass cup or the cup of the gold leaf electroscope, just like this. Have the gold leaf electroscope. So there we go with the gold leaf electroscope. We bring the objects that are under test. Let's say this is one of the objects. These objects have to be held by hand. Oops, can't draw this very well. These objects are held by hand so that the hand acts as the earthing. So these objects are made to touch the cup of the gold leaf electroscope. Now when that happens, one of these things could happen. Let me show you the possible observations here. Okay, so the possible observation the first possible observation, if the leaf falls means if the divergence goes down, if the leaf falls quickly, then the test body is a good conductor. So if the leaf falls quickly, it means this conductor was able to conduct electrons either to the gold leaf electroscope or out of the gold leaf electroscope to neutralize it, so that the leaf falls very quickly. So that would mean that the test body is a conductor. Another possible observation is that if the divergence remains constant, so if the divergence remains as it is, then we conclude that the test body is an insulator. If we touch the brass cup with an object and the divergence does not change, it means it could not conduct electrons to or from the gold leaf, so it is an insulator. Also, another possible observation is that if the leaf falls slowly, we conclude the object is slightly conducting. So we could say it's a semiconductor because it has a small degree of conductivity. Some electrons can pass through, but at a slow rate, so the leaf falls slowly. And that's how we can use the gold leaf to compare the degree of conductivities of different materials and also distinguish between conductors and insulators. Make sure that in this experiment the material has to be held by the hand or it has to be connected to the earth so that electrons can easily flow in and out through it if it is a conductor. We'll end this episode of the gold leaf electroscope by looking at how to test for the polarity of charge using the gold leaf electroscope. How to test for the polarity of charge using the gold leaf electroscope. Now, in this experiment, let's begin with a charged gold leaf electroscope. Unlike the previous experiments, I want to begin with an electroscope whose charge I know. So let's begin with a negatively charged gold leaf electroscope. Of course, I could also begin with a positively charged gold leaf electroscope. Doesn't matter. So there we have our gold leaf electroscope. Oops. Our gold leaf electroscope. There we go. Since it is positively charged, we know very well that the gold leaf is going to be diverged because we have positive charges all over and the positive charges repel each other. So that's how the gold leaf electroscope is going to look like. Should make this an insulator. Like, I'm drawing it not so good, but hope you get the idea. So we begin with a negatively charged gold leaf electroscope. The next step I'm going to do is to bring the test body near the cup or the brass cup of the gold leaf electroscope. Okay, so I have the gold leaf electroscope still. It is charged positively. There we go. The gold leaf electroscope. There it is. The leaf is diverged because of the positive charges, and there we have our test body. So this is our test charge. We do not know the charge on this body, so we bring it near the cap of the gold leaf electroscope. One of these things could happen, so let's look at the possible observations in this experiment. Let's look at the possible observations here. The possible observations here are as following. The first observation we can have is that if the leaf of the gold leaf electroscope falls, let's see if the leaf, let's begin the better way. If the leaf diverges further, then the test charge is positive. Wait a moment, looks like we made a mistake. Okay. Oops, I didn't see this. I wanted to start with a negatively charged gold leaf electroscope. I ended up making it positive, but that's okay. So that's positively charged gold leaf electroscope. It's fine. So let's proceed. So in this case, if the divergence of the leaf increases further, then we conclude that the test charge is positive. Let me show you why. If this is a positive charge, then it means all the positive charges will be repelled down. So that means we'll have more positives here, making the leaf to diverge even further up. So that is the first case. If the test charge is positive, then the divergence will increase further. But if the divergence falls, then the test charge is either negative. The test charge is either negative, but there is also a possibility that the test charge is neutral. So if we don't get an increase in divergence, we cannot conclude by a fall in divergence that the test charge is negative, because there are two possibilities. It could be negative or it could be neutral. So in order for us to distinguish between the two possibilities, we have to charge the gold leaf electroscope with another type of charge. So we began by charging it positively. So let's now charge it negatively. So let's charge it negatively. So the GLE is okay. This is step C. The GLE is discharged. And charged negatively. Is discharged and charged negatively. And the test body is brought again near the cap. Now if we do that and we bring it near the cap, let's see the possible observation here. if there is an increase in divergence, that would mean that the test charge is negative. I don't need to illustrate that so much, but there you go. This is our gold leaf negatively charged. It would be already diverged, but if we bring a negative test charge, it means we'll have more negatives. More negatives repelled down, so the divergence will increase even further. But if the observation is a fall in divergence is the angle here. If there is a fall in divergence, then we conclude that the test charge is neutral. So let's recap the steps taken in this experiment. We start out in this case with a positively charged gold leaf electroscope. We bring the test charge, and if the test charge is brought near, one of these things could happen. The leaf can diverge further and increase in divergence, in which case the test charge would be positive, because if the test charge is positive, these positives would increase down here, making the divergence to go up. But if the divergence falls, that could mean the test charge is either negative or neutral. To distinguish between the two possibilities, we have to discharge the gold leaf and charge it again with a negative charge. And after charging it negatively, we repeat the steps. We bring the test body again, and if we see an increase in divergence, then the test charge is negative. However, if we see a fall in divergence, then we conclude that the test charge is neutral. So you can only conclude that the test charge is neutral if you get the same observation of a fall in divergence in both experiments. If both experiments tell you that the divergence is falling, that means the test charge does not have a specific charge, it's neutral. But if you see divergence, that tells you the test charge is similar to the charge of the gold leaf electroscope. So let's end with a note here. Divergence, I think I should say further divergence. Further divergence is the only sure test. Further divergence is the only sure test for polarity of the charge. So a fall in divergence cannot be used to tell us what the polarity of the charge is. Okay, thank you for watching this episode of the gold leaf electroscope. In the next video, we will see charge distribution in conductors. Also, it's taking time to compile this video and make sure everything comes together. So I would appreciate if you give me a subscribe, a like, and a comment so that I continue doing more of this stuff. Thank you. Let us now consider the distribution of charge. Let us consider the distribution of charge in a conductor. The distribution of charge in a conductor. Throughout the course, we have discussed that conductors are materials that allow free movement of charge. So this is very important, that since conductors allow free movement of charge, if a conductor is charged, the charges will redistribute themselves, in the conductor, but this distribution is going to be depending on the shape of the conductor. So different conductors with different shapes have different charge distributions, and this, as we shall see later, yields very interesting consequences like the corona discharge that we will see later. So different materials, different conductors with different shapes have different charge distributions. Whenever a conductor is charged, let's say this here is a conductor, if I give it a charge, say by contact, this charge is going to distribute itself depending on the shape of this conductor. Okay, this is just a rough sketch. So let's perform some simple experiment to see the distribution of charge within conductors. So let us examine investigating charge distribution. Investigating charge distribution in conductors. In order to do this, we'll need a few things here. So requirements, we'll need a gold leaf electroscope. We'll also need something called a proof plane. Now I'll talk about a proof plane briefly. A proof plane is a device for picking charge from a conductor. So what basically we are going to do is to charge up a conductor, and then we'll pick charge from different parts of the conductor and we investigate how this charge is. Okay, let's go ahead and do this. So we'll investigate charge distribution for different shapes of conductors. We'll look at the following. We'll begin by looking at a uniform sphere. We'll go ahead and investigate the charge distribution in a pear-shaped conductor. We'll also look at a hollow conductor. Okay, so we are going to investigate the charge distribution due to these three types of conductors. Let's begin with a uniform sphere. So let me have more space here. Okay, maybe not. I'll have this charge distribution. Charge distribution on a uniform sphere. Should say conducting sphere. But anyway, we are talking about only conductors. So in our experiment, we are going to have a uniformly conducting sphere. Let's put it on an insulating stand. So we charge this conductor. So our step number 1, let's charge the sphere either positively or negatively. It doesn't matter. Let's assume I give it a positive charge. So I give my sphere a positive charge. That's going to be my first step. After giving my sphere a positive charge, in the second part of the experiment, I'm going to pick charge from the sphere So there we go, I have my sphere. I'm going to use a proof plane to pick charge. This sphere is positively charged. You could also make it negatively charged. So I use a proof plane. A proof plane looks like this. It's basically something like this. Has an insulating handle. So basically this part here, I can place it anywhere and it will pick charge, and I can easily transfer that charge to the gold leaf electroscope. So let me pick charge from this point. This is the proof plane. I also pick charge from this point. Oops. Okay. Pick charge from this point. I also pick charge from here. Okay. So after picking this charge, let me transfer it to the gold leaf electroscope. Oops. Okay, let me use a slightly different shape to make it more interesting. So I transfer the charge, I transfer the proof plane here. I do the same for this. I transfer this to the gold leaf electroscope after picking the charge. Oops. Okay, there it is. I also do the same for this. I transfer the proof plane to a gold leaf electroscope. So there we go. So if we do this, the observation is as follows. Observation is as follows. When the proof plane is touched at different points or at different parts of the sphere and transferred to the gold leaf electroscope, the divergence is the same in each case. So since the divergence is the same in each case, what does this tell us? This gives us an interesting conclusion. We can then conclude that charge is uniformly distributed. Charge is uniformly distributed on the sphere. And basically, if I'm to draw the charge distribution for this sphere, it would look like this. In the first diagram, I was only indicating a positive charge here, but now let me draw it more specifically. Because the proof planes have shown that the charge distribution is the same, it means the charge per unit area is the same all throughout the sphere. So there we go. The charge is uniformly distributed across the sphere. Okay, I'll show you the whole page once again. So we began with our sphere, which is either positively or negatively charged. I chose to charge it positively. Then using a proof plane, I pick charge from different points, like 3. I transfer each to the gold leaf electroscope in each case, and I observe that the gold leaf electroscope, when I transfer the proof plane, that the divergence is the same in each case. That means the charge at every point is the same. That tells me that the charge density is uniform, so I can draw this showing you the charge distribution being uniform across the sphere. Okay, let us now investigate the charge distribution for a pear-shaped conductor. Charge distribution for a pear-shaped conductor. So a pear-shaped conductor is a shape of this kind. With a sharp end at one point. So this is the pear-shaped conductor. Pear-shaped conductor. Let's assume that the pear-shaped conductor is given an initial positive charge. We assume that the pear-shaped conductor is given an initial positive charge. So I'll do the same experiment like I did at first. I'll use a proof plane to pick charge from different parts of this pear-shaped conductor. So there we go. I get pear-shaped conductor. There we have it. It is positively charged. Let me use a proof plane to pick charge from different places. So I'll pick charge from here. I'll also pick charge from here. Then I'll pick charge from here. Okay, in each case I transfer the charge to a gold leaf electroscope. Oops. Okay, try to make this better. In each case, I transfer the proof plane to the gold leaf electroscope. Okay, so there we go. Let's see the observation for this kind of conductor, the pear-shaped conductor. So to state the observation well, I'll make this point A, I'll make this point B, and this point C. So I'll use these as reference points. At point A, okay, let me make a general observation. The divergence of the gold leaf is greatest at point C, followed by point B, and least at point A. So if I carry out this experiment, it is observed that the divergence is going to be greatest when the proof plane is touched at point C of the pear-shaped conductor, followed by point B, followed by point A. This observation here shows that, if I can make some rough conclusion here, this observation shows that the charge density at the charge density at C is greater, followed by B, and then A. So let's see how this looks like if we are to draw a diagram showing the charge distribution. Okay, we draw the diagram showing the charge distribution. Okay. So, according to our observation, it means there are more charges here because the divergence of the gold leaf was too great at this point. Oops, over exaggerating it. So the charge density is too great compared to the other points. So as you can see, the spacing between the charges increases and the charge distribution is very small at the other points. So you can see this is point A, point B, point C. You can see that at point C there is greater charge density. And overall we can say that the charge density, the charge distribution is not uniform. The reason for this is because of the shape of the conductor. We have seen previously that for a spherical shaped conductor, the charge distribution would be uniform, but now for the pear-shaped conductor, the charge distribution is non-uniform because of the shape. Some places on the conductor have more charges than other places. This shows that the charge distribution is non-uniform. Let's look at the charge distribution. Charge distribution for a hollow conductor. Charge distribution on a hollow conductor. So for charge distribution on a hollow conductor, let's assume we have a hollow conductor like this. Okay, try to draw a hollow conductor. Let us give our hollow conductor a positive charge. So this positive charge could be anywhere. In fact, let me indicate the positive charge here. I'm not sure whether the positive charge is inside or outside, but it's positively charged. Positively charged hollow conductor. Ideally, I should have made this a sphere, but I need somewhere to pass the proof plane, so I cannot make it a perfect sphere. That's the best I can do. I have to leave some opening here. So there is my sphere. There is my hollow conductor. It's positively charged. So I get the proof plane like in the previous experiments. I touch the proof plane inside, and I also touch the proof plane outside. After, I transfer to a gold leaf electroscope. Okay, there we go. So the observation here is such that okay, for the proof, let me begin like this. For the proof plane, that was touched inside the hollow conductor, there was no divergence in fact there is no divergence here. So what does this tell us? If there is no divergence, it means no charge inside, the conductor. So this is a very important observation. It tells us that there is no charge inside the hollow conductor, and also this experiment will actually show us that for the proof plane, that was touched outside the conductor, there was divergence of the gold leaf. So this tells us that there was charge outside. Outside the conductor. So these two statements actually give us a very important conclusion. They give us a very important conclusion that in hollow conductors, charge only resides on the outer surface. So ideally, if I'm to draw a charge distribution for this kind of conductor, I would come up with this kind of distribution. All the positive charge is uniformly distributed on the outside, but no charge is inside the hollow conductor. So charge in hollow conductors only resides outside the hollow conductor, and it does not reside inside the conductor. We can investigate this by charging up an approximately hollow conductor. Then we touch the inside and the outside part with a proof plane and transfer it to the gold leaf electroscope, and this is the observation. For this, there is not going to be a divergence. For this, there is going to be a divergence. Remember, divergence means there is a charge on the proof plane, so that means there is a charge that was picked from outside here. That tells us that there is charge on the outside but not on the inside. So charge only resides outside a hollow conductor, not inside the conductor. So this phenomenon helps us, this very important observation shows us that, or it helps us in the process of electrostatic shielding, So let's take just a few moments to talk about electrostatic shielding. electrostatic shielding. So as you can guess, the word shield means to put a protection against something. So electrostatic shielding is the process of protecting delicate devices or instruments against effects of external electric fields. So electrostatic shielding is mainly done by enclosing the device. This could be a device or anything that is charged. So this is done by enclosing the device in a hollow conductor. We have just seen that in hollow conductors, charge does not reside, it only stays on the outside. So this is interesting because it means if I put any charge inside the hollow conductor, the charge will not be affected. For example, if I get a hollow conductor and I put a positive charge here, this is a hollow conductor, and there is an external electric field this means that the positive charge will not be affected. Positive charge will not be affected by the external electric field. So this is very important, electrostatic shielding. As a matter of fact, Michael Faraday did an interesting experiment with electrostatic shield with something he called the Faraday cage. Let me talk about the Faraday cage briefly. So the Faraday cage was a device made by Faraday to demonstrate electrostatic shielding, and basically what Faraday did, he enclosed himself in a net, in a sphere made of a net. So let's have this as our sphere, and inside here we have, okay, not good at this, we have Michael Faraday, and inside here he's having very sensitive electroscopes. Should make this better. It's having very sensitive electroscopes, and outside he charged this hollow sphere using very powerful Van der Graaff generators. We'll discuss Van der Graaff generators in a moment. And after some time, he would realize that the gold leaf electroscope could not detect any charge inside the cage. That shows that inside this cage there was no charge, yet these are sparks being seen on the outside as the cage was being charged. So Michael Faraday successfully showed that inside this cage there was no charge, while it was very evident that there is charge on the outside of this cage. So today we use Faraday cages in modern cars So modern cars are some sort of Faraday cages. Modern cars are some sort of Faraday cages, since they shield us from effects of electrostatic forces like lightning. Okay, Michael Faraday went ahead to do several experiments to show that indeed charge does not reside charge does not reside inside a hollow conductor but only on the outside. One of his famous experiments was the Faraday's icepail experiment. So we'll discuss Faraday's icepail experiment briefly. Faraday's icepail experiment. And basically, before we do the experiment, just a sneak peek here is that this experiment helps to show or to illustrate that charge only exists outside a hollow conductor, not inside the hollow conductor. So how do we do this experiment? I'll show you that next. In this experiment, we need an icepail to work as our hollow conductor. So the requirements: we need a charged ball, okay, let's have a charged small sphere. We'll also need an icepail to work as our hollow conductor, and then we'll also need a gold leaf electroscope. So let's begin the experiment. Step number 1, this is our icepail. On our icepail, we have a positively charged small sphere. So the sphere is charged positively. Okay, in the first place, shouldn't put the sphere here. So the sphere is positively charged and I'm lowering it down into the can. In the second step, let me lower the charge inside completely. It's positively charged, so as you would guess, it induces negative charges inside and positive charges on the outside of the conductor, since positive charges would induce negative charges near them and repel positive charges far away from them. So very important note here is that, okay, I think this is some sort of silk thread, maybe it's important to know. Okay, I've already named it here. So if the sphere, this here, is the positively charged sphere, if the small positively charged sphere if the small positively charged sphere is moved inside, okay, is moved to different parts. If the charged sphere is moved to different parts inside, the can or inside the pail without touching the surface should have connected this to a gold leaf electroscope. So in this case we have a can connected to a gold leaf electroscope. Sorry about that. In this case the gold leaf electroscope basically shows no divergence, but after connecting this, there is a divergence on the gold leaf electroscope because this positive charge is going to be spread all over. So the positive charge is here, here, here and here, so it causes a divergence. So if it is moved inside without touching the surface, the divergence remains constant. As you can see in this diagram, the number of positive charges on the sphere is equivalent to the number of negative charges. Okay, the diagram cannot illustrate this. I don't want to make it so clustered, but ideally the inducing charge and the induced charge must be equal. So the net charge inside here is 0. All the charge is residing on the outside. If I withdraw the ball right now without touching anywhere on the surface of this can and I test it on the gold leaf electroscope, it will still test positive. That's very important to note. It's very important to note that if the sphere is withdrawn and tested, it still has the positive charge. Okay, so that's very important. So that's our step number 1 and step number 2 in this experiment. We have our ice pail connected to a gold leaf electroscope. If we insert the the positively charged sphere without touching, negative charges are induced on the outside and on the inside, and positive charges repelled to the outside, making the gold leaf to diverge. Moving this anywhere inside here does not affect the divergence because the net charge inside is already 0. If we withdraw the ball and test it, it still has a positive charge. In that case, if we withdraw, then this one has to go down, of course, because there are no charges that will be induced in that case. Now, finally in this experiment, if we make the ball to touch the surface, as you can guess what happens, the positive charge is going to cancel out with the negative charge, but the divergence of the gold leaf is going to remain unaltered. So there we go. If the sphere is made to touch, the surface, the divergence remains unaltered. Divergence remains the same. The divergence of the gold leaf, it remains the same from step 2. It does not change. But if the ball, okay, I did not call it a ball, I called it the sphere. But if the sphere is withdrawn and tested, it is found to have no charge. It is found to have no charge. So the basic conclusion from this experiment is still the same, that charge only resides on the outside. No charge can reside inside the surface, because literally I have charged this hollow conductor by contact with the charged metallic conducting sphere. But as you notice from the experiment, all the charge moves to the outside and no charge remains inside. So you can pause the video and rewind it to be sure to understand this experiment. It's a common experiment, especially what happens throughout the experiment, and the most important part is what the experiment proves. It is an experiment that proves further that the charge only resides outside a hollow conductor and not inside the hollow conductor. Okay, thank you for watching this video. Don't forget to subscribe to this channel. That will support my work and help me to produce more videos. Also, comment if you have any questions or ideas for future videos. Next, we will look at corona discharge. In the previous section, we discussed the distribution of charge across conductors. Let us now discuss the concept of corona discharge, also known as action at points. So what is corona discharge? Well, this is the apparent loss of charge from the surface of a sharp conductor due to very high electric field intensity. Now let's see how corona discharge works. Suppose we have a pear-shaped conductor like the one we discussed in the previous section. Let us assume this conductor is given a positive charge. We know that the positive charges are going to concentrate more on the sharp end than the other part of the conductor. This is a typical distribution of charge for such a conductor. Notice that there is more charge density at the sharp point than the other points of the conductor. This conductor is surrounded by air molecules around it. So these are air molecules. Now, because of the high electric field intensity at this point, which is caused by the high charge density, the air molecules around here are going to get ionized. This is very important. The air molecules around the sharp conductor get ionized. That means they become positive and negative ions. Let's go ahead and do that. So in this case, our sharp conductor, because of the high electric field intensity at the sharp points, the air molecules will get ionized. Indicate the charges. So instead of having air molecules here, the air molecules have become ionized. We have a stream of positive and negative charges. Let's do that. Stream of positive and negative charges. And because these ions are charged, that means they have positive and negative charges on them, the negative ions will be attracted towards the sharp end, while the positive ions in this case will be repelled away. From the fundamental laws of electrostatics, negative charges are attracted by positive charges, while positive and positive repel each other. So we have negative ions attracted, while the positive ions are repelled. So let's see what happens hereafter. Because the negative ions are attracted towards the sharp end, they are going to neutralize the sharp end, and at the end of the process, the sharp end is going to be neutralized, and the stream of positive ions is going to propagate forward. So virtually, the positive charge that was originally here is now being repelled away. But in reality, this positive charge isn't the very charge that was here. The original charge has been neutralized, while in the process of neutralization, some positive ions have been repelled away. So virtually, these positive charges here represent a loss of charge that was originally here. And this process is collectively what we call coronal discharge, the apparent loss of charge from the surface of a very sharp conductor due to high electric field intensity. This is a very important phenomenon in physics because we use it for very important applications, as we will see. So one of the applications of coronal discharge is the lightning conductor. You've probably seen a structure of this kind on roofs. This is called the lightning conductor, and we use the lightning conductor to protect structures like buildings and bridges and tall trees from the damages of lightning, As you notice, on the lightning conductor we have very sharp pointed ends. This is done so that coronal discharge can easily occur, and we'll see how coronal discharge helps in the action of the lightning conductor. So take note of the sharp pointed spikes at the top of the lightning conductor. Let's take this diagram, in our case use. So we have a lightning conductor placed on top of the roof with the sharp spikes. We'll use 3 in this case. For our demonstration, let's have a negatively charged cloud passing over our house. So this is a negatively charged cloud. Because the cloud is made up of polar molecules, there is a possibility that on top of this negatively charged cloud, there are some positive charges, a few of them. Since the negative charges are the ones at the bottom, we'll consider this to be, on average, a negatively charged cloud, but that's not important. All that matters is we have a thunder cloud on top here, or a storm cloud for that matter, which is charged. As you can see, our lightning conductor has sharp spikes on top with a copper strip that extends down to the ground, and inside the ground we have a ground rod, or sometimes we use a copper plate so that electrons can be easily conducted to and from the ground. So these thunder clouds or storm clouds have a very, very high charge, and if a cloud is passing above our house, since this is a negatively charged cloud, it will induce positive charges on the thunder clouds. This is possible by the process of electric induction. Remember, the induced charge is always equal to the inducing charge, and since the inducing charge is immensely huge, Also, the induced charge is going to be very huge here. So we have an induced positive charge. But because these sharp points, because of these sharp points here, there will be a very high electric field intensity at this point. And so because of the very high electric field intensity, the air molecules in the air surrounding this lightning conductor will get ionized. So we'll have ions in the space here, negative ions and positive ions. So these are ionized, okay, ions that have been formed in the air due to the high electric field intensity at this point. As in the previous explanation of coronal discharge, the negative ions will be attracted to the sharp spikes and the positive ions will be repelled to the cloud to neutralize it. Meanwhile, these electrons that have been attracted to the sharp spikes will be conducted to the ground. So these are electrons conducted to the ground. And virtually the negative charge that was originally on the storm cloud has been conducted to the ground safely. This ground has immense amount of charge because the earth is at zero potential, so it can take up any amount of charge, or it can give us any amount of charge that we always need. So in this case, our thundercloud is safely discharged and our structure is protected from the danger of lightning. This process would be exactly the same if we had a cloud whose underside is positive, only that the charges induced here would be reversed. Let's have another application of coronal discharge, and that's going to be the electrostatic generator, commonly called by the Van de Graaff generator, named after Robert Van de Graaff, who invented it. And basically this is a type of generator used for generating very high potential differences. We haven't discussed what potential difference is, but we can talk about it. It's a generator used for generating very high potential differences, especially those used for atomic experiments. Basically, the Van de Graaff generator consists of a uniformly shaped sphere or dome, metallic and highly conducting. It has two pulleys, up and down, and it has a silk belt passing over the pulleys. So we have a silk belt going round like this. This dome is supported by insulating stands. So here we go, the insulating stands. The silk belt is rotating on the two pulleys in the clockwise direction, and it is being driven by a motor. So in this case, I'll assume there's a driving motor here, perhaps. Okay, here we go. This is a driving motor. This is a silk belt. These are pulleys, we have already discussed that. This is a sphere, conducting sphere, I'll call it the dome. Very important here are the two sharp spikes on the generator. We have one on top here and another one at the bottom. The distance between these sharp points and the belt is extremely small to enable charge exchange occur easily. The lower spikes are connected to a positive potential. Okay, there we go. So this is about positive 10 kilovolts, so that the lower electrode is kept at a positive potential, okay, while the second electrode is connected to the metallic dome. So if we start the driving motor, the belt is going to begin moving upwards. Oops, indicate the direction. The belt is going to start moving upwards and rotating like that. Because the lower electrode is connected to a positive potential, these positive charges are going to be all around this electrode, including the sharp points here. And because of the high electric field intensity at the sharp points, coronal discharge will occur, making the positive charges to be lost apparently, and the belt will pick up these charges. So the belt will become positively charged as it moves upwards. The belt becomes positively charged because of the positive charges, and these positive charges are lost from here by coronal discharge. So when the belt reaches the second electrode, negative charges will be induced at this point. Okay, use another color. Negative charges will be induced at this point, and positive charges will be induced at this point. So these positive charges will be distributed across the dome. Because it is uniform in shape, the charges will be distributed uniformly, and because of the high electric field intensity, coronal discharge will also take place at this point, and the negative charges will discharge the belt before it goes over. So this side of the belt does not have any charge because the belt is discharged at this point before it crosses over the pulley, and so this side does not have any charge. The process continues. Every time the belt reaches here, negative charges are sprayed onto it because they are lost from the electrode at the bottom here. As the belt moves up, due to coronal discharge, the positive charges are repelled to the dome, while negative charges generated due to induction will also suffer coronal discharge, being repelled to the belt, and the belt will get discharged. The process continues, and as the process continues, more charges are added to the dome. Charges are added to the dome, and the more charges are added to the dome, the more electric potential difference we generate. So practically, we always have an ion source connected to the dome. This is a source of positive ions. Source of ions. These are positive ions, and because positive and positive repel each other, these positive ions are repelled with a very high force for practical use, for example, for initiating nuclear reactions or for use in atom splitting experiments. So I have two pictures here, perhaps to give you a clear view. My diagram is only for explanation, not so suitable, but you can see we have a positive potential here. Okay, we have a positive potential. Then the electrode B1 has sharp points. Due to coronal discharge, this positive charge is lost to the belt. The belt moves up. At electrode E2, the positive charge induces negative charges. The positive charges are repelled to the dome, while the negative charges are repelled to the silk belt due to coronal discharge. And by the process, by the time the belt passes over the pulley P2, it has lost all the charge, and the process continues. In this diagram, the source of positive ions is placed at the top here, and the positive ions are repelled down to the target experiment. I'll also show you the three-dimensional look to give you a better feel of how the setup works. Still, you can see we have a silk belt, this time around in a three-dimensional form. We have our charged comb due to this positive source. We have a driving motor at the bottom here, perhaps this, and then we have the pulleys at the bottom and at the top. Then we have another electrode here which discharges the belt and also repels the positive charges to the metal sphere on top here. So this is how the Van de Graaff generator works, and this is just a few of the very important applications of corona discharge. Next, we'll look at Coulomb's law. We already know that if two positive charges are brought together, they will repel each other. When two negative charges are brought together, they will repel each other. But if a positive and a negative charge are brought together, they will attract each other. So the question is, with how much force do these charges repel or attract each other? So Coulomb's law is going to help us have a quantitative analysis of the electric force, and it will enable us to calculate the electrostatic force of repulsion or attraction between the charges. To begin with, let us consider two charges Q1, okay, two charges of magnitude Q1 and Q2 placed in a medium. So we have charges Q1. By the way, we are talking about point charges. I'll talk about why we use point charges in a later chapter. So we have 2 point charges, Q1 and Q2. Just want to make them unique. So Q1, Q2. Let's assume all these charges are positive. And from all we know is that these charges are going to repel each other with a certain force. So let this be the force on Q1 due to Q2. This be the force on Q2 due to Q1. I'll write that in a moment so that we keep using this notation. This is the force on Q1 due to Q2, while F21 is the force on Q2 due to Q1. Now by Newton's third law, the magnitude of the force F12 must be equal to the magnitude of the force 21. We'll prove that in a moment, but this is a very important concept because electrostatic force is mutual. If Q2 exerts a force on Q1, Q1 also exerts a force on Q2, so things remain constant. Now let us look at Coulomb's law. Well, Coulomb's law, like we said in the beginning, is a law, a mathematical relationship that helps us to find the magnitude of the force acting between the charges, and this law was put across by Charles Augustin de Coulomb. Okay, most importantly is the law, so let's go to that. Coulomb's law. Now, with respect to the two charges that we have just seen, Q1 and Q2, according to Coulomb, or Coulomb's law as a formal statement, the force between two charges is proportional to the magnitude, the product of the magnitude of the charges. So force or electrostatic force is proportional to the product of the charges, of the magnitude of the charges. To be more specific, this is magnitude because we will not consider the polarity of Q1 and Q2. Coulomb's law also goes ahead to say the force between the charges is inversely proportional to the square of the distance between the charges. In this case, I'll add another element. Let's assume the distance of separation between the charges, okay, is a distance r. So according to Coulomb's law, the force is inversely proportional to the distance. Force is inversely proportional to the square of the distance or of the separation between the charges. To put these two factors together, we'll have the following. So the full-scale Coulomb's law is that the force, electrostatic force between two charges, is directly proportional to the magnitude of the charges and inversely proportional to the square of the distance between the charges. This is Coulomb's law. To make it mathematically viable, we have to get rid of the proportionality constant. So for that matter, we'll have the force being equal to, now because we get rid of the proportionality sign, we must introduce a constant. Let me call that K. Then Q1, Q2 divided by R squared, where K is a constant. And this constant depends, so K is a constant which depends on the nature of the medium where the charges are placed. Remember our original assumption, we said consider two charges, Q1 and Q2. Okay, we had to consider two charges, Q1 and Q2, placed in any medium. So the electrostatic force depends on the magnitude, the product of the magnitude of the charges, and it also obeys the inverse square law, but also the constant of proportionality between the force and the charges is dependent on the material in which the medium in which the charges are placed. And through experiments, it is found that K is actually equal to 1 over 4 pi epsilon, where epsilon, this is a Greek letter called epsilon. It's a Greek letter called epsilon. So where this, in this case, stands for the permittivity. We'll talk about this later. The permittivity of the medium. Epsilon is the permittivity of the medium, and it is measured in farads per meter or coulomb squared per newton per square meter, like that. The choice is yours, but both units can work. We'll explore more about the permittivity of the medium later. So the force F from the formula F equals K Q1 Q2 over R squared, where K is 1 over 4 pi epsilon. F is in newtons when Q1 and Q2 are in coulombs and are in meters. So this is very important. Every time we use Coulomb's law for numerical problems, we have to make sure Q1 and Q2 are measured in coulombs or converted to coulombs, and we also have to make sure that R is measured in meters. So just a simple laboratory activity to prove Coulomb's law. Lab activity. Oops. If we have a well-insulated surface and we have a force sensor on both sides, and we have metallic spheres connected. Okay, I think I have to make another color here. So this is a force sensor. These two. This A and B are metallic spheres. So if A and B are charged oppositely, that means if A is given perhaps a positive charge and B is given a negative charge, there will be a force of attraction between the two spheres A and B, and the force sensors are calibrated to give us the magnitude of force between A and B. In this activity, if we add more charges to A and B by any method of electrification, perhaps by contact, if we add more charges to A and B, you realize that the force between A and B increases as we charge up A and B more. Also, we can try to investigate what happens to the distance between the two spheres, which is R. If we increase R, then the force reduces rapidly. So this shows us that indeed the force is proportional to the product of the magnitude of the charges, and it is inversely proportional to the square of the distance between the charges, which is a good proof for Coulomb's law. Also, if we are to plot graphs to demonstrate Coulomb's law, you realize that, if we have the electrostatic force, then we have Q1 and Q2, you realize that the force increases as you increase the magnitude of Q1 and Q2, then the force reduces very rapidly. The force reduces very rapidly if we try to change the distance between the charges. So force is proportional to the magnitude of the charges, but it is inversely proportional to the distance between the charges, or the square of the distance between the charges, to be more specific. So until now we have discussed Coulomb's law and how to calculate the force between two charges. Now let us see the different use cases of Coulomb's law, especially the most common ones. So if the charges are placed in air, if the charges are placed in air, then epsilon will be equal to epsilon naught, where epsilon naught is called the permittivity of free space, and epsilon naught is 8.85 exponent negative 12 farad per meter. This is very important. So the force between the charges in this case is 1/4. Okay, to write it the basic way, K Q1 Q2 over R squared, which is equal to 1/4 pi epsilon naught R squared Q1 Q2. So this is commonly used because in most cases we'll have our charges placed in air. And because of this common usage, if F equals 1/4 pi epsilon naught times Q1 Q2 over R squared, if you substitute epsilon naught equals 8.85 exponent negative 12 in 1/4 pi epsilon naught, you'll have K equals 1/4 pi epsilon naught, which is going to be, you can plug in this value into the formula here, you'll get about 9 times 10 to the 9th power. Of course, the units change per farad meter. So for charges placed in air, we precisely use this common form of Coulomb's law, and we say that the force is simply 9 exponent 9 times Q1 Q2 over R squared for two charges placed in air. Let us proceed and write Coulomb's law in vector form. In our previous study, we have only looked at the magnitude of force without taking into consideration the direction of the force. We will now write Coulomb's law in vector form. So there we go. Coulomb's law in vector form. Let us consider the two charges that we had at the beginning, Q1 and Q2, all of them positive in this case. We have the force, the force on Q1 due to Q2, it's a vector quantity, so I indicate this. Also, we have the force on Q2 due to Q1. It's a vector quantity, so I indicate that. Also, in this case, I indicate the directional vector, the directional unit vector. In this case, we have R1, 2, R cap 1, 2. Also, R cap 2, 1. These are the unit directional vectors of the direction force. The distance between the two charges is R, so I indicate that here 2, where R1, 2 cap, this is the unit vector from Q1 to Q2. R cap 2, 1 is the unit vector from Q2 to Q1. Okay, nice. Let us now rewrite Coulomb's law in vector form, having all this in mind. So Coulomb's law will be written as follows. The force on charge 2 due to charge 1 is going to be given by K Q1 Q2 divided by r squared, and here we'll have r cap 1 to 2 because we have to consider the direction of the force. Oops, this is a vector quantity, so I indicate that. Also, the force on 1 due to 2 is going to be k q1 q2 divided by r squared r21. Oops, this is a mistake. Okay, we've got to have 1 2 here, not 2 1. Then here we have 1 2. Okay, that's better. So there we go. We also know from the study of vectors that r21 is the same as r21 divided by the magnitude of r21, where r21 is r2 minus r1. Consequently, r12 is r12 divided by the magnitude of r12, where r12 is equal to r1 minus r2. From these two expressions, it is evident that r12 or r21 is equal to negative r12. That means r cap 21 is also equal to negative r12 cap. Let us substitute these two expressions. So let us substitute these two expressions into the formulae for electrostatic force that we have just stated, this and this. Okay, so there we go. I rewrite them again. F12 is equal to k q1 q2 over r squared r12 cap. This is going to be written as, okay, this is k q1 q2 over r squared into negative r21, if you like. That means F12 is the same as negative F21. So this shows that electrostatic force obeys Newton's third law, because the forces are equal and opposite. Okay, very important. Next, let us explore the concept of absolute permittivity and relative permittivity. Absolute permittivity and relative permittivity. So literally every time we have talked of permittivity, what we actually meant was the term absolute permittivity. The permittivity of a medium is what we call the absolute permittivity. Intuitively, permittivity is the ability of a medium to permit or to allow electric forces through it. The ability of the medium to allow electric forces through it. Air or vacuum is best known to do this because it has one of the highest permittivities that we can always know. So from the formula F equals 1 over 4 pi epsilon naught, 4 pi epsilon times Q1 Q2 over R squared. Let's try to make epsilon, the permittivity, the subject of the formula. What will that become? Okay, this case, let's see, we'll have F R squared 4 pi divided by Q1 Q2. This is going to be 1 over epsilon, so epsilon is going to be Q1 Q2 over F R squared 4 pi. So the units will be Coulomb squared divided by newtons and meters squared. So this is where we get the units. Okay, there we go. The units of permittivity being Coulomb squared per newton per square meter. Sometimes we use Farad per meter. Okay, I will not derive this unit for now because it involves a study of capacitors, but we'll commonly use it as opposed to the previous unit, Farad per meter. That's also another unit for permittivity. So the permittivity of a medium is also called the absolute permittivity, and it is the measure of how much electric force that material can permit to pass through it. Let us now talk about relative permittivity. Since it is generally difficult to measure the absolute permittivity of a material without any reference, relative permittivity becomes a very important and common measurement when it comes to the permittivities of all media. So relative permittivity is the ratio of the absolute permittivity of the medium divided by the reference medium, which is the free space or the vacuum. So this is divided by the permittivity of free space or the permittivity of vacuum or air. Let us use epsilon r for relative permittivity. The absolute permittivity is epsilon and the permittivity of free space is epsilon naught. This is very important, and sometimes epsilon r is also called the dielectric constant, because, as we have already discussed, the permittivity depends on the nature of the medium, which medium is quite often a dielectric, some sort of insulator, and so it is logical to call this term the dielectric constant. Sometimes we use K, sometimes we use epsilon r. I will use epsilon r throughout the course. Let's look at the relationship between electrostatic force and the relative permittivity. So we have already discussed that for charges placed in air, if we have two charges placed in air, then the force between those charges will be 1 over 4 pi epsilon naught Q1 Q2 over R squared. If the charges are transferred to a medium of relative permittivity epsilon r, remember epsilon r is equal to epsilon, the permittivity of the material, over the permittivity of free space. So the permittivity of the material is epsilon naught epsilon r. This is very important. So the electrostatic force, pardon me, the electrostatic force in this case in a medium of relative permittivity ER is going to be 1 over 4 pi epsilon Q1 Q2 over R squared. Notice this is epsilon naught, they are different. This is the same as 1 over 4 pi epsilon naught epsilon R Q1 Q2 over R squared. So if I call this equation 1 and this equation 2, if we take ratios, in this case we'll take the ratio of F. This is the force, the electrostatic force in a medium, so let me call it Fm. The electrostatic force is in a medium, which is different from F, the electrostatic force in air. So I'm going to take the ratio F to Fm, and if I do that, I get the following result: F divided by Fm equals the relative permittivity. You can try that out more detailedly. So the force in a medium is given by 1 over epsilon r times the force in air. This is a very important relationship because it tells us that if the charges are transferred from air to any medium, when the charges are transferred from air or free space to a material of relative permittivity, epsilon r, the electrostatic force reduces by a factor epsilon r. As you can see, the electrostatic force in a medium is 1 over epsilon r times the electrostatic force in air. If we take an example of water, let's take this. Water and salt. By salt we mean sodium chloride crystals. Sodium chloride is an ionic compound where sodium ions are positively charged and chloride ions are negatively charged, and these two charges are being bound together by electrostatic forces. So air has a relative permittivity of about 81. So if a sodium chloride crystal is transferred to water, just like this, if the sodium chloride crystal is transferred to water, the electrostatic force between the sodium and chloride ions is going to be approximately 81 times. So this is the force in water. It's going to be about 81 times less than what the force was in air, and so sodium chloride will easily dissolve and dissociate because the force has reduced by a factor of 81, 1 over 81 of the force that it was between the crystals, between the atoms, the ions, when the crystal was in air. So this explains why sodium chloride and probably many other ionic compounds will dissolve in water, because the electrostatic force between them reduces. So this explains why most ionic compounds dissolve in water. It is because the electrostatic force between the ions reduces. Okay, so suppose we have a system of charges placed in a certain medium. In this case we'll consider air, and all these charges are exerting forces on each other. How do we calculate the resultant force? So next we'll look at the superposition principle, or the principle of superposition, to help us calculate the resultant force for a system of charges placed in the vicinity such that they can all exert forces on each other. So let us consider a charge Q0 placed in the vicinity or in the space of other charges. Let's have Q1, Q2, and many other charges up to Qn. So there we go. I'll illustrate this with a diagram. We have a charge Q0. Let's assume it's positive. We have Q1 here, Q2 here, Q3 here, and many other charges up to Qn. These charges, let me give them some polarity. Let this be negative, let this be positive, positive, and maybe negative here. The electrostatic force between Q0 and Q1 is going to be a repulsive one. So the force on Q0 due to Q1 is going to be force of repulsion. There we go. Between Q2 and Q0, the force is going to be repulsive too. So this is the force on Q0 due to Q2. Okay, I should have write F, the force on Q0 due to Q2. In this case, the force is going to be attractive, like this. So this is the force on Q0 due to Q3. And finally, the force between Qn and Q0 is going to be attractive. So the force on Q0 due to Qn. Our goal is to find the resultant force that is acting on Q0 after different forces in the system have acted on it. So let's go ahead and do that. Our goal is to find the resultant force. Let me call this resultant force F0, the force on Q0. So according to the superposition principle, the resultant force acting on the charge Q0 is going to be equal to the sum of all the forces acting on the charge Q0 in vector form. So the resultant force F0 is going to be equal to F01 plus the force acting on Q0 due to Q2 plus the force acting on Q0 due to Q3 plus many other forces plus the force acting on Q0 due to Qn. And this is what we call the superposition principle or the superposition theorem in as far as electrostatic force is concerned. Notice that in this case I'm using the vector form of force, so I don't have to worry about the direction. Everything will be taken care of. In the next section, we'll look at several numerical examples in 1 dimension and 2 dimension of how to apply the superposition theorem to find the resultant force on a charge due to a system of many charges. Hello, welcome back. In this video we are going to do some numerical problems on Coulomb's law. So let's get started with our first question. Find the force between 2-point charges. This is very important. Coulomb's law only works if we have point charges. So we have find the force between 2-point charges of positive 4 microcoulombs. This is microcoulombs, and negative 3 microcoulombs placed 10 centimeters apart in air. Okay, so this is the most important information in the question. Let me draw a sketch of what this looks like. We have a positive charge of 4 microcoulombs. There we go. We also have another charge of, this is negative 3 microcoulombs. Now, from all we know about the fundamental laws of charge, these two charges will attract each other with a certain force that we want to calculate. These charges are placed 10 centimeters apart. So I represent that 10 centimeters. There we go. And then there is a force of attraction. Also, the charges are placed in air, so we know the permittivity that we are going to use. It's the permittivity of free space. So from Coulomb's law, we know that the force between two charges is given by 1 over 4 pi epsilon naught times Q1 Q2 divided by R squared. I'm using epsilon naught because the charges are placed in air. Otherwise, I would have to use some other figure. But for this special case, when the charges are placed in air, we know that the whole of this is approximately 9 times 10 to the power negative 9. So I'll instead use this instead of using the whole of this. Only use this figure when you have the permittivity of free space. So if you have a different permittivity, you may want to directly substitute into the formula. So let's go ahead and do that. So our force is going to be 9 exponent, this is positive 9, not negative 9, sorry about that. So that's 9 exponent 9, okay, times Q1, or the first charge. In this case we have 4 microcoulombs. So 1 microcoulomb is actually 10 to the negative 6 coulombs. So I have to convert this to coulombs. That's 4 times 10 to the power negative 6 times Q2, the second charge, which is 3. Also, it's in microcoulombs. I've got to change that to coulombs times 10 to the power negative 6. I do not indicate the negative sign because I'm basically finding the magnitude of charge. So that is reasonable. I only want to know the magnitude. I'll tell the direction later. So the distance between the charges, it's 10 centimeters. So I have to change that to meters. 10 times 10 to the power negative 2. That changes it to meters. Then I square it according to the formula. This has to be squared. Okay, there we go. So if you plug this into the calculator and try that out, you'll get 10.8 newtons. And in this case, the force is going to be attractive because we can see that the forces are of different polarity. Okay, so this has been a simple one-dimensional problem. Let's move on to more interesting problems. Later on, we'll also look at two-dimensional problems to do with Coulomb's law. In our second example, we have 3-point charges. Another emphasis on point charges. 3-point charges A, B, and C are placed as shown below. So here we have our illustration. We have 3 charges A, B, C, negative 3 microcoulombs, 4 microcoulombs, negative 7. In this question, the medium is not specified, so we'll assume they are placed in air. We want to find the resultant force on the charge at B. We want to find the resultant force here. So we will assume that all the other charges are at rest while the charge at B is free to move in relation to the forces that will be acting on it. So let us resketch this and see how it looks like. This is the charge at point B, I'll only look at the forces. The charge at B is experiencing a force from the charge at A and a force from the charge at C. Let's see the nature of these forces. The charge at B is positive while the charge at A is negative. So there will be a net force of attraction. So this charge is going to be attracted to this side because there is a there is an attractive force between B and A. So I indicate that it's an attractive force. The force on B due to A, you can allow me use that. Also, the force on B due to C, as you can see, this is positive, this is negative. So there we go. There is another force of attraction from C, which is also on that direction. So there we go. The force on B due to C. So I can indicate that FBA represents the force on A, the force on B due to A. FBC represents the force on B due to A. Very important here, take note that the charge at B does not move. Only the charge at B is free to move. The charges A and C cannot move. They all, in this question, we consider them to be static. They are only exerting a force on the charge at B. So only the charge at B is free to move. That's why we indicate the forces at the charge at B. So let's calculate the force on B due to A. Of course, that's going to be equal to 1 over 4 pi epsilon naught, the charge at A times the charge at B divided by r squared. Let's do the math here. We already know what the whole of this is. It's 9 exponent 9. We know the charge at A, that's 3 exponent negative 6. That's to convert it to coulombs. We know the charge at B, that's 4 exponent negative 6. We know the distance between A and B, it's 10 centimeters. We've got to change that to meters, and then I square it. So if you do this, if you plug in these values into the calculator, let's see what you get. That's 10.8 newtons. Let's also do it for the force on B due to C. That's going to be 1 over 4 pi epsilon naught QC QB divided by r squared. This is the charge at C, the charge at B. There we go. We have this 9 exponent 9. The charge at C is 7 microcoulombs, negative 7, but we're only concerned with the magnitude. Also, the charge at B, 4 exponent negative 6. The distance between the two charges, here we go, it's 5 centimeters. So I change that to meters, then I square the result. This force, if you plug these values into the calculator, let's see what you get. In this case, you get 100.8 newtons. Okay, I'll draw a force diagram to show you what this looks like at this point. So there we go. We have our charge at B with two forces acting on it. We have a force of 100.8 newtons and another force of 10.8 newtons. So the resultant force obviously is going to be in the direction of the stronger force. So we'll have 100.8 minus 10.8. What's that going to be? Okay, if you do the math, that's going to be 90 newtons. Got to indicate this, the units, newtons. So the force, the resultant force is going to be 90 newtons. Which direction is that? If we draw a little compass here, this is the north. I think this is going to be the east direction. So this is going to be 90 newtons eastwards. Okay, there we go. So in this case, we've given a complete description of the force, and the force including its magnitude and its direction. This is always a good practice when we are describing a force, because it is a vector quantity. Let's have another question, question number 3. So in question number 3, in the figure below, find the resultant force on the -3 microcoulomb charge. Okay, there we go. We have our diagram indicating the charges. We have a charge of -3 microcoulombs. It's placed at point B. We want to find the resultant force on it. So let me draw the force diagram. Remember, in this case, the charge at B is free to move, while the charges at A and the charges at C are static. So they are all exerting their influence on the charge at point B. So we want to find the resultant force at B. So there we go. Between charge A and charge B, as you can see, this is a positive charge while this is a negative charge. So the charge at B is going to be attracted. So there we go. Oops. I think I better get another color. Okay. So there we go. We'll have a force of attraction, this direction. This is the force on the charge at B due to the charge at A. I think that's better. Okay. Also, you can see that between the charge at C, -4 microcoulombs, and the charge at B, there is going to be a force of repulsion, because this charge and this charge have the same polarity, so they repel each other. So the force of repulsion, let me indicate that with the red color, it's also going to be in this same direction. Okay, so if you can allow me do that here also. So there we go, the force on B due to the charge at C. Okay, this is a good force diagram. We can see all the forces are acting in that direction. The attractive force and the repulsive force, all of them happen to be in the same direction. Let's calculate the force on B due to A. That's going to be 1/4 pi epsilon naught, the charge at A times the charge at B divided by r squared. There we go. We know this is 9 exponent 9. The charge at A is, okay, that's positive 2 microcoulombs. That's 2 times 10 to the power -6 to change it to coulombs, times the charge at B, 3 times 10 to the power -6, divided by, the distance is 2 centimeters. I change that to meters, then I square the result. If you plug these values into the calculator, the force on B due to A is going to be, okay, you can do that and see what you get. In this case, okay, let me do this. That's 135 newtons. Also, let's find the force on B due to C. That's going to be 1/4 pi epsilon naught QB QC of r squared. Oops, r is not good, r squared. Okay, we have 9 exponent 9 multiplied by the charge at B, 3 exponent -6, the charge at C, 4 exponent -6, divided by the distance. The distance is 4 centimeters. I change that to meters, then I square it. If you put these values into the calculator, you have 67.5 newtons. So as you can see on our force diagram, all the forces are acting in the same direction. We have two forces of, okay, let me see, we have 135 newtons and another force of 67.5 0.5 newtons, all of them acting in the same direction. So the resultant force, or the total force, or I think it's better I call it the net force, all can mean the same. Since the forces are in the same direction, it's going to be this force plus this force, 135 plus 67.5 newtons. Okay, let's see what we get there. That's 202.5 newtons. This is going to be in the westward direction, or you can describe this direction in terms of angles, but this is better since we have a clear definition of what the direction is. It's towards the west. So there we go. We have given a complete description of the force, its magnitude, and its direction. Okay, let's have another problem. Number 4. Calculate the resultant force on a charge of 1 microcoulombs placed at point P. Sorry about that. So we have point P. Here we go. Here it's point P. So, and at point P we have a charge, because that's positive. So we have a charge of positive 1 microcoulombs placed here, and we want to find the resultant force. Okay, let's indicate the forces acting at point P on the charge of plus 1 microcoulombs placed here. The first force is due to the 3 microcoulomb charge. Okay, should we begin with that? Okay, that's fine. So 3 microcoulomb, this is negative and this is positive. There's going to be a force of attraction. So there's going to be the force of attraction, the force at P due to the 3 microcoulomb charge. Let me just write that as FP3. Also, we have negative 2 microcoulombs here, and this is positive 1. So positive and negative, there's going to be another force of attraction. This is the force on P due to the 3 microcoulomb. This is going to be the force on P due to the 2 microcoulomb charge. Let me add that there, the force on P due to the 2 microcoulomb charge. All the forces in this direction. So we are good to go. Let's apply Coulomb's law. The force on P due to the 2 microcoulomb charge. Let's begin with that. It's no problem. That's going to be 1 over 4 pi epsilon naught. The material is not indicated here, the medium, so we'll take that to be air or free space since it is a common medium. Q, okay, here we have the charge at P times the, how shall I call that? Perhaps the 2 microcoulomb charge, okay, Q2, there we go, divided by R squared. That's going to be 9 exponent 9. The charge at P is 1 microcoulomb. Then Q2 is the 2 microcoulomb charge. Okay. The distance between the 2 microcoulomb charge and P is 0.6 meters. That's already in meters, so I'll just square that. And then if you put these values into the calculator, let's see what you get. The force on P due to the 2 microcoulomb charge, that's going to be, let's put this in the calculator, approximately 0.05 newtons. Okay, let's calculate the force on P due to the 3 microcoulomb charge. 1 over 4 pi epsilon naught QP Q1 over R squared. That's 9 exponent 9. QP, that's 1 microcoulomb. Okay, that's 1 times 10 to the negative 6. That's enough. Q1 is the charge at oh, what was that? Oops, that's Q3. I think that's better. The 3 microcoulomb charge, so that's 3 times 10 to the negative 6 divided by the distance, square of the distance between the two charges. As you can see, the distance from here all the way, up to point P is actually 0.4 plus 0.6, so it's 1 meter. So that's the distance I'm going to use here. That's 1 squared. If you put that into the calculator, let's see what you get. 0.027 newtons. So the net force in this case, okay, let's see, all the forces are acting in the same direction, so we'll have 0.027 plus, okay, we have this and this all acting in the same direction, so the net force is going to be that plus 0.05. That's going to be, okay, let's add this quickly and see what we get. Okay, 0.0, let's see, if you add 0.05, this is going to be 7, okay, 0.077, okay, yes, that's it, okay, that's perfect. So there we go, 0.07 newtons, that's the net force, and you can see the direction in which this force is actually acting. Okay, let's proceed to the next example, number 5. So in example 5, we have a rather interesting problem. We have a two-dimensional problem. The charges are assembled in sort of a triangular configuration, and we have to find the resultant force on the charge placed at C. So we have to find the resultant force on the 3 microcoulomb charge, as you can see, placed at point C. So there we go. Let's indicate the forces acting on it. Let's indicate the forces acting on it. I'll try to sketch this. So this is the 3 microcoulomb charge placed at point C. Let's indicate the forces acting on it. What should we begin with? Let's begin with the force due to B. So you can see the charge at B is a positive charge. Also, this is a positive 3 microcoulomb charge. So the force between B and C is going to be a repulsive force. Also, remember, all the forces A, B, and D are at rest. They are fixed in this configuration. Only the charge at C is able to move, so it is experiencing all these forces. So we indicate the forces at the charge at C. So there we go. The force between B and C is a repulsive force acting in the upward direction at vertical direction 90 degrees. So that is the force. Okay, make that better. The force at C due to B. Okay, let's also compare this, C and D. This is positive, this is also positive. So positive and positive repel each other. So the force of repulsion will act in that direction. There we go. This is the force on C due to D. Okay, anything left? Yes. Let's also look at the charge at A. So between A and C, this is negative 4 microcoulombs. This is positive 3. Positive and negative attract each other. So there's going to be a force of attraction. The 3 microcoulomb charge is going to be attracted down towards the negative 4 microcoulomb charge. So have this, the force on C due to A. It's an attractive force. Okay, so we have to find the resultant force after all these forces have acted on the force on the charge at point C. Now, because we are going to be doing this, it's important to find the angles, especially when we are resolving the forces here. So let me complete this diagram. Okay, there we go. So to help in resolving this better, we've got to find these angles. I guess either this angle or this angle would be sufficient for us to do the math. So let's begin Also, another thing we will need is to find this distance from here to here, because we need to know the distance between A and C for us to calculate this force. Let's begin with that. That will also help us to find the direction. So there we go. We have 4 centimeters here and 4 centimeters here. We do not know this distance. Let me call it AC. It's the distance from A to C. So using Pythagoras theorem, so if you use Pythagoras theorem for right-angled triangles, we know that 4 squared plus 4 squared has to be equal to AC squared. So AC is going to be, if you do the math here, you'll have square root of 16 plus 16, square root of 32. So you'll have approximately 5.66 centimeters. That's the distance from A to C. Also, it's important to find the angle at this point. Let's call that angle theta. So you can see that tan theta, in this case, it's going to be 4 over 4. Tan theta is going to be 4 over 4, which is 1. So I guess you know what that means. That means theta is going to be 45 degrees. That's important. So the angle here is 45 degrees. That's going to be important when we are resolving the force. Okay, I also indicate the 45 degrees here for simplicity. Let's proceed now to find the forces one by one. Okay, get another color. So let's begin with the force. The force at C due to B. That's going to be, okay, also this configuration will assume the medium is air, because the medium is not stated. So we'll have K, then we'll have the charge at C and the charge at B over R squared. In this case, K means 9 exponent 9, the constant. So we have 9 exponent 9 times the charge at C is 3 microcoulombs. Okay, there we go. The charge at B is, as you can see, 8 microcoulombs, 8 exponent negative 6. The distance between 8 and 3 microcoulomb charges is 4 centimeters. So that's centimeters. I've got to change that to meters. Then I square the result. So if you do that, okay, plug these values into the calculator, you'll get 135 newtons. Let's proceed. The force, okay, get another color for this. Let's find the force on C due to the charge at A. Force on C due to the charge at A, that's K QC QA over R squared. That's going to be 9 exponent 9. The charge at C, what's that? 3 microcoulomb charge. The charge at A, that's 5 microcoulomb. There we go. 5 exponent negative 6. The distance between 5 and 3 microcoulomb charge is actually 4 centimeters. This is a square, so 4 times 10 to the negative 2 squared. That's going to be, if you put these values into the calculator, 33.75 newtons. Lastly, we have the force on C due to the charge at A. Oops, did I just say A? Okay, I just said A, and then I ended up actually using D, so this should have actually been D. Okay, sorry about that. So that's actually D. Okay, because I used the charge for D, and I sort of don't want to repeat this yet. I'm going to do it again here. So let's do the one for A here. Okay, that's better. So that's K QC QA. Also, moment, I think this is going to be a different value. this is going to be force at C due to D, that's going to be about 84. That's 84.375 newtons. Okay, so there we go. Let's calculate the one of A. That's going to be K QA QC over R squared 9 exponent 9. The charge at A, that's 4 microcoulombs. The charge at C, that's 3 microcoulombs. The distance between the charge at A and the charge at C is actually 5.66. We calculated that already. 5.66. We've got to change that to meters, then square the result. Okay, let's see what we get. Yeah, that's going to be 33.75 newtons. Okay, so now we have all the forces. We have this force, we have this force, we have this force. Next we have to do is to resolve the forces to find the resultant force. So I'm going to pull this aside. And redraw the force diagram. So oops, there we go, our force diagram. We had the force here, we had the force here, we also had another force. Was it this direction? I guess that was the direction. Okay, so let's begin. This charge, the force at C due to A, I think this was the one. That's 33.75, 84.375, and then this is, okay, what's that? That's 135 newtons. Also the angles here were 45 degrees. That's very important. Okay, so let us now find the resultant force. In this case we have forces in two dimensions, the vertical dimension and the horizontal dimension. We'll call the vertical dimension the y-axis and the horizontal the x-axis. So let's find the summation of all forces. What should we begin with? Let's find the summation of all forces in the y-axis. That's going to be in the vertical plane. So we have a force of 35 newtons, 135 newtons. That's upwards. By convention we call that positive, so it's a positive force. Then we have a force that's heading downwards, a component of 33.75 newtons in the downward direction. That's going to be minus 33.75 cos 45. As you can see, this force has two components. We have 33.75 cos 45. Also here we have 33.75 sin 45. So this force here has two components, the horizontal component and the vertical component. So there we go. So the summation of forces in the vertical direction will be 111.17 newtons. Let's go to the summation of forces in the y-axis or in the x-axis. That's going to be, we have 84.375. Okay, by convention, forces to the east or to the right are called positive, and then forces to the left are negative. So there we go. So this is negative 3.75 sin 45. If you put this on the calculator, you have about 60.57 newtons. Okay, let me create more space. Let me redraw the force diagram again to show you what we have. So if I summarize all this information into one diagram, we have in the vertical direction we have a result. Oops, just make this better. In the vertical direction, we have a resultant force of 111.17 newtons. In the horizontal direction, we have a resultant force of 60.57 newtons. Let's assume our resultant force will act in this direction. So I call F the net force, or the resultant force. Could complete this, then I have the 111.17 newtons. Also, let alpha be the direction of this net force. So let's begin by finding the net force. It's going to be the square root of 60.57 squared. I'm using Pythagoras theorem, plus 111.17 squared. If you put these values into the calculator, I'll have about 126.59 newtons. We can also find the angle at which this force is acting. That's going to be tan arctan of, let's see, the vertical, 111.17 divided by 60.57. Okay, this is going to be okay, let's do this, 61.42 degrees. So our final answer here is that the net force is 126.59 newtons at an angle of 61.42 degrees. Okay, that angle is with respect to the horizontal, so at an angle of that to the horizontal or to the x-axis. Okay, so that's a good example of a two-dimensional problem. Let's have more problems of the same type to get a better idea. Number 6, find the resultant force on the charge at C. So there we go, we have a rectangular configuration. The charge at C is 3 microcoulomb charge, negative. The charge at A is negative and the charge at B is positive. Let's see the resultant force, how it looks like. So this is the charge at C. As you can see, between A and C, there will be a net force of repulsion. This is negative, this is also negative. So it's going to be a repulsive force on the negative 3 microcoulomb charge. That's the force at C due to A. Let's look at B. As you can see, this is negative, this is positive. So there's going to be an attractive force. That's the force at C due to B. Okay, so we only have two forces in this case. I'll write this somewhere else. Let me put that here. So we have two forces acting on our charge at C, and we want to find the resultant of these two forces. Just to make our work easier for resolving, I'll have to indicate the x-axis and the y-axis. Oops. Okay, just got to make this a little better. Okay, so this is the y-axis, this is the x-axis. That will help us to resolve the forces easily. So this is an isosceles triangle. As you can see, this is 20, also this is 20 centimeters. So let's see, we want to find the angle at this point. Also, we want to find the angle at this point. From this triangle, let's see how we'll do that. That's our triangle. So it's easier to work with right-angled triangles. So let's do that. Instead of the 10 centimeters, I'll have 5 centimeters and 5 centimeters. Then we'll have 20 centimeters here. Okay, 20 centimeters. So let me find the angle at this point. Let me call that angle theta. Okay, that's a better one, theta. So how do we find theta? We have the hypotenuse and the adjacent. I think cos theta would be a good choice. In that case, cos theta is going to be 5 over 20. So theta will be cos cos inverse of 5 over 20, that's about 75.5 degrees. Okay, so that's the angle here. As you can see, these are vertically opposite angles. Okay, let me just show you this here. So this line, the x-axis, is actually parallel to this line, so the angle here is also the angle here. So that's why we have this angle appearing here, 75.5 degrees. This looks like 8.5 degrees. Okay, let's take off this. Okay, not bad. Okay, we also need to find the angle at this point here because we will need it. So let's call that angle alpha. Okay, let's go ahead and find what that angle is. In that case, we'll have okay, what do we need? That's going to be alpha. We have the hypotenuse and we also have the opposite. So in this case, sine of alpha is going to be equal to 5 over 20. So alpha is going to be sine arc of 5 over 20. So let's see what we get in that case. Just pull out my calculator here. Oops. About 14.5 degrees. By the way, this angle here is also 75.5 degrees. I think we could have avoided all this by just using this angle here. I think that would be much better. Okay, so let's go ahead and find what these forces are. Let's begin with the force at C due to A. That's going to be 9 times 10 to the 9 times the charge at C is 3 times 10 to the 6th. The charge at A is 5. The distance between A and C is 20 centimeters, so I change that to meters, then square the result. If you put these values into the calculator, you'll get 3.375 newtons. Let's find the force at C due to B. That's 9 exponent 9 times 3 times 10 to the negative 6, then 4 times 10 to the negative 6th. The distance between the two charges is also 20. Change that to meters, square the result. Okay, our force is going to be 2.7 newtons. So there we go. We can find the resultant force or the net force in the directions. Let's do that. So the summation of forces on the y-axis, we have the component of CA across the y-axis. That's going to be 75.5. That's going to be sine of the angle. that's not 75, that's the angle. So that's going to be 3.375 sine 75.5 minus, because this is actually in the negative direction, okay, that's 2.7 sine 75.5. Let's see what that is. So the summation of forces in the y-axis is going to be 0.653 0.653 newtons. The summation of forces in the x direction is going to be 3.375 cos 75.5 plus, because all forces are on the positive side of the x-axis, so that's plus 2.7 sine 75, not sine, cos 75.5, because it's actually lying here. So the summation of forces in the x direction will be 0.65, what's that, the horizontal direction, okay, sorry about that, that's 1.521 newtons. So let's see what we have. In this case we have two forces, the force in the y direction, that's 0.653, forces in the x direction, we have 1.521 newtons in each case. The resultant, or the net force, is that. So F is going to be the square root of 1.521 squared plus 0.653 squared, and that's going to be okay, if you do that, we'll have 1.8655 newtons. Also, let the direction be called beta, so tan of beta will be, okay, 0.653 divided by 1.521. If you do the math here, I'll get beta as 22.23 degrees. So the net force can finally give our complete result, that the net force is 1.655 newtons at 22.23 degrees to the horizontal. Okay, so that's a good description of the force. Let's have another problem, number 7. Again, we have a rectangular configuration. So we have point charges Q1, Q2, Q3, and Q4 placed at corners of a rectangle, as shown below. We want to find the resultant force on the charge Q3. So there we go, our charge Q3 is here. Let's try to draw the forces. Okay, make that better. So the force on Q3 due to Q1, this is 2000 nanocoulombs, this is negative 3000, that's going to be a force of attraction. So there we go, the force on Q3 due to Q1. Also, we have a force here, 5000 positive, this is negative, so we'll have a force of attraction. This force is going to be attracted that side. There we go. The force on Q3 due to Q3, oops, is that true? think this has got to be Q2, if I'm not mistaken. Yeah, this has got to be Q2. Okay, this is force on Q3 due to Q2. Then here we have Q4. I just wrote this in advance. So Q4 and Q3, this is positive, this is negative. That's going to be also force of attraction, the force on Q3 due to Q1. So that's our force diagram. Let's calculate these forces. But before we do that, we've got to find this distance here. So let's do that. We have 4, then we have 3 centimeters. By Pythagoras theorem, if I call this distance, okay, if I call that distance C, C is going to be the square root of 3 squared plus 4 squared. That's going to be 5 centimeters. There we go. Then we also need to find this angle here, the angle with the horizontal. Let's do that. If I call that angle theta, we know that tan theta is going to be 3/4. In that case, theta is going to be 53.13 degrees. Okay, that's good. Let us now calculate the forces one by one. Let's begin with the force 3(1). That's going to be 9 exponent 9, the force between this and this, times, now the force, let's begin with this, 3000 nanocoulombs. 3000, 1 nanocoulomb is actually 10 to the negative 9 coulombs, so that's going to be 10 to the negative 9 times 2000 nanocoulombs. That's going to be 2000 times 10 to the negative 9 divided by the distance, 3 centimeters. Convert that to meters, then square the result. If you do that, the answer here will be 36 newtons. Okay, the force on 3 due to, okay, this should have been 4. Oops, I don't know what's happening to me today. Okay, that's 3 due to, let's do 2. Okay, that's 9 exponent 9. 3 is 3000 nanocoulombs, also 5000 nanocoulombs. Okay, it's the right one. The distance is 4 centimeters. Change that to meters, then square the result. Okay, what will that be? 84.4 newtons. We've got one more. Let's do that. The force on 3 due to 4, that's 9 exponent 9, 3000 nanocoulombs. What's the charge? What's the charge at? Okay, that's 1000. Oops. Okay, let's do that. 1000 nanocoulombs. The distance, we've just calculated that as 5 centimeters. Change that to meters and square the result. Let's see what we get there. That's 50 newtons. So just show you what our force diagram looks like. So here we go. Have a force diagram. I will draw that once more here. So we have a force here, have 50 newtons here. Okay, there we go. 53.13 degrees. What's this? Okay, so we have F32 is 84.4 newtons. Okay, there we go. Then up here we have 36 newtons. Let's find the summation of forces. Okay, good to get another color here. The summation of forces in the y direction, we've got 36 newtons minus, okay, not minus, it's actually 36 newtons plus we have a force of 50 newtons. The component in the vertical direction is going to be 50 cos, not cos actually, that's sine 53.13 degrees. So the resultant force in the vertical direction is going to be 71.6 newtons. The summation of forces in the x direction, we have, okay, x direction, so we have negative 84.4. That's negative by convention, it's to the left. Okay, minus, we also have a component of 50, that's 50 cos 53.13 degrees. So the resultant force here is 55.6 newtons. Okay, what else? Let's now find, that's negative. The negative sign only shows that it's towards the left. So our resultant force diagram looks like this. Have a force of 55.6 newtons and a force of 71.6 newtons. We've got to find the resultant force, which is going to be the square root of 71.6 and 55.6 squared. So if you do the math here, you'll have 90.66 newtons. 90.66 newtons. Let's find the direction. Let me call that direction alpha to the horizontal. So alpha will be tan arc tan of, let's see, 71.6 divided by 55.6. That's going to be about 52.2 degrees. So the net force is 90.6 newtons at 52.2 degrees to the horizontal. Don't forget that. Okay, I have two more problems. Three more problems. Okay, that's good. Problem number 8. 2-point charges A and B of negative 17.6 microcoulombs and negative 9 microcoulombs are placed in a vacuum. So we know the permittivity of vacuum, 21 centimeters apart, and when a charge Q is introduced midway between A and B, the result of the force at B is 0. Let's find the charge Q. So there we go. We have 2-point charges at A and B. This is 21 centimeters apart. When a charge Q is introduced midway, so a charge Q is introduced 10.5 centimeters. 10.5 centimeters. Okay. Important here, the resultant force on B becomes 0. So the resultant force on B, let's find the resultant force on B. So, okay, let's do this. So if this is the charge at B, let's see the forces that B is experiencing. There is a force due to Q. So the force due to Q, since Q is a positive charge, what charge is at B? Okay, this is negative 9.0 microcoulombs. This is, what is this force? Negative 17.6 microcoulombs. Okay, so there we go. In this case, we'll have a force of attraction. The force of attraction, the force on B due to Q. Then also we'll have a force of repulsion from A, because so we'll have a force of attraction and a force of repulsion due to A. So the force on B due to A. There we go. Let's find the two forces, and actually the two forces are equal. So since the resultant force on B is 0, the force on B due to Q is the same as the force on B due to A. So let's find this. That's going to be K times the charge at B is 9 times 10 to the power -6 times Q divided by the distance is 10.5 times 10 to the -2 squared equals K times the charge at B is 17.6, 10 to the -6 times the charge at B, that's 9, divided by the distance is 21. The distance between A and B is 21 times 10 to the -2 squared. So in this formula, K crosses out, and if you do the math, you'll find that Q is actually 4.4 times 10 to the -6 coulombs, or you could just say 4.4 microcoulombs. Hello everyone, let us discuss about an electric field. So imagine you bring a positive charge. And place it somewhere in space. If you bring another positive charge, there will be an invisible force of repulsion. If you bring a negative charge near the positive charge, then there will be an invisible force of attraction. How does the negative charge A and the positive charge B know about the presence of the charge that you placed here at the beginning? Well, the answer lies in what we call the electric field. Well, an electric field is the space. An electric field is the space around the charge where its influence of attraction or repulsion can be experienced. Okay, so let's look at this in great detail. Every time you place a charge in space, say a charge at this point, it creates a region around itself, and within this region, if you bring another charge in this vicinity, then it can experience the force of attraction or repulsion. This space here, or this region around the charge, is what we call an electric field. Within this region, if you bring any other charge, it can feel the presence of the charge that you placed here, the positive charge or a negative charge, whatever case it is. Okay, electric fields are invisible, but we can only visualize them or see them using electric field lines. Let us talk about electric field lines. So electric field lines are used to represent and visualize an electric field. Let us go ahead and look at the characteristics or the properties of electric field lines. So the properties of electric field lines are as follows. Let us look at them one by one. The first one is that the lines of force, which are the electric field lines, that's another name, the line of force start from the positive charge and terminate at the negative charge. So suppose we have a positive charge, okay, put this better, suppose we have a positive charge placed in space and a negative charge placed in space. Electric field lines will move or start from the positive charge towards the negative charge. So there we go. Our electric field lines start from the positive charge and head towards the negative charge. Oops. These electric field lines do not intersect, so take care of that. So we have electric field lines moving from the positive charge. They travel until they meet a negative charge in which to terminate. So in this case, there we go. If I place another negative charge here, some of these electric field lines will be attracted to this negative charge. They will terminate at this negative charge. Let us keep our diagram simple just to explain the properties of the electric field lines. So they start from the positive charge and they terminate at the negative charge. Number two, electric field lines or the lines of force, they never intersect. Okay, that is very evident. These lines are very distinct. However many they are, they cannot or they must not intersect. You see, electric field lines represent the direction of an electric field. So if two lines intersect, that would mean that the electric field has two directions at a point, which would violate the laws of physics. So electric field lines never intersect. Number three, the tangent to the electric field line or the line of force at any point gives the direction of the electric field at that point. So let's take a case study of these electric field lines here at the bottom. If we want to know the direction of an electric field here, simply draw a tangent at that point. Okay, not so accurate, but hope you see the idea. So if I placed a positive charge here, it would move in this direction. So this is the direction of the electric field. An electric field line is a line such that any tangent drawn to it at a point gives the direction of the electric field at that point. So a tangent drawn anywhere at the electric field line gives us the direction of the electric field at that point. The direction of the electric field is the direction in which a positive charge would move if placed at that point. Number four, the number of electric field lines per unit area through a plane at right angles is proportional to the magnitude of E. E represents the electric field. So this means that where the lines of force are close together, the electric field is large, and where they are far apart, the electric field is small. In this diagram, you can see that the electric field lines are close. So the field lines are close at this point. Here the field lines are spaced. So that also here the field lines are spaced. So what does this mean to us? This means the electric field is stronger at this point, and the electric field is weaker at these 2 points. So where the electric field lines are so close together, that represents a stronger electric field. The measure of how strong the electric field is what we call the electric field intensity. the electric field intensity. It's a vector E which represents the force per unit positive charge placed at that point in an electric field. We'll discuss that in a moment. Okay, another property of electric field line is that each unit positive charge gives rise to 1 over epsilon lines of force in free space. So, of course, in this diagram, to avoid exaggeration, we have only drawn few electric field lines, but the number of electric field lines is proportional to 1 over epsilon naught. So if I have a charge of just plus 1 coulomb, a charge of plus 1 coulomb placed in free space, the number of electric field lines is going to be 1 over the value of epsilon is 8.85 times 10 to the power negative 12, so that's going to be 8.85 times 10 to the power 12 electric field lines. Just from a charge of plus 1 coulomb will have that number of electric field lines, 8.85 exponent positive 12. That's quite a big number of electric field lines, which we do not represent here to avoid exaggeration of the diagram, but something important to know. And lastly, the number of electric field lines is proportional to the magnitude of charge. Okay, so let us imagine we have two charges, a charge Q and a charge, okay, so let's have a charge positive Q. Let's also have another charge positive 2Q. So the number of electric field lines is proportional to the magnitude of charge. If the charge is bigger, then we'll have more electric field lines. If we have, from this charge of positive Q, if we have 1, 2, 3, 4, 5, 6 electric field lines, since this charge is twice the number, the magnitude of this charge, it must have twice the number of electric field lines. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So there we go. So take care of this, or take note of this when you're drawing electric field lines, especially when you're dealing with charges of unequal magnitudes that are not equal. Make sure that the bigger the magnitude of the charge, the more the electric field lines that come from it. So these are the properties of electric field lines. Next, let us apply these properties of electric field lines to draw some examples of electric field patterns or configurations. So we'll begin with isolated charges. An isolated charge is a charge that is placed alone in free space. So when we talk about isolated charges, let us begin with an isolated positive charge. An isolated positive charge. If a positive charge is placed in space and isolated, that means there are no other charges surrounding it, then the electric field due to this positive charge will be just like that. So this is what an isolated positive charge would form. There we go. As you can see, the electric field lines are starting out from the positive and heading outwards. They will travel any distance up to infinity until they find a negative charge to terminate at. Okay, if we have an isolated negative charge, if we have an isolated negative charge, that's how it would look like. We have a negative charge, we have electric field lines. Now, we don't care where they come from, but they must terminate at the negative charge. So the arrows are pointing inwards. This is very important. Okay. let us draw electric field lines involving charges that are unlike. So let's talk about unlike charges. Unlike charges placed together. So let us have a charge, a positive charge. Let's assume this is plus Q, and a negative charge minus Q. So these unlike charges are of equal magnitude. So the size is the same, plus Q minus Q. This is how our electric field is going to look like. Electric field lines start out from the positive towards the negative. There we go. The electric field lines that are far away will not have a chance to make it to the other side. So we can just represent them like this. Arrows are very important. They give us a clear definition of which is positive and which is negative. So we always have to include the arrows. Okay, there we go. Notice that in this example, we have unlike charges. That means positive and negative charges, but of equal magnitude. So the size is the same. That's why the configuration looks like that. So let's suppose that these charges had different magnitudes. So let's suppose they had different magnitudes, so different sizes. So let us suppose our positive charge is plus 2Q, while our negative charge is minus Q. So the magnitude of the positive charge is 2 times bigger than the magnitude of the negative charge. Let's see how this would look like. Remember, the number of electric field lines is proportional to the magnitude of the charge. So this charge is bigger, obviously it will have more electric field lines. So there we go. Oops. Okay, so because this charge is bigger, okay, it will have to take up all the electric field lines that come from the minus Q. Not any of them will go away. So there we go. So all the electric field lines coming out of negative Q have been absorbed by the positive charge, but the positive charge is going to have an excess number of lines coming out of it, which will travel to find another negative charge. So I have 1, 2, 3, 4, 5, assuming this also had to give up 5. So I have more 5 from this that did not find a charge. 2, 3, 4, 5. Okay. There we go. That's how this would look like. And you can draw many more other diagrams. You don't have to necessarily count the number of electric field lines, but I find it a good practice to make my sketches look better. So let's look at more configuration. Here we have unlike charges of equal and different magnitudes. Now let us look at like charges and see how the pattern would look like. So let's have equal charges, like charges. So we'll begin with like charges of equal magnitude. Like charges of equal magnitude. Let us use positive charges in our illustration. You could also do this with negative charges. So there we go. Positive charges, 2 of them placed in space. Okay, just extend this a little bit near. So we know that positive charges will repel each other because they are all positive, they are like charges. So there we go. The electric field lines cannot intersect, so they must move as close together as possible, but without intersecting, without coming together. Oops, it's a little difficult to draw. Try to make that better. Okay. So there we go. As you can see, the electric field lines do not meet at any one point. Okay, just try to make this a little more clearer. Likewise down here. So this is how the electric field line will look like, and in between here we'll have a point called the neutral point. Because of the repulsion of these charges, we'll have a point left where there is no electric field. So I've got to indicate the electric field lines. All the electric field lines are pointing outwards. So it is very clear why they cannot intersect, because all of them are from the positive charges and all of them are defining the direction, so they cannot intersect at any one point, and yet they cannot move from one charge to the other. So this creates some kind of diagram like this, and we have a neutral point where the electric field is 0. The fact that these lines are actually not intersecting but passing close to each other tells us why there is a force of repulsion between these charges. So let us suppose we have the same configuration but of different magnitudes. So let's have unequal magnitude. So let's suppose we have plus 2q against plus q. So this charge is obviously bigger than this. Oh, by the way, I didn't count the number of electric field lines here, so sometimes that may be of concern, but okay, let's just leave it that way. So here I have twice the charge, here I have the charge q. Let's see how this would look like. So because this charge is stronger, obviously the force of repulsion is going to be great on this charge. So there we go. This is kind of what this would look like. It would push the other charge far away. So as you can see, the distance of the neutral point has now extended towards the plus q charge, because the plus 2q is actually bigger. So this is typical of what we could have. There we go. We indicate the electric field lines with arrows, very important. Okay, still the electric field lines do not intersect. The difference here is that more electric field lines are coming from the plus 2q charge, and the neutral point is also close to the plus q charge than the minus q. In this first diagram, the neutral point is actually equidistant from both, and so you can see also the electric field lines from this plus q charge, most of them or all of them are actually being pushed to the other side. So that explains why it will experience a bigger force of repulsion. So this same process could happen for negative charges. I want to make this longer by doing that too, but the same would occur. So let us see the electric field line between a positive charge. Okay, positive charge, maybe, and a negative plate. So let's suppose we have a positive charge, a point charge, and then we have a plate. Okay, this is a conducting plate or something that is charged negatively. The rules of electric field lines would still work here. So electric field lines would move from positive to negative, just like that. Okay, there we go. The electric field lines would look like that. If I had a positive plate and a negative charge, the same process would occur, only the arrows would be reversed. The arrows would be facing upwards. Okay, so that's that easy. Okay, let's look at, that was DE. Let's look at oppositely charged plates. Oppositely charged plates. So suppose we have a positively charged plate and a negatively charged plate. Okay, just to make them look better, I'll draw this. Oops. So the electric field lines would move from the positive to the negative charge. Sorry, from the positive plate to the negative plate. The electric field is very uniform inside the plates, and this electric field inside the plates is given by V over D, where D is the distance of separation and V is the potential difference between the plates. Okay, but that's not important for now. What is important is that the electric field inside here is uniform, but as you come towards the edges, the electric field is not that uniform. It begins to bulge outwards. So the electric field outside or close to the ends of the plates is not uniform, but inside the electric field is uniform. Oops. So the electric field lines do not have to intersect even here. Okay, so that's what it would look like. So we have so far discussed that the magnitude of the electric field, or the strength of the electric field, is determined by the closeness, the density of the electric field lines at a point. So let's look at how to calculate the electric field intensity in great detail. So let's look at electric field intensity or strength. So the electric field intensity or electric field strength, sometimes we just call it the electric field, and you'll hear me say electric field more commonly. So the electric field strength is the force, or the electrostatic force, is the electrostatic force acting on a charge of +1 coulombs placed, +1 coulombs placed at a point in an electric field. So, as you know very well, or you may, but this is very common in physics, every time we talk about the intensity of a force, we always define it as the force per unit measure. So intensity is basically the force per unit measure. And likewise, when we talk about, or when we discuss electric field intensity, it is the electrostatic force per unit measure, in this case per unit charge, and the unit charge is +1 coulombs. So intensities of forces in physics are very important because they help us to make general equations, or they help us to classify force fields using general quantities like their strength. So let's write this in some sort of mathematical equation. So the electric field strength is represented by letter E. That would mean the magnitude, but this is a vector quantity, do not forget that. But let's only represent it using its magnitude. So the electric field intensity is given by the force per unit charge. So let me have Q naught as my charge. So the electric field intensity is given by this, where the force is in newtons, the charge is in coulombs. So the units of E, units of the electric field intensity, are newtons per coulomb, newtons per coulomb, or volts per meter. So this is newtons per coulomb or volts per meter. Now we haven't discussed what volts is, but we'll discuss this as we look at electric potential. It's also another common unit for electric field intensity. So what does this mean for us as physicists? It means if we know the electric field intensity, we can always find the electric force at any point. So if we know the electric field intensity, we know the electric field intensity, we can calculate the force on any charge, Q naught placed at a point in the electric field. So from this equation, you can see that if the electric field intensity is the force per unit charge, so the force, the electrostatic force of attraction or repulsion, is the product of the electric field intensity and the charge that is placed in an electric field. So using this equation, we avoid the hassle of applying all the full-scale Coulomb's law equation to find the electrostatic force. So it becomes easier to generalize the properties of the electric field if we know the electric field strength. So we'll end this by looking at the electric field strength or the electric field intensity due to a point charge. So the electric field intensity due to a point charge, So we know from Coulomb's law that the electrostatic force is given by K times Q naught divided by R squared. Suppose we have two charges, Q and Q naught, where K is 1 over 4 pi epsilon. In case this is free space, then we have epsilon naught. So that's okay. Let me just leave it as a general equation. Now the electric field intensity is given by the force per unit charge, Q naught, force over Q naught. So our electric field intensity is going to be K, Q times Q naught divided by R squared. All this is going to be divided by Q naught. If you do the math, this will give us K Q divided by R squared. So I substitute the value of K. Our electric field intensity is going to be given by Q over 4 pi epsilon R squared. This equation here gives us the electric field intensity. The electric field intensity of okay, the electric field intensity at any point, a distance r from the charge q. So what does this mean for us? It means every time we know the distance from the charge q, if I have a charge q in space, if I bring another charge any distance r from the charge q, then I can calculate the force that test charge q naught is going to experience. It's just going to be the electric field intensity times the test charge. So electric field intensity is important because it helps us to generalize our calculations in physics. Thank you for watching this video. Don't forget to subscribe. If you're watching this on YouTube, also like the video, leave a comment, and I'll see you sometime. Okay, we know that the electric field intensity due to a point charge is given by Q over 4 pi epsilon 0 r squared. So this is the electric field intensity due to a point charge. But what if we have more than one point charge in space? So we have a point charge Q1 here and another point charge Q2 placed here. All these point charges will contribute to an electric field at any arbitrary point P. So the electric field at this point will be having that direction. Let's say the electric field intensity due to Q1 will also have the electric field intensity due to Q2 and many other electric fields that we may have. Remember, electric field is a vector quantity, so the total electric field intensity at that point, the total electric field intensity will actually be the vector sum of the electric field intensities. So if I could add the vector sum of the electric field intensity due to Q1 plus the vector sum, okay, plus the vector of the electric field intensity due to Q2, that would give me the electric field. So that's the so-called principle of superposition of electric fields, and we're going to be applying it to solve most of these problems involving electric field intensity. Okay, let's begin. So we have point charges of 4 microcoulombs and negative 6 microcoulombs, and I want to find the electric field intensity at point P. So let's look at this in a vector diagram. So the electric field intensity due to the 4 microcoulomb charge at this point is actually going to be, this is a positive charge, so electric field intensity is the force per unit positive charge. So we assume there is a charge of +1 coulomb placed here, so plus and plus will actually repel each other. So that's the direction of the electric field intensity due to Q4. I'm going to call that E4. Also the electric field intensity due to the negative 6 microcoulomb charge. Since this is a negative, the electric field intensity will point to the left. So allow me to call that E6. Okay, there we go. So let's calculate the resultant electric field intensity, beginning with the electric field intensity due to Q4, the charge of 4 microcoulomb. That's going to be 4 microcoulombs. So okay, just to begin with the electric field intensity of any point charge given by Q over 4 pi epsilon 0 r squared. So the electric field intensity due to the 4 microcoulomb charge is going to be, I summarize all this of course to the common formula, K times Q divided by R squared, where K is 9 times 10 to the power 9, assuming we're working with free space or vacuum. So our charge is 4, then our K is 9 exponent 9, our charge is 4 microcoulombs. Don't forget to change that to coulombs. The distance from 4 microcoulombs to point P is 5 centimeters plus 2 centimeters. That's a distance of 7 centimeters. So 7 centimeters, that's 0.07 meters. Okay, I've got to square that. Okay, so let's see what we get. If you put this on the calculator, you get approximately 7.347 exponent 6 newtons per coulomb. That's the electric field intensity due to Q4. Let's do that also for the electric field intensity due to the negative 6 microcoulomb charge. That's going to be 9 exponent 9 times 6 times 10 to the power negative 6. I change the 6 microcoulombs to coulombs. Of course, I don't indicate the negative sign here because I will take care of the direction using the vector diagram. The distance between the negative 6 microcoulomb charge and the point P, where we are finding the electric field intensity, is 2 centimeters, that's 0.02 meters. So if you plug these values into the calculator, you have 1.35 times 10 to the 8th power. Okay, guess that's it. Okay, got to prove that perhaps. Newtons per coulomb. So this, of course, is to the right. Just indicate that. To the right. Is that right? To the left, sorry. That's to the left, it's in that direction. And then this is to the right. So obviously they are in different directions, so we can find the resultant electric field intensity. Let's call that E. The greater one is, you can see from the figures that this is actually greater, so we'll have 7.347 exponent 6 minus this 1.35 exponent 8, and if you do the subtraction, you've got 1.2765. That's so 1.2765 times 10 to the negative positive 6 newtons per coulomb, and that's going to be to the right. So that's very important because electric field intensity is a vector quantity. You've got to state the magnitude and the direction. So in this case, the right is the direction and the magnitude is this 1.2765 exponent 6 to the power 6 newtons per coulomb. Let's look at another problem. So we'll find the electric field intensity at this point B. Let's draw a force diagram. Assume there is a charge of +1 coulomb placed here. That's by definition what electric field intensity is, the force on a charge of 1 coulomb. So the electric field intensity due to A at this point is going to be in this direction to the right, since there is repulsion between positive and positive. So let's call that the electric field intensity due to the charge at A. Then the electric field intensity due to the charge at C, as you can see, this is positive, negative, so it's going to be attraction. So the electric field intensity due to the charge at C will also be in that direction. So the resultant will probably be in that direction because all the vectors are pointing to that direction. So let's go ahead and calculate the electric field intensity due to the charge at A. The charge is 5 microcoulombs. Okay, 9 exponent 9 times 5 times 10 to the negative 6. That's to convert it to coulombs. The distance between A and B is 10 centimeters, so that's 0.1 meters squared. Okay, if you plug those into the calculator, I have 4.5 exponent 6 newtons per coulomb. Let's find the electric field intensity due to the charge at C. Oops, this has got to be C, the electric field intensity due to the charge at C. 9 times 10 to the power 9, 3 times 10 to the power negative 6. The distance between B and C is 5 centimeters. That's 0.05 squared. If you plug this into the calculator, you have 10.8 times 10 to the 6th power newtons per coulomb. So our resultant electric field intensity, or our total electric field intensity, or our resultant, let's call that E. It's actually going to be EA sorry about that, plus EC, because they're all in the same direction. So we'll have 4.5 exponent 6, then 10.8 exponent 6. Okay, if you do that, you'll have about 15.3 exponent 6 newtons per coulomb. So that's our resultant electric field intensity. Okay, I forgot to do this often. So this is to the right. Also, this is to the right. So all the forces are pointing to the right. So our final answer also is 15.3 times 10 to the 6th power. This is to the right. By convention, all forces to the right are positive, forces to the left are negative. Okay, let's have another problem. This time around we have a two-dimensional problem. We have forces in some kind, charges placed in some kind of triangular configuration. We want to find the electric field intensity at point C. So here we go. Assuming there is a charge of +1 coulomb here, let's see the forces acting at this charge. If that's our point C, the electric field intensity due to A, this is positive, so that's going to be repulsion. It's going to be in that direction. Okay, just to have this letter C, I'll bring it at another point. Okay, so there we go, the electric field intensity due to the charge at A. The electric field intensity due to the charge at B is going to be pointing in this direction towards B, because this is positive and negative. So that's going to be attraction. There we go. Let me introduce the y-axis and the x-axis just to help us in resolving the forces easier. So if I have this line here and then another line here, it's important to find these angles because we'll use them while resolving the forces. So this is an equilateral triangle. You can see this side is equal to this, is equal to this. So all the angles in an equilateral triangle are going to be 60. We don't need to do a lot of calculation there. The interior angle sum has to be 180. So each one of those angles has to be 60, 60, 60. That's from the properties of an equilateral triangle. So there we go, we have 60 degrees here, also 60 degrees there. So this is the electric field intensity due to the charge at B. Okay, so this is going to be helpful for us to find the resultant electric field intensity, because we will easily get the components of EA and EB in the vertical and horizontal directions. So let's find the electric field intensity. The electric field intensity due to the charge at A, that's going to be 9 times 10 to the power 9. That's the constant K. Then the charge is 5 microcoulombs. So 5 times 10 to the negative 6. The distance between A and C is 20 centimeters. This is an equilateral triangle. So that's 0.2 meters squared. If you put these values into the calculator, you get about 1.125 times 10 to the 6th power newtons per coulomb. let's do that also for the electric field intensity due to the charge at B. 9, okay, 9 exponent 9 times the charge is -3. Okay, I don't need to indicate the negative. After all, we'll take care of the directions using this force diagram. So there we go, -6 divided by the distance between B and C is 20 centimeters, that's 0.2 meters. So if you put these values into the calculator, you have 6.75 times 10 to the 5th power newtons per coulomb. So there we go, we have these two forces. We can now find the resultant force. Let's begin with the forces in the horizontal direction. So the forces in the horizontal direction, I love to call this the x-axis. So the summation of forces or the electric field intensity in the x-axis. So let's see, the component of EA in the x-axis is going to be, of course, EA is this 1 point, okay, let's just do it this way. We have EA cos of 60 degrees plus also EB is in the positive direction, since this is the positive x-axis, negative, positive, negative. We know that from the Cartesian plane. So plus EB times cos of 60 degrees, this angle here. So that's the resultant force in the x-axis. If we put in the values, EA is 1.125 exponent 6, then cos 60 plus EB is 6.75 exponent 5 cos 60. If you do the math here, put these values into the calculator, you get 9 times 10 to the power 5 newtons per coulomb. That's the resultant force in the horizontal. Let's find the resultant force in the vertical, in the y-axis. So I'll call that the summation of forces, or the summation of the electric field intensity in the y-axis. Okay, from this diagram, that's going to be EA, okay, EA sine 60, because that's in the positive direction, the component of EA in the positive direction, but EB is in the negative direction, so I just have to subtract that, minus EB sine 60. So put in the value of EA here, that's 1.125 exponent 6 sine 60 minus EB is 6.75 exponent 5 sine 60. Okay, just have more space here. If we go ahead and do this, you have, if you do this on the calculator, you have about 9.81 exponent 5, okay, times 10 to the power 5 newtons per coulomb. So there we have the forces in the horizontal direction and the forces in the vertical direction. Let's do the final resolution here to find what the total force is. So the resultant force in the x-axis, is a positive force, so it points in this direction. That's 9 times 10 to the power 5 newtons per coulomb, and the resultant force in the vertical direction also is positive. So there we go, 9.81 exponent 5 newtons per coulomb. So our resultant electric field intensity, if I call that E, is going to be, by Pythagoras theorem, the square root, just have more space here, that's better, the square root of, okay, begin with the vertical, 9.81 exponent 5 squared, what's that going to be, plus 9 exponent 5 also squared. So the resultant electric field intensity here is going to be, oops, guess I made a mistake here in the values. Okay, so just a moment, let's correct that. This value is going to be different. Okay, there we go. The resultant force in the vertical direction is actually, if you do that on the calculator, it's about 3.8971 exponent 5. Okay, exponent 5, 3.897 exponent 5. There we go. 3.897 exponent 5. Okay, that's better. So the resultant here is approximately 9.81 exponent negative 5. There we go, newtons per coulomb. Also, since this is a vector quantity, we've got to find the direction at which this force is acting. So to find the direction, you just have to find this angle alpha. Let's go ahead and do that. So also looking at that triangle, you can see that alpha is actually going to be tan arc tan of the vertical component, 3.897 exponent 5 divided by 9 exponent 5. Okay, so if you do this, have about 23.4 degrees. So our answer is that the electric field intensity, so I'll call that the E field intensity, is going to be the force, the electric field intensity, 9.81 exponent, this is not negative 5, okay, sorry about that, exponent 5 at an angle of 23.4 degrees to the horizontal. Okay, so let's recap for this problem. It's quite a long one because it's in 2 dimensions. So the most important part is to extract the force diagram, a correct force diagram from the configuration of charges. After finding these forces, resolve to find the total force in the x direction, the horizontal direction, and the total force in the vertical direction. Then we draw a separate diagram for only those 2 forces. That helps us to find the total or the resultant electric field intensity. So using Pythagoras theorem, also using simple rules of trigonometry, basic trigonometry, you can find the direction of that force, and there we go. Okay, let's have another example. Okay, this example, we have the same thing. We have A, B, C. So let's indicate the charges here. The charge at A is actually 0.1 microcoulomb. The charge at B is 0.05 microcoulomb. So we want to find the electric field intensity at C. Okay, this is a 2-dimensional problem, so let's draw also a force diagram here. For simplicity, I always put a +1 Coulomb charge here. So between 0.1 and 1, all these are positive charges, so the direction is going to be that direction. Let me call this the electric field intensity due to the charge at A, it's in that direction. Then the electric field intensity due to the charge at B, this is positive, this is also positive, so it's in that direction. There we go. The electric field intensity due to the charge at B. So let's go ahead and include our y-axis and x-axis just to make it easier for us to resolve the forces. Also, let's find these angles. They will be helpful. So if I draw this this line here, that means we have 4 centimeters here. So these are 5 centimeters, 5 centimeters. I can find what this angle here is. Let's go ahead and do that. So let's call this angle theta. That angle theta is the same angle here and is the same angle here. So let's calculate what that angle theta is. Theta from this diagram is going to be from cos arc of 4 over 5. Okay, cos arc of 4 over 5, which is what's that, 36.9 degrees. Okay, 36.9 degrees. So we have 36.9 degrees here, 36.9 degrees here. That's going to be very helpful. Okay, let's calculate the electric field intensity due to A. That's going to be the electric field intensity due to the charge at A, 9 exponent 9. The charge is 0.1 times 10 to the negative 6th. The distance between A and the point C is 5 centimeters. So that's 0.05 meters squared. If you plug those values into the calculator, okay, you can go ahead and do that. So we have about 3.6 times 10 to the 5th power newtons per coulomb. The electric field intensity due to the charge at B is 9 exponent 9 times the charge 0.05 exponent negative 6 divided by the distance, which is also 5, 0.05 squared. That's about 1.8 times 10 to the power 5 newtons per coulomb. So let's use these two values to find the resultant electric field intensity. So let's find the electric field intensity in the horizontal direction, in the x-axis. The summation of electric field intensity in the x-axis will be EA cos 36.9, because that's in the positive x direction, minus EB cos 36.9. Okay, that's degrees. Anyway, so go ahead and put in the value of EA here, the value of EB there. Let's see what we have. EA is 3.6 times 10 to the 5th power minus EB is 1.8 times 10 to the 5th power cos 36.9. That's about 1.45 newtons per coulomb. Let's also find the resultant electric field intensity in the vertical direction. That's going to be EA, let's begin with that, EA sine 36.9 plus, because all of them are pointing, all the components are pointing in the positive y direction, so that's plus EB sine 36.9 degrees. So let's substitute the values. So let's substitute the values. We have EA, that's 3.6 exponent 5 sine 36.9 plus 1.8 exponent 5 sine 36.9. So if you put these values into the calculator, let's see what we have. That's about 3.24 exponent 5 newtons per coulomb. So let's use these two, okay, these two results, this and this, to draw a force diagram, a final force diagram representing the vertical and horizontal component. So our vertical component is positive, there we go, 3.24 exponent 5. Our horizontal component is also positive, 1.45 exponent 5 newtons per coulomb. So our resultant electric field intensity will be in that direction, and it's equivalent to the square root of 3.24 exponent 5 squared plus 1.45 exponent 5, okay, that's squared 2. That's about, let's see what we have, 3.55 exponent 5, that's newtons per coulomb. Okay, that's the electric field intensity due to the two charges. Let's find the direction, call that direction beta perhaps. So beta is going to be tan arc of the vertical component, 3.24 exponent 5 divided by 1.45 exponent 5, and that's going to be about 65.9 degrees. So the resultant electric field intensity, in this case, the electric field intensity is going to be this 3.55 exponent 5 newtons per coulomb at an angle of 65.9 degrees to the horizontal. Okay, there we go. Let's have a final problem on electric field intensity. So here we're having a rectangular configuration, okay, still a two-dimensional problem. We want to find the resultant electric field intensity at this point S. Okay, let's draw the forces at point S. Of course, we assume there is a charge of +1 coulomb here. So let's begin with R. This is a positive charge, and this is a positive charge. So at R, there's going to be a repulsion electric field intensity in that direction. So that's the electric field intensity due to R. Okay, let's look at in this direction. This is negative, this is positive here. So this is going to be attraction. Is that so? Yes. Okay, yeah, that's it. So the electric field is going to be in that direction. Let's see due to the so this is the electric field intensity due to P. Let's see the electric field intensity due to Q, as you notice here. So this is a positive charge, this is positive, there's going to be repulsion. So the electric field intensity due to Q is in that direction. This distance, okay, let's check the question. This distance is 3 centimeters. This distance here is 5 centimeters. 4 centimeters, sorry. So by Pythagoras theorem, you can calculate this distance. If you have 3 here, oops, just make this better. if you have 3 and 4, then this is 3 squared plus 4 squared under square root. So that's going to be 5 centimeters. Okay, so let's have that 5 centimeters. Also, we could find this angle here. Let's call that angle alpha, because that's going to be very useful in resolving. We've got to find what this angle is. Just prolong this a little with this angle here. So let's call that alpha. Let's see how to find alpha. We have every alternative we could ever want. So let's just say alpha equals arctan of 3 over 4, and that's going to be, okay, that's 36.9 degrees. Okay, let's go ahead and find the electric field intensities now. So that's 36.9 degrees. Let's begin with the electric field intensity due to P. The electric field intensity due to the charge at P, the negative 3 microcoulomb charge. So that's 9 exponent 9 times 3 exponent negative 6, because that's, oops, these charges are in coulombs, very important here. So no need to convert. That's 3 exponent negative 9 here, as it is given here. This is already in coulombs. The distance between P and S is 4 centimeters. This is a rectangle. So this is the same as this. This is equal to this. So that's 4 centimeters, 0.04 meters squared. In this case, the resultant, the electric field intensity due to P is 1.687 exponent 4 newtons per coulomb. Let's do that for the electric field intensity due to Q. That's 9 exponent 9 times the charge at Q is 4 exponent negative 9. That's actually 4 nanocoulombs. The distance is 5 centimeters, so 0.05 squared. Okay, let's see, what do we get there? Put this in the calculator. It's 1.44 exponent 4 newtons per coulomb. Then the electric field intensity due to R, that's 9 exponent 9 times the charge at R is 3 times 10 to the negative 9 divided by the distance. The distance is actually 3 centimeters, 0.03 squared. If you do this, you have 3 exponent 4 newtons per coulomb. So let's find the resultant force in the x-axis, the resultant electric field intensity. Okay, that's going to be negative EP, because that's in the negative direction. ER has no horizontal component, so we don't have any component in the horizontal, plus we have EQ cos 36.9. so EQ has vertical and horizontal components. The horizontal component is that. So if you put in these values, so I'm not going to do that for this, but if you put in these values, actually have negative negative 5.355 times 10 to the positive 3 newtons per coulomb. The negative here shows you that the resultant is actually pointing in the negative direction. If you do that for the resultant force in the horizon, the resultant electric field in the in the vertical direction, so the summation of forces in the y direction, you have the resultant, the electric field intensity due to R plus the electric field intensity due to Q sine 36.9. So As you see, the electric field intensity due to Q has a vertical component in the positive direction. If you put in the values here, you'll have about 3.865 exponent 4. Okay, there we go, newtons per coulomb. So let's draw a final force diagram to find the resultant electric field intensity. Notice that this is in the negative direction, so our force diagram looks like this. Oops. We have 5.355 times 10 to the third power, so that's in the negative direction. I don't need to put the negative here again. This is positive 3.865 times 10 to the fourth power. There we go. Our resultant electric field intensity is here, and that's going to be the square root of 5.355 exponent 3 squared plus 3.865 exponent 4 squared. If you put this into the calculator, I'll have about 3.9 times 10 to the fourth power newtons per coulomb. Okay, there we go. Let's go ahead and find the direction of this force with respect to the horizontal. Let's introduce an angle, maybe theta. So theta is going to be arctan of the vertical, 3.865 exponent 4 divided by 5.355 exponent 3. That's about 82.11 degrees. Okay, so our final answer here is that the electric field intensity is 3.9 times 10 to the fourth power at an angle of 82.11 degrees to the horizontal. Okay, that's perfect. In this video, we will discuss the concept of electric flux and Gauss's law. Let us begin with electric flux. So electric flux, we denote that with the Greek letter phi. Electric flux is the amount of electric field penetrating a surface. So the amount of electric field penetrating a given surface is what we call the electric flux. Let us consider this in a more mathematical form. Before we do that, we know that the electric field intensity or the electric field strength is directly proportional to the number of electric field lines, passing through a given area, and perpendicular to that area. Okay, so this tells us that the electric field is equivalent to the electric field lines or the electric flux per given area, phi divided by A. And from here we can conclude that the electric flux, phi, is equal to the electric field intensity times the area through which the electric flux is flowing. In this equation, we have considered a plane area and an electric field that is perpendicular to the plane of this area. So in that case, the formula holds because the electric field is perpendicular to the plane. The electric field is perpendicular to the plane of the area. Okay, so there we go. Or the normal to the area and the electric field are actually parallel. But this is not always the case. What if the plane of the area is aligned at a different angle to the electric field? So let's have that. Let's suppose we have an area, certain area that is aligned at an angle theta to the electric field. So that's our area. Then we have an electric field. An electric field flowing through this area. There we go. Let's suppose the electric field is in this direction. The electric field is in this direction. As you notice, the electric field and the plane of this area are actually inclined at a certain angle. Which angle? Let's call that angle alpha. And let's suppose that the normal to this area is this. So I draw a line that is normal to this area, perpendicular to this area. Let me extend this line. And let's suppose that the angle between the normal to this area and the electric field is theta. So in this case, the component of the electric field that is passing through this area perpendicular to it is going to be given by, so this component is E cos theta, and so our electric flux is going to be given by E cos theta times the area. So to make it more general, we have E times A times cos theta, and this gives us the electric flux through an area. As you notice from this equation, if theta is 0 degrees, that means if we have a case where the plane is perpendicular to the electric field, that means the normal is going to be parallel. Normal is going to be parallel to the electric field. In that case, theta is going to be 0, and so we'll have phi as the electric flux as E times A times cos of 0, which is 1. So we have E times A, and in this case we have the maximum electric flux. Also, if we have theta as 90 degrees, that would mean that the electric field and the area are actually parallel, like this. So in this case, this is the normal to the area. There we go. This is the electric field. In this case, the electric flux, which is given by the electric field times the area times cos theta, will be E times the area times cos of 90 degrees, because there's an angle of 90 degrees between the electric field and the normal to the area, and cos of 90 degrees is 0. So in this case, the electric flux through the area is going to be 0, and this is the case where we have minimum electric flux. Minimum electric flux. Okay, let's look at the flux through open surfaces and the flux through closed surfaces. We'll begin with open surfaces. So electric flux through open surfaces. Let us suppose we have an arbitrarily open surface and we have an electric field through this surface. So there comes our electric field in that direction. Now, to avoid the exaggeration, I'll only draw one electric field line to represent all the other electric field lines. So there's our electric field. And let's suppose that it is passing through a certain element of the area. Let's call that area dA, and the normal to that component, to that small portion of the area, is this. I'll draw this in dotted lines, so there we go. This line is the normal to this area. It's a small vector dA, and this is the electric field. Okay, so this is just to name that this is the area. So the electric flux, as we have just discussed, is given by the electric field times the area times cos of the angle between the electric field and the area, cos theta. This can also be written in mathematics using the vector notation as E dot A. This is a scalar product, vector E dot the vector A. So the amount of electric flux passing through the area dA, let's see what that is. The amount of flux penetrating through a small area dA, let's call that d phi, is going to be given by the electric field E times the small area element dA. So all these are vectors, which I can write as E times dA times cos theta. That's d phi. If I want to find the total electric field through this open surface, the total electric flux phi, I'll have to integrate or to add up all the small areas making up this arbitrary open surface. So I have to integrate over the whole area of d phi. So in that case, my total electric flux is going to be the integral of E times dA, cos of theta over the whole area. So there we go, the integral over the whole area of the electric field dot the small area element. Okay, let's proceed and look at the electric flux through closed surfaces. The electric flux through closed surfaces. So let us consider an arbitrarily closed surface of any shape. Just to emphasize that it is closed, I'll try to make it like this to show that it is three-dimensional. So we have our closed surface here. By convention, the normals to the surface of to the area of a closed surface point from the inside to the outward. So let me consider two small area elements dA, and the electric field is pointing from the inside to the outwards. So this is the electric field, and this is the normal to the small area element. So this is a vector dA pointing from the inside. The same happens on this side. Oops. So we have the normal. Suppose the normal is this. Then we have the electric field. Also, there we go. So the electric flux is given by the electric flux through a small area element dA, let's call that d phi, is given by the electric field dot the area element dA. Now this is only a flux through a small element. This is a flux through an area element dA. Now if we want to find the total flux through the whole surface, we have to integrate this equation. So in that case, we have the total flux is the integral of d phi, which is going to be the integral. Now this is a closed surface, so we have to integrate over the closed surface. That's very important. So we'll have the integral over the closed surface of d phi, but d phi is E dot dA. So there we go. This is going to be our total flux, the integral over the closed surface of the vector of the electric field dot the vector of the area element pointing from the inside to the outwards. Now we will use this knowledge of the electric flux through closed surfaces to derive Gauss's law. So let's look at the derivation of Gauss's law. So let us look at the derivation of Gauss's law. The derivation of Gauss's law. So for simplicity in our derivation, let us consider a sphere of radius capital R, having a charge plus Q placed at the center. So let's see what we have. Here we go. We have a sphere of radius capital R. Okay, let's have this of radius capital R having a charge of plus Q placed at the center of the sphere. So in this case, we'll have electric field lines pointing outwards from the charge plus Q, like that. Okay, there we go. So let's also consider an arbitrary element of the area dA with a vector pointing outwards, dA. So there we go. The electric field, due to the positive charge placed at the center of the sphere, is E. So let's have one line to represent the electric field vector. Okay, there we go. So we know that the electric flux, let's have another color, the electric flux due to electric flux through a small area element, the electric flux through a small area element dA, if we call that electric flux d phi, it's going to be given by E dot dA, which of course is the same as the magnitude of the electric field times dA times cos theta, if theta is the angle between the electric field and the vector of the area element dA. But as you notice from this diagram, the angle theta, so note that the angle theta is going to be 0 degrees everywhere, since the electric field is radial. So everywhere will have theta as 0 degrees, and so we can conclude that the electric flux through a small area element dA is going to be given by E dA everywhere. So let's find the total flux. If we can find, this is the electric flux through a small area element dA, so let's use this to find the total electric flux through the sphere. The total electric flux through the sphere. So the total electric flux phi is going to be the integral over the closed surface, because this is a closed sphere. So the integral over the closed surface of d phi, which is, of course, the integral. So we have phi equals the integral of E dA. So this is the integral over a closed surface of E dA. There we go, which is the same as EA, but we know that the area of the sphere is given by 4 pi r squared, and we also know that the electric field intensity due to the charge plus Q is given by Q over 4 pi r squared in this manner. So let us substitute A and E in our equation, see what we have. So E, the integral over the closed surface of E dA, is going to be given by the electric field, okay, which is Q over 4 pi r, oops, there's epsilon naught here, forgot that, 4 pi r squared epsilon naught times the area, 4 pi r squared. So Gauss's law comes out to be, you can see some terms are cancelling here. For example, 4 pi r squared, 4 pi r squared, so we have Q over epsilon naught, and on this side we have the total flux, which is the integral of E dA. Now to make this equation more general, we can have vectors E dot dA, since Gauss's law holds even for configurations that are not necessarily spherical. So this general equation here is what we call Gauss's law. Okay, just put this in a border. The equation here is called Gauss's law. Now Gauss' law is used to find electric fields due to certain configuration where we can achieve the conditions of symmetry. So let's go ahead and look at some of these applications of Gauss's law. Gauss's law is used to find the electric field due to certain configurations which are symmetrical. So applications of Gauss's law. We will use Gauss's law to find the electric field, due to, so the first one we'll deal with is to find the electric field due to a spherical shell. Spherical shell, that means a hollow sphere. Gauss's law will help us to find the electric field due to a spherical shell, both inside and outside. We'll also find the electric field due to a uniform spherical distribution of charge. So here we're talking about a solid field sphere. We'll also use Gauss's law to find the electric field due to an infinite line of charge, distribution, and we'll use Gauss's law also, number 4, to find the electric field due to an infinitely large plane. Let us begin with the first one, the electric field due to a spherical shell. So find the electric field due to a spherical shell. Let us suppose we have a spherical shell with a charge positive Q. The charge positive Q is on the surface, and we know that there is no charge inside the hollow sphere, so the electric field inside is going to be 0. So this is the center of our sphere, In order for us to use Gauss's law, we have to introduce what we call a Gaussian surface. Now let's find the electric field inside of the sphere, or inside of the spherical shell. For that case, we'll draw a Gaussian surface inside our spherical shell. The Gaussian surface is at a distance r from the center, small r. Let us suppose that the radius of this spherical shell is capital R. There we go. So inside the spherical shell, we mean that, so this is the first case, we mean that the radius of the Gaussian surface is less than the radius of the sphere. So we know by Gauss's law that the integral over a closed surface of E dot dA is given by the total charge enclosed in the surface of area A divided by epsilon naught. But in this case, the charge inside the sphere is 0, so the electric field, the electric flux E times A is going to be 0, and likewise the electric field inside the sphere is going to be 0. Let us look at the electric field outside the sphere, or outside the spherical shell. In this case, we'll draw a Gaussian surface that covers all the outside of the spherical shell. Let us suppose now that this is a Gaussian surface of radius small r still, so outside the spherical shell corresponds to a radius that is greater than the radius of the sphere under consideration. So by Gauss's law, by Gauss' law, we know that the integral, the closed surface E dot dA, is given by the charge enclosed divided by epsilon naught. In this case, since the electric field is radial and symmetrical, we have the electric field times the area, which is the total flux, is given by the charge enclosed divided by epsilon naught. The area of this spherical surface is 4 pi r squared. So the electric field times the area, 4 pi r squared, equals the charge enclosed in the sphere, which is Q, the charge enclosed in the Gaussian surface. So the total charge inside this Gaussian surface outside here is Q, divided by 4 pi epsilon naught, divided by epsilon naught, this is it. Okay, so also, about this, this is 4 pi small r squared. Should have made this clear. 4 pi small r squared. This is the radius of the Gaussian surface, and this is the charge enclosed in the Gaussian surface. So should have made this. So the electric field is given by the charge enclosed divided by 4 pi epsilon naught r squared. This is the electric field outside the Gaussian surface. Now let me plot a graph of the electric field inside and outside, the electric field inside and outside of this sphere. Let us suppose our sphere is here. The sphere is of radius r. Okay, just to make this look like a sphere, I'll try that. Okay, so at this point, this is the radius of the sphere. Inside here is the radius of the sphere, and we know that the electric field inside of the sphere is 0. So our electric field is 0 inside the sphere. Okay, just have that line inside the sphere. The electric field is 0. From here to here is a distance of r, the radius of the sphere. Then outside the sphere, the electric field is inversely proportional to the square of the distance. So it follows the inverse square law, just like that. Let's make it smoother. Oops. So the electric field is inversely proportional to the square of the distance from the center of the sphere. So this is the electric field on the vertical axis and the distance from the sphere. So in this case, this is one application of Gauss's law to find the electric field inside and outside a spherical shell. Let us also use Gauss's law to find the electric field due to a uniform spherical distribution. A uniform spherical distribution of charge density. Of course, this is a charge distribution, so it must have a charge density. Let's assume the charge density is rho Coulomb per cubic meter. Okay, so let's sketch what this looks like. We have a spherical distribution. This is a solid filled sphere. So there we go. And the charge density here, this is the center of the sphere. Suppose this sphere has a radius r. If we apply Gauss's law inside the sphere, it means we have to draw a Gaussian surface inside the sphere. So there we go, a Gaussian surface of radius small r. We know that by Gauss's law, the total flux E dot dA is given by the total charge enclosed divided by epsilon naught. In this case, the integral over E dot dA is EA, since there is symmetry and the angle is 0 degrees everywhere, because the electric field is going to be radial. The vectors of E and A are actually parallel in this case. The total charge enclosed in this Gaussian surface inside the sphere corresponds to small r less than capital R. So the charge enclosed in the Gaussian surface inside here is going to be the charge density rho times the volume of the sphere, the Gaussian surface, which is 4 over 3 pi r cubed. Okay, there we go, divided by epsilon naught. So this, the charge density times the volume charge density times the volume gives us the total charge enclosed by this Gaussian surface. Also, we know that the area of the sphere is 4 pi r squared. Sorry, the area of the Gaussian surface, not the sphere. It's very important here when we're dealing with Gaussian surfaces. This A is the area of the Gaussian surface. So let's apply that here. We will have the electric field. Now this here, the electric field times the area, 4 pi r squared, equals rho times 4 pi r cubed divided by 3 epsilon naught. In this case, 4 pi is going to cancel out on both sides, so 4 pi cancels out. Then r squared cancels out. I only have r remaining here. What else? Okay, that's it. So we have the electric field. The electric field inside the sphere is given by rho, the charge density, times the radius of the Gaussian surface divided by 3 epsilon naught. Notice that inside the sphere, the electric field intensity is directly proportional to the distance from the center. Let's look at the electric field outside the Gaussian surface. So outside the Gaussian, outside the sphere, in that case we have our Gaussian surface outside the sphere. The Gaussian surface is of radius small r, so outside the sphere corresponds to r greater than capital R. There we go. So by Gauss's law, the electric field, the electric flux, over a closed surface is given by the charge enclosed by the Gaussian surface divided by epsilon naught. This is going to be E times A. The charge enclosed by the Gaussian surface is the charge in this whole sphere, which is rho times 4 over 3 pi capital R cubed. In this case, the charge enclosed by the Gaussian surface outside is the total charge in this spherical distribution, so I use capital R here, divided by epsilon naught. The area, as previously, the area of the Gaussian surface is 4 pi r squared. The small r is for the Gaussian surface, not for the sphere, equals rho times 4 times pi r cubed divided by 3 epsilon naught. Okay, some nice terms are cancelling out here. 4 pi. What do we have left? The electric field is given by rho times r cubed divided by 3 epsilon naught r squared. So notice that in this case, the electric field intensity outside the sphere is inversely proportional to the square of the distance from the center of the sphere, like that. Let's plot a graph of the electric field intensity inside and outside the sphere. So there we go. Inside the sphere, we discovered that the electric field is proportional to the distance from the center of the sphere, and at the moment we reach the surface, then the electric field begins to vary as the square of the distance from the center of the sphere. So this is how the graph would look like. From the center to the radius, the electric field is directly proportional. This is our electric field on the vertical axis. This is our center from the sphere, the distance from the sphere. So this is what the graph looks like. From the center of the sphere to the surface of the sphere, the electric field increases with the distance from the center. Outside, when the radius, the distance from the center is greater than the radius of the sphere, the electric field begins to decrease rapidly as the square of the distance from the sphere. So there we go. This is our graph for the electric field intensity inside and outside of our spherical shell. Next, we look at the electric field intensity due to an infinite line of charge. The electric field intensity due to an infinite line of charge. So let's say this is the charge density is going to be, let's suppose it's lambda coulombs per meter. So this is what we have. We have an infinite line of charge, very thin line of charge. Let's suppose it's given a positive charge. So the suitable Gaussian surface for an infinite line of charge would be a cylindrical surface, because it can cover the whole of the infinite charge. It can cover part of this while keeping in mind the laws of symmetry. So our Gaussian surface is going to be like this. Notice in this case we do not have to consider inside and outside, since this is a very thin, I have to mention that, an infinite thin line of charge. So we cannot know what is on the inside. Assume it is very small, so there we go. That's going to be our Gaussian surface. The radius, or the distance of the Gaussian surface, is going to be small r, and the charge density here is lambda Coulomb per meter. Okay, so by Gauss's law, by Gauss law, we know that the electric field, the electric flux over a closed surface is given by the total charge enclosed in the Gaussian surface divided by epsilon naught. Since there is symmetry, this is always going to be E times A, the area of the Gaussian surface. In this case, the charge enclosed by our Gaussian surface is equal to the charge density, the linear charge density, times the length of our Gaussian surface. Sorry, that should have been L. So the length of our Gaussian surface, L, divided by epsilon naught. The area of our Gaussian surface, the area of our Gaussian surface is the area of this cylinder, which is given by, okay, the area of the cylinder, 2 pi r times L. So the electric field times the area of the Gaussian surface, 2 pi r L, equals lambda L divided by epsilon naught. As you can see, the length is going to cancel, so that means the electric field intensity. This is nice because the electric field intensity will not depend on that length, so the length cancels out in both. So we have the electric field intensity equals lambda over 2 pi epsilon naught r. So the electric field intensity is inversely proportional to the distance from the line of charge. If I plot a graph for this, start out from 0, as the distance increases, the electric field intensity falls in this manner, the inverse proportion of r, not as rapid as that of the charge sphere, but it also decreases. Let us also consider the electric field intensity due to an infinitely large charged plane. So the electric field intensity, due to a charged and infinitely large charged plane of charge density. Let's assume the charge density is sigma Coulomb per square meter. So let's suppose this is our plane. There we go. It's a very large plane, but we only take this portion. Let's suppose the plane is given a positive charge. For this case, the suitable Gaussian surface would be a cylinder. There we go. Let's assume the electric field intensity to this side is E1 and the electric field intensity to this side is E2. As you can see from the diagram, this is a positively charged sphere, so we have an electric field going this side and another electric field to the left. So in this case, if we apply Gauss's law, okay, here the charge density is sigma Coulomb per meter squared. If we use Gauss's law, the integral of E, okay, over the closed surface, so this gives us the total flux equals Q over epsilon naught. Now because of symmetry, this is always going to be EA. But in this case, as you can see, we have the electric field to the right and the electric field to the left. So we have the integral of E1 dA plus the integral of E2 dA, that's the total flux that is penetrating our plane, equals the charge divided by epsilon naught. Let us suppose E1 equals E2, and let's call all this E at once. This is reasonable because this is the same plane, so the electric field to the right and that to the left is ultimately the same. So if we add up all this, we'll have integral over the closed surface of E dA plus integral over the closed surface of E dA equals the charge enclosed in this Gaussian surface divided by epsilon naught. So this is going to be twice the integral of E. Okay, this must have been a vector dA. Just made this mistake. I make this mistake commonly, so just bear with me. Okay, there we go. So the E field dot dA equals the charge enclosed in the Gaussian surface divided by epsilon naught. Let's have more space here. Okay, this is not looking clear. So E dot dA, okay, that's better. So we have twice E times A equals, what's the charge enclosed by our Gaussian surface? Well, that's the charge density times the area of our Gaussian surface, the area of our Gaussian surface, which is in that case A, divided by the epsilon naught. As you can see, A cancels on both sides. Now this is one nice thing with Gauss's law, that every time there is symmetry, then the unknown term is always going to cancel out. In this case, it is very difficult to know what that area would be, but we can easily cancel that out so that we get a generalized equation. So we have 2E equals sigma divided by epsilon naught. Our electric field intensity is going to be sigma divided by 2 epsilon naught. So this is the electric field intensity due to a charged, infinitely large plane. We could also find the electric field intensity due to parallel plates, which perhaps we'll do. So let us calculate the electric field. The electric field due to two parallel plates, okay, due to two infinitely large parallel oppositely charged plates, of charge density sigma Coulomb per meter squared. So previously we have looked at the electric field intensity due to an infinitely large plane or plate. So if we have a plate of this kind, infinitely large, we say the electric field intensity due to this side and due to this side, the electric field intensity, if this is this is a positively charged plate, we have considered this in our previous video, the electric field intensity is going to be sigma divided by 2 epsilon naught. Even this side, the electric field intensity is going to be sigma, sigma over 2 epsilon naught. So this is what we have considered in our previous video. Now let's have two planes of this kind, or two plates. So we have one plate here, another plate here. So there we go. These plates are infinitely large, but we only consider this for purposes of not exaggerating the diagram. So let's suppose this plate is positively charged and this plate is negatively charged. Okay, just have a different color for that. So the electric field due to the positive plate is going to be, so have this, the electric field due to the positive plate, we use the blue color, is going to be sigma over 2 epsilon naught. Also outside on the other side, the electric field due to this plate is still going to be sigma divided by 2 epsilon naught. The electric field, okay, also this side, the electric field is going to point to this direction, sigma over 2 epsilon naught. The electric field due to the negative plate is going to be pointing towards the plate itself, so it's going to be, so we suppose the charge density is sigma in all cases, so it's sigma over, okay, over 2 epsilon naught. It also points towards the plate here, so I have sigma over 2 epsilon naught. It points towards the plate, not outwards. Recall that electric field lines point from the from the positive charge and then to the negative charge. So that's why we have a configuration of this kind. So sigma over 2 epsilon naught. Now let us find the resultant electric field intensity at this point. If you add this plus this, since they are in opposite directions, the electric field intensity here is going to be 0. Okay, the electric field intensity is going to be 0 in this region. In between the plates, we have sigma over 2 epsilon naught plus sigma over 2 epsilon naught. So there we go. Sigma over 2 epsilon naught plus sigma over 2 epsilon naught, because they are in the same direction. Okay, so perhaps I can take off this, it's not important here. So we have our resultant electric field intensity in this region as sigma over epsilon naught. On this side also we have this sigma over 2 epsilon naught in this direction to the right. We have sigma over 2 epsilon naught to the left, so the resultant is going to be 0. So we only have the electric field in between the plates. On the other sides of the plates, we do not have an electric field. Notice that this electric field applies well inside the sphere, the plates. So if you have two parallel plates, a positive plate and a negative plate, the electric field inside here is sigma over 2 epsilon, sigma over epsilon naught. That is, as long as you're inside, well inside the plates, the electric field is going to be that. Okay, but towards the surface, towards the end of the plates, the electric field is going to be a little different. So this electric field is inside the plates in the middle here, but as you come towards the edges, the electric field intensity becomes a little bit bizarre. Okay, so this is all for the electric field intensity due to two infinitely charged oppositely parallel plates. And all these are some of the different applications of Gauss's law. Notice that we are able to deduce this result from our previous derivation of the electric field intensity due to a charged plate using Gauss's law. Okay, if you're watching this on YouTube, please don't forget to subscribe to this channel. Also leave a comment, leave suggestions for future videos, and I'd really appreciate if you help us to grow this channel by sharing with friends. Okay, see you till then. Hello everyone, in this video we'll look at electric potential energy, for which we will use the letter U, and electric potential, for which we will use the letter V. So these are two different quantities in physics that give us a clear definition of the properties of an electric field, the electric potential energy U and the electric potential at a point. So suppose we have a charge of plus q placed in placed at a point in space. So this is our charge plus q. As we already know that if we place a charge plus q in space, it will create an electric field around itself. And so because of the electric field it creates, it is able to attract or repel other charges that are brought close to it, or that are brought in its electric field. So suppose we bring another charge, a test charge q0, from infinity to an arbitrary point. Let's say we bring a test charge q0 from infinity to a certain point q0, to a certain point p. So the charge we bring, the test charge is q0. Let's suppose it is also a positive charge. This charge, the test charge q0, is being brought from infinity. Now this is some kind of exaggeration. Of course, infinity means anything that is outside the electric field of q is considered to be infinity. So suppose we bring this charge plus q. Obviously, because, okay, plus q0, obviously because this charge is positive, the charge that is creating the field and the test charge that we are bringing from infinity, there is going to be a force of repulsion. So there's going to be an electrostatic force of repulsion. In that case, let's call that force Fe. This is the force due to the electric field, so the electrostatic force of repulsion. And so we have to do work against the electric field created by q in order to bring this charge q0 from infinity to place it at this point p in an electric field. We have to do some work, and in doing that work we have to apply some force. Let's call that Fa. So in this, I mean Fe is the electrostatic force between the two charges, while Fa is the applied force. So the force that we are applying in order to bring the test charge q0 from infinity to this point. Now, of course, since there is repulsion, we have to do work against the field. So let's calculate the work we have to do in order to bring the test charge and place it there. So the work done to bring the test charge, so the work done to bring the test charge q0 to the point P, well, it's difficult to calculate that work, but there's a simpler trick using calculus to calculate this work. So let's consider moving the charge q0 through a very small distance. Let's suppose we could move this test charge q0 through a small distance dr. So we can calculate the work done to move the test charge q0 through a small distance dr. So let's call that small amount of work dw. So that's going to be equal to, so before we do that, we know from the laws of basic physics that work done, or work in physics, is actually the same as force times displacement. Okay, force times displacement. So the small amount of work we have to do, let's call that dw, is going to be the force. So the force we are putting in is the applied force times the displacement. In our case, the displacement is dr. Okay, let's see what that gives us. Now this is only the work done in moving the charge through a small distance dr. Let's suppose we want to find the total work done. So okay, let's find another color here. Okay, so let's find the total work that we have to do to move the charge from infinity to this point. So the total work W is obviously going to be the integral of all the small elements of work that have to be done. So this is of course a known law in mathematics. Integration means adding up very small tiny elements. So the work done, the total work, is going to be the integral from infinity, okay, the integral from infinity to r, integrating the electrostatic force, that's the electrostatic force dr. Okay, just something here very important, that as you notice in this diagram, Fe, the electrostatic force, and the applied force are actually in opposite directions. So we can conclude that the applied force is actually equal but opposite to the electrostatic force. So in this case, I could also say the amount of work done is negative Fe dot dr. Okay, notice that this is negative because the electrostatic force does negative work while it is opposing. So our total work done here is going to be the negative of Fe. So if I integrate this, we'll have negative Fe. Okay, choose this again, negative Fe dr. There we go. Let's substitute for the electrostatic force. We know that the electrostatic force, according to Coulomb's law, is going to be Q times Q naught. These charges are placed in free space, so we have 4 pi epsilon naught r squared. Also, just forgot to mention that the point P is actually at a distance r, so that's reasonable. Let us substitute for Fe. So our work done is going to be negative integral of Q naught over 4 pi epsilon naught r squared dr. Okay, there we go. And if you do the math here, you'll actually have all these are constants, so we have negative Q naught. Okay, this is from infinity to point P, which is at a distance r. This is over 4 pi epsilon naught integral of 1 over r squared dr, which gives us, okay, let's see, negative Q naught over 4 pi epsilon. So if we integrate 1 over r squared, we actually have negative 1 over r, which is integrated from from infinity to r. So we have infinity and we have r there. Okay, let's proceed and see what that gives us. Okay, so we have our work done is going to be negative Q naught over 4 pi epsilon naught. Let's substitute in the upper limit. It's going to be negative 1 over r, okay, minus negative 1 over infinity. So we know that 1 over infinity is actually 0. So we have negative 1 over r times this negative here. So we'll have Q naught divided by 4 pi epsilon naught r. So this work done to move a test charge Q naught from infinity to a point P in an electric field of Q is what we call the electric potential energy. So we conclude that the electric potential energy U is actually given by Q naught over 4 pi epsilon naught r. So this is the electric potential energy. It's a scalar quantity since this is just the work done to bring Q naught from infinity to a point P, which is at a distance r from the charge Q. So this is the electric potential energy that we need to do in order to bring Q naught from infinity to a point P. Let's go ahead and look at electric potential V, which is very different from electric potential energy. So electric potential. Now in physics, for purposes of generalization, let's just write that for easy generalization, so for easy generalization, it is always necessary to find the potential. Now every time we talk about potential, we actually mean the work done per unit measure. Okay, just like we talk about electric field intensity as the electric force per unit charge, also the electric potential is like the work done per unit charge. So in this case, the potential of a force is the work done by unit measure, and in this case our measure is going to be the unit charge. So we have already discussed that the electric potential energy is given by Q naught over 4 pi epsilon naught R. So suppose our test charge Q naught is actually a charge of +1 coulombs. So that means our electric potential, so if we have our test charge Q naught as 1 coulomb plus 1 coulomb in this special case, so this is a special case where Q naught is plus 1 coulomb, and in that special case the electric potential energy U is actually equal to electric potential, which we denote with the letter V. So I now write out the formula for electric potential V as the, if I substitute Q naught as plus 1 coulomb here, so I remain with Q divided by 4 pi epsilon naught R. This formula here gives us the electric potential of a field. Very important, the electric potential. So just to give you a clear view of why this is very important in physics, we know that the work done, which is also the electric potential, is given by Q naught divided by 4 pi epsilon naught R. I could write this same thing as you notice, this Q over 4 pi epsilon naught R is actually the electric potential V times the test charge Q naught. So would conclude that the work done by the electrostatic field is given by the potential of that field times the test charge Q naught. That means every time we know the potential of the field, we can easily calculate the work done to bring any test charge Q naught in that field without having to go through all the calculation, because the electric potential is a general property of the field. So the electric potential is a scalar quantity, and the units of V, the electric potential, so units of electric potential, as you notice from here, it's going to be the work done divided by charge. So the units of potential are going to be joules per coulomb. The units of potential are going to be joules per coulomb. Yes, so this is what we have as the electric potential, a general property of the field, and it's a scalar quantity. So suppose we have several charges. Let's look at the superposition of electric potentials. The superposition, spell that right, superposition of electric potential. Superposition of electric potential. So suppose we have several charges. Suppose we have a configuration. Suppose we have a configuration of many charges in space. So let's say we have Q1, Q2, Q3, and so on. Perhaps also we have Qn, several charges placed in space. Let's have what that would look like. So have a charge Q1, have a charge Q2, have Q3, have Q4, and many other charges up to Qn. Suppose we want to find the electric potential at P. Suppose we want to find the electric potential at P. As you notice, there are several charges in this vicinity, in this space. All of them have electric fields around themselves, so all of them have an influence on the electric potential at this point P. So according to the law of superposition of electric potentials, the total potential, or the electric potential at P, is going to be, if we call that potential to be V, it's going to be V1 plus V2 plus all the other potentials up to Vn. Since potential is a scalar quantity, this holds and it is true. So every time we're calculating the electric potential, there is no need to change the signs of the electric potential. As you notice in the, okay, let's go to the previous. Okay, every time you're calculating the electric potential of a negative charge, it will be a negative potential. If you're calculating the electric potential of a positive charge, it will be a positive potential. So it is logical to have this, since potential is a scalar quantity. If you have a configuration of positive and negative charges, so if you have more positives than negatives, then that will have an impact on the potential, and so like that. So we'll look at in some other video, we'll look at some examples where we calculate the resultant potential due to a certain configuration of charges, but we'll do that in a moment. For now, let's look at the potential difference due to a point charge. Very important phenomenon here. Potential difference. The potential difference, we usually denote that as PD, the potential difference due to a point charge. The potential difference due to a point charge. Every time we talk about a point charge, we actually mean a charge that is small compared to the distance on which we are measuring its potential. So that's why we say point charge, a very small charge compared to the distance where we are doing the calculations of potential and electric field intensity. So let's use a previous illustration. Suppose we have a charge plus Q placed in space. It creates an electric field around itself. We know already about that. So let's say at a certain point, let's say at a certain point P, we actually bring or we put there a charge of +1 coulombs, and we want to find the potential difference at 2 points. Let's say we have 2 points. Okay, we're going to take point A. Let's take point B here, and then we take point A here. Let's put some distances here. We have a distance from the test charge to A. Let's call that distance A. Let's call the distance from the charge, so it's not the test charge, it is the charge which is bringing out the potential. Let's call this distance B, and let's call this distance here R. It's not actually so necessary in this configuration, but there we go. So let's suppose we want to find the potential difference between points A and B. In other words, if I move a test charge from B to A, how much work will I have to do? What's the difference between the potential of this point and this point? Let's begin with an analogy. Let's say I have a stone and I raise it up to a certain height. Let's say this is a height h1. Okay, let's say this is a height h1, and let's say I increase the height to this point, and I call this height h2. So the potential energy at this point is going to be mg h1, and the potential energy at this point is going to be mg h2. So this is potential energy 2, this is potential energy 1. I can find the potential difference by subtracting the higher potential minus the lower potential. The same applies to electric fields. We can find the potential difference between 2 points. Now, of course, there are two approaches. There is a simple approach of simply subtracting the two potential differences. So I would say the potential difference, we commonly use PD. Let the potential difference between A and B, the potential difference between A and B, I'll call that VAB. So it's going to be the difference between the potential at A and the potential at B. Now, of course, since potential is given by Q over 4 pi epsilon naught R, as you can see, the potential at A is actually greater than the potential at B for this positive charge, because B is at a greater distance than A. Okay, let's clear up that, then we continue. So that's the potential difference between A and B. It's VA minus VB. So the potential at A is given by Q divided by 4 pi epsilon naught A minus the potential at B is given by, okay, I think it's good to use the same letter Q here, Q over 4. This is the charge here, 4 pi epsilon naught R, not R, A, that's the potential at A. Then the potential at B is Q over 4 pi epsilon naught B. So the potential difference between A and B is actually Q over 4 pi epsilon naught. I pull out the common factor, then I have 1 over A minus 1 over B. That will give me the electric potential between the points A and B. Now, if you're preparing for an exam or something, they might want you to derive this in a slightly different way, which I will not use, but I'll show you the highlight. So suppose you move the test charge, the 1 Coulomb charge, from point B to point P through a small distance, dr. Suppose you do that. Okay, just make this better. Suppose the distance between B and P is a small distance, dr. You would simply say that the potential difference is the same as, okay, this is just another way, the small amount of work done to move this charge from B through a small distance, dr, is going to be, okay, the product of the electric force, that should be a minus, because the electric force is acting, let's just use another color, the electric force is acting in this direction while the applied force is actually acting in this direction. So, and we know that FA is negative FE, so I should be using FA here, but I use negative FE times the distance, dr, and that would give us the total work done, which is also serving as the potential difference between A and B. If you would like, that would be the integral of negative Q over 4 pi epsilon naught R, that's from point A to point B. There we go, from point A to point B. And in this case, you would actually find what the answer is if you take on this integral. Okay, this is with respect to R. You'd actually get the same. You see, we are not including the test charge Q naught, because Q naught, the test charge, is a 1 Coulomb charge, so that wouldn't be necessary in this case, since that's why even here we are putting potential, not work done, because potential is the work done when Q naught is 1 Coulomb. So there we go. That would suffice for us to find the electric potential. That would be a good exercise to try out, and you would actually come up with this same answer, I believe. Okay, this is R squared. Yeah, that's R squared, because this is the electrostatic force. Okay, let us look at the relationship between electric field intensity and electric potential before we look at problems to the numerical problems to do with electric potential. So the relationship between electric potential V and electric field strength or electric field intensity E. So let's begin with an assumption here. Suppose, or let dx be a small distance. Let dx be a small distance between 2 points A and B. Let dx be a small distance between 2 points A and B. So suppose we have a charge here, and we have some 2 points along the line, this line here. We have some 2 points A and B, and there is a small distance dx between these 2 points. So suppose we have to move a unit charge from A to B. So suppose we have to move a unit charge means +1 coulomb from A to B. In that case, of course, we already know that the work done is going to be the force times the displacement, which in this case is dx. As in the previous explanation, the electric force acts in that direction, while the applied force acts in this direction. So this is actually the applied force, which would actually be negative Fe dot dx. So that's a negative Fe. Okay, let's proceed. In this case, since the test charge is a 1 coulomb charge, dW, the work done, is going to be the electric potential. So we will not call that dW since the test charge is +1 coulomb. So these things are very important to notice here. Because of the test charge being 1 coulomb, then the work done is going to be dV, the small change in potential. That's the same as the small work done. Also, the electric force is going to be equal to the electric field intensity, because the electric field intensity is the work done per unit positive charge. So that's reasonable. So I substitute all those here now, and I'll have this formula now becomes dV equals negative E dx. And so we'll conclude that E is going to be negative dV dx. In this equation, this gives us the relationship between potential, the electric field, and the electric potential. Also, the quantity dV dx is known as the potential gradient. This is known as the potential gradient. Okay, so why is the potential gradient negative? Well, it shows that the potential decreases in the direction of the field. So as we move away from the charge plus Q, the electric potential decreases as we go in the direction of the electric field. So this is a very important relationship that is applied in many calculations, as we'll see, or as you may study in more advanced courses. Okay, that's it for this video. Hope to see you again. Okay, so we have just looked at the equation E equals negative dV dx. Now the beauty of this expression is that if I know the electric field intensity, I can always get the electric potential, and if I know the electric potential, I can find the electric field intensity. So just as an example, let's look at how we can derive. So we'll look at the derivation of electric potential V, the derivation of electric potential from this formula E equals negative dV dx, this expression. So it's very important. Let's write this in a more favorable way. Let's say E dx equals negative dV. Of course, I could say dV equals negative E dx, but we already know that E, so since we're using this expression to find V, it means we already have a clue about E. The electric field is given by Q over 4 pi epsilon x squared for any medium. So go to substitute that here. Therefore dV, okay, that's squared. So dV is going to be negative Q over 4 pi epsilon, not epsilon naught, epsilon x squared times dx. So that's dV, but if we want to find the total potential, then we've got to integrate from 0 to V of dV. Also, by definition, for electric potential, moving a charge from infinity to a point, a distance r. So there we go, negative q over 4 pi epsilon x squared dx. So the integral from 0 to v of dv is going to be v. On the other hand, we have negative q over 4 pi epsilon. Let's see, if we integrate 1 over x squared, we have negative 1 over x from infinity to r. So that's going to be, let's see what we get there. That's negative q over 4 pi epsilon, not x. Okay, in brackets we have negative 1 over r, because 1 over, okay, just indicate all that, minus that, minus plus, okay, plus 1 over infinity. Okay, so 1 over infinity is 0, and we'll end up with electric potential as q over 4 pi epsilon r. So you can see that if we have, or if we already know the electric potential, the electric field intensity, we can always find the electric potential. So that's one useful thing with this expression. So let us solve some numerical problems on electric potential. Our first problem here is to calculate the electric potential at point P. So there is point P, it's 10 centimeters from a point charge of negative 10 microcoulombs. So the electric potential is given by Q over 4 pi epsilon 0 R. So in this case, our electric potential will be, of course, 1 over 4 pi epsilon naught is 9 exponent 9. Already know that this is the same as K Q over R, where K is this, times the charge, which is negative 10 times 10 to the negative, what's that, negative 6 here. Change that to coulombs. The distance between the point at which we want to find the electric potential from the point charge is 10 centimeters. That's 0.1 meters. So if you put this in the calculator, you have 9 to power times 10 to power 5 joules per coulomb. But more specifically, we use a common unit of volts. Although joules per coulomb is the same, but volts is preferred to joules per coulomb, and 1 joule per coulomb is equal to 1 volt. So it's okay to use volts in this case. Let's have another example. We have to find the electric potential at point B. Point B is somewhere here, and we have point charges of negative 5 microcoulombs and positive 10 microcoulombs. So let's find the electric potential. Okay, that's a formula for electric potential for charges in free space. That's KQ over R. Now the electric potential, due to, in the previous question, I forgot this. This must have been a negative. Okay, this must have been a negative. Electric potential is a scalar quantity, so there we go. Work done can be negative or it can be positive, so got to do that. Also, the next problem, so we have the electric potential due to the charge at A. So the value of K, 9 exponent negative 9, positive 9, not negative 9, times the charge, which is negative 5 microcoulombs, divided by the distance from the point charge at A to point B, where I want to find the electric potential. It's 10 centimeters, that's 0.1 meters. Okay, put that in the calculator, you get some value. Let's leave it at that. The electric potential due to the charge at C is going to be 9 exponent 9 times the charge, that's 10 microcoulombs, change that to coulombs, divide by the distance between C and B, that's 5 centimeters, that's 0.05 meters. So the total potential at point B, let's call that V, the total potential at B is going to be, I add up the potential at A plus the potential at B, so that's going to be 9 times 10 to 9 times negative 5 times 10 to the power negative 6 divided by 0.1 plus 9 times 10 to the power 9 times 10 times 10 to the negative 6 divided by 0.05. So if you add this up, you have a common factor of 9 times 10 to the negative, to the positive 9. Also you have 10 to the negative 6. Okay, so inside you have negative 5 divided by 0.1 plus, what's this? We have 10 over 0.05. So if you put this in the calculator and solve this, you'll find a value of about, let's see what this is. Okay, this is the potential at C, not the potential at B. Okay, so you'll find the value of 1.35 times 10 to the 6 volts. Okay, there we go. Let's move on to our third example. So we have charges placed at point A and point B, negative 10 microcoulombs and negative 15 microcoulombs. We want to find the electric potential at C. The electric potential at C, let's call that Vc, is equal to the electric potential at C due to A plus the electric potential at C due to B. Okay, let's just use this notation. So the electric potential at C due to A is going to be given by the charge at A. Okay, so the constant, there we go. The charge at A is negative 10 microcoulombs, so that's negative 10 okay, times 10 to the negative 6. The distance between A and C is 10 centimeters. There we go. The potential at C due to the charge at B is going to be, okay, 9 exponent 9 times the charge is negative 15. Okay, change that to coulombs. The distance between B and C is 15 centimeters, so that's 0.15 meters. So the potential at C is going to be the sum of these two. I have 9 exponent 9. Okay, then we have negative 10 times that divided by 0.1 plus, got negative, what's that, negative 15 times 10 to the negative 6 divided by 0.15. Oops. Okay, there we go. So if you put these values onto the calculator, the potential at C is going to be, okay, that's going to be about negative 1.8 times 10 to the negative 6 volts. Okay, hope that's so. Okay, then, okay, that's the electric potential at C, so that's part A. Part B is to calculate the potential energy of a charge of 10 microcoulombs placed at C. So the potential energy is the same as work done, so which is the same as the charge times the potential. So yeah, we know that the potential energy, which is the work done, is the same as the charge times the electric potential at that point. So in this case, the charge of 10 microcoulombs, that's 10 times 10 to the negative 6, the electric potential, there we go, negative 1.8. I think this has got to be a positive. Yeah, that's positive, sorry about that. Okay, so we have negative 1.8 times 10 to the 6th power. So this will actually cancel out, and we have negative 18 joules. So if I bring a charge of 10 microcoulombs and place it at C, then it will have a potential energy, or okay, yeah, I'll have to do work of negative 18 joules. Okay, or the electric field does that. Okay, let's have a fourth example here. So we have 2 points A and B. I have 2 points A and B. There we go. Okay, and we have charges, a charge of negative 6 microcoulombs placed here. So we want to find the potential difference between A and B. The potential difference between A and B, let's call that VAB. Okay, that's the potential difference between A and B, and that potential difference VAB is going to be the potential at A minus the potential at B. Sorry, the potential due to A and the potential, okay, due to B. So let's go ahead and do that. What's the potential? The potential at A, that's going to be, so we have 9 times negative 10 to the power 9 times, okay, what's the charge? It's 6 microcoulombs. So there we go, 6 times 10 to the negative 6 divided by the distance between air and the charge, that's 15 centimeters, 0.15 meters. That's about 3.6 times 10 to the 5th volts. Just try that, see. Okay, the potential at B, that's 9 to the positive 9 times the charge. Okay, charge is the same, 6 times 10 to the negative 6 divided by the distance here is 20 centimeters, which is 0.2 meters. In that case, you have about 2.7 times 10 to the power 5 volts. So the potential difference between A and B, just have more space, potential difference between A and B is the potential at A minus the potential at B. So they'll have 3.6 times 10 to the 5th power minus 2.7 times 10 to the 5th power. Okay, so if you do the subtraction, you have about 9.0 times 10 to the power 4 volts. That's our potential difference. That's Roman numeral 1. Roman numeral 2. Part 2, we can calculate the energy required for a charge of plus 1 microcoulomb to be moved from infinity to point A. So the potential at A is 3.6 times 10 to the 5th volts. So the energy required, that's the same as the work done, which is equal to the charge that we are moving times the potential at A. What's that? The potential at A. So the charge is going to be, that's a charge of plus 1 microcoulombs. That's 1 times 10 to the negative 6. The potential at A is 3.6 times 10 to the 5th power. So there we go. We'll have to do an energy of about 0.36. Sorry, we have to apply energy of 0.36 joules. Okay, let's have a final problem on electric potential. So in this figure, we have points P, Q, R, and S, and we have the following charges placed there. We want to find the electric potential at S. So this is point S. There is no charge here, so no potential will be contributed due to Q. So let's find the potential at S. That's going to be equal to the potential at S due to P plus the potential at S due to R, only that. So the potential at S due to P, potential at S due to P, that's going to be 9 times 10, okay, I can do that mistake, okay, times What's the charge at P? That's negative 22.2 microcoulombs. So just change that to coulombs. The distance between P and S. Okay, so these are sides of a square, 0.5 meters. Okay, it's nice. So we'll have negative, what's that? Negative 3.99 times 10 to the power 5 volts. You can also find the potential at S due to R. That's 9 times 10 to the power 9 times the charge at R. That's positive 44.4 microcoulombs. This is a square, so all sides are equal. 0.5 meters. Okay, this is about 7.99 times 10 to the power 5 volts. So the potential at S is going to be equal to the sum of these, negative 3.99 times 10 to the power 5 plus 7.99 times 10 to the power 5. Let's see what that is. It's about 4.0 times 10 to the power 5. Is that it? Okay. Yeah, hopefully that's it. 4.0 times 10 to the power 5 volts. Okay. Then the second part is to calculate the potential energy. Just have more space here. To calculate the potential energy of a 10 microcoulomb charge placed at S. Okay, so the potential energy is going to be equal to the work done, which is equal to the charge times the potential difference, or the potential at S. So the charge is 10 microcoulombs. That's 10 times 10 to the negative 6. The potential at S, it's 4.0 times 10 to the 5th power. So that's going to be about, this is okay, 10 to the negative 5 and that. So we'll have 4.0 joules. That's the potential energy of a charge placed at S, the charge of 10 microcoulombs. Okay. So let us talk about equipotentials. Equipotentials are very important in the study of electrostatics and physics at large. So what are equipotentials? Well, instead of just telling you, I'll show you. Let's suppose we have a charge of plus Q placed here. We know that this charge is going to create an electric field around itself. In that sense, so there we go, the charge creates an electric field in that sense around itself. So at any point around the charge, we can calculate the electric field. But also, we can calculate the electric potential anywhere in space surrounding this charge. So let us draw a concentric circle to this charge. Let's suppose I draw this circle here. Okay. So I suppose this circle is of a given radius, and all points on this circle are the same distance from Q. So we know that from electric potential of a point charge, which is given by Q over 4 pi epsilon r, is that fine? 4 pi epsilon r. So this is the expression for electric potential of a point charge. So from this expression, we can say that all points on this circle are actually having the same potential, since they have the same distance from the point charge itself. And so what does electric potential actually mean? Electric potential is work done. That's what we mean by electric potential, work done to move a unit charge, or to move a charge of plus 1 coulomb from infinity, okay, from infinity to a point in the electric field of a given charge. So what if we move our charge and we bring it and place it somewhere here. Let's say that's our test charge Q0. What if we now begin moving the test charge along the line, along this arc of this circle that is surrounding the point charge? Are we really doing any work? Let's see what that is. Is there any potential difference between a point A and another point B here? There is no work because all points at this circle, at the arc of this circle, are actually at the same potential. So you cannot do any work by moving from A to B since there is no difference in the potential. Let me show you another good illustration of this. Suppose this is a building. So this is the ground level, okay? This is the ground level and this is the building. Suppose I move a big mass and I place it here. This is a big mass. I place it at this point. It has a potential energy given by the mass times the acceleration, gravitational acceleration times the height from the ground. That's the potential energy that this object has. What if I move the object up to here? Is there any change in potential energy? There isn't any change because potential energy only depends on the height. As long as I'm on the same altitude, I will not be doing any work. Okay? In geography, we use lines called contours. Contours to represent lines on a map with the same altitude. And at those lines, you actually don't do any work in moving an object. So that's very important to us as physicists. Now, just like we have contours on maps, we also have equipotentials in electric fields. There are points at which are at the same potential, so you don't have to do any work in moving a charge from one point to the other. So that's very important. Equipotentials are points with the same potential, or points around the charge, with the same potential. So the potential at A, the potential at B, if I add another point here, perhaps C, they will all be at the same potential. So there is no work done in moving a charge around this. Now, equipotentials can be of different sorts. We could have equipotential lines, for example. This concentric circle here can be considered an equipotential line. Yes, it is an equipotential line because all points on it have the same potential. If I draw another line, okay, perhaps of a smaller radius, oops, I don't want to use that same color. So, okay, here we go. If I draw another circle here, this is also an equipotential line. If I draw another line, that's also an equipotential line. So the surface that is bound by this equipotential line is what we call an equipotential surface. So we can have equipotential points, equipotential lines, and equipotential surfaces. And you'll hear the word equipotential surfaces being used more often. Those are surfaces in electrostatics, surfaces at which you don't do any work in moving a charge around it because the potential is the same. So surfaces that are bound by equipotential lines are called equipotential surfaces. Okay? Also, you can see that the electric fields are always perpendicular to the equipotentials. That's one property of the equipotentials, and that's what makes the work done to be zero. So that's very important. So why is it that the equipotential lines are always perpendicular to the electric field lines everywhere? Well, we already discussed that dV, the electric potential, is given by E dx. Now, to be more specific, electric potential is a scalar quantity, but the electric field and the electric field and the equipotential lines are actually vectors. So to To be more specific, I should write this as dv equals vector E dot vector dx, where vector dx is the direction of the electric field or the equipotential line at any chosen point. So to be more specific, this is going to be E times dx times cos of the angle between E and dx, so that's going to be dv. Now for the electric potential to be 0, or the work done to be 0, so for dv equals to 0, then we'll have E dx cos theta equals to 0, and E and dx will actually be equal to 0, but cos theta, E and dx may not necessarily be 0, but cos theta here will have to be 0. So this means that theta would have to be 90 degrees strictly. So that's why the electric field lines and the equipotentials are actually perpendicular at all points. That's a good point to observe when drawing equipotential lines. Hello, my name is Dennis. Welcome, and in this video we are going to study electric dipoles. So an electric dipole is an arrangement. An electric dipole is an arrangement of two equal but opposite charges. An arrangement of two equal but opposite charges separated by a very small distance. By a very small distance. An electric dipole is an arrangement, and this arrangement should consist of two equal but opposite charges, and they have to be separated by a very small distance. I have a picture here to give you a visual representation of what a dipole may look like. So we have a positive charge here and a negative charge here, and these charges are separated by a very small distance. Let's call that distance 2a. So these charges constitute an electric dipole. Just like point charges, dipoles can have electric fields around themselves. They can form electric potentials, and we can also calculate their electric field intensity, as we shall see. So dipoles are formed when atoms are polarized. So by electric fields. Let's see how this occurs. We all know that in a normal atom we have our atom, the nucleus is at the center, and we have an electron cloud surrounding the nucleus. In a polarized atom, so this is a normal atom, the one that is not polarized. In a polarized atom, this is how it looks like. If we have an electric field, let me represent that. If we have an electric field in this direction, it means the positive charge will move in that direction and the negative charge in this direction. So the shape of our atom is going to be changed, and the atom will get polarized like this. The distance between the positive and negative charge is so small that the two charges actually constitute an electric dipole, which has interesting properties like we will study later in this chapter. Some dipoles can exist naturally. So some dipoles can exist naturally. For example, in water molecules, also in ammonia molecules. These dipoles are very common because of the electronegativity of some of the atoms making up these elements. So very important for our study of electric dipoles is this quantity called the dipole moment. So the dipole moment is a vector. We'll represent that vector with P. So the dipole moment is a vector that points from the negative charge to the positive charge. So if we have a negative charge here and a positive charge here, these two charges separated by a distance, a very small distance, 2a, to form an electric dipole. Let's say this is the line, the axis joining the two. So we have a vector that goes from negative q to positive q, and this vector is what we call the dipole moment. The dipole moment P, and the dipole moment is defined by the formula 2a, the distance between the two charges, times the charge. Okay, there we go, in the direction from negative q to positive q. If we take the magnitude, we'll have our dipole moment as 2aq. This is very important. We'll be using it for the next part of our study. So this formula here, this expression, gives us the magnitude of the electric dipole moment of the dipole. Next, we look at the torque experienced by a dipole placed in an electric field. So suppose a dipole is placed in a uniform electric field such that, so the dipole is placed in a uniform electric field such that it makes an angle, such that it makes an angle theta with it. Let's have an illustration to show what this looks like. So we have a dipole, it's made up of a positive charge, okay, I have this here, positive charge on the negative charge. It's placed in an electric field. Let's assume the electric field is in this direction, and let's assume it makes an angle theta with the electric field. So we know that the force experienced by the dipole, the electric force, is given by the electric field intensity times the charge. So the positive charge of the dipole is going to experience a force of EQ in this direction. Also, the negative charge is going to experience a force of EQ in this direction. The two forces constitute a torque. The two forces consist of a couple, and this couple is what leads to a torque, which is the moment of a couple. Also, very important here, the distance between the positive and negative charges is 2a. So let us calculate the torque. So the torque is given by the product of one of the forces multiplied by the perpendicular distance between the forces. One of the forces multiplied by the perpendicular distance between the forces. Let's actually see what that perpendicular distance is. So the forces are here and here, so the perpendicular distance is here. If I drop a perpendicular from one force to the other, this proceeds up to here, So that's the perpendicular, and this distance from here to here, if this angle is theta, then likewise this angle will also be theta. So the perpendicular distance from here up to here is going to be given by 2a sine theta. So our torque is given by the force times the perpendicular distance, 2a sine theta, but our force is given by EQ times 2a sine theta. I can rearrange the terms in this equation, so I can have torque equals 2aq times E sine theta. Okay, but very important here, we know that 2aq is the dipole moment, the magnitude of the dipole moment. So our torque, lastly, our torque is going to be given by the electric dipole moment times E times sine of the angle between the dipole and the electric field. This is of course the same as P vector P cross vector E by definition. So this gives us the torque between, the torque experienced by a dipole placed in an electric field. As you can see from this equation, you can draw some conclusions from here. One of the conclusions is that when theta equals 0, when theta equals to 0, in that case the dipole is going to experience 0 torque. That is when the dipole is parallel to the field. So in this case, dipole is parallel to the field. Okay, just create more space here, very little. Another interesting case here is when, so this is one case, another case is when this is 0 degrees, when theta equals 90 degrees. So tau, the torque is going to be given by PE from this formula here. Sine 90 is 1, so this is going to be maximum torque, and this is going to be experienced when the dipole is perpendicular to the field. Okay, next we look at the work done, or the electric potential energy of a dipole in an electric field. So electric potential energy of a dipole in an electric field will basically mean a uniform electric field. So as you know, electric potential energy which is denoted by letter U, is the same as the work done by the dipole, or the work done to rotate the dipole in an electric field. So let's have our illustration once again. Suppose we have our dipole with plus Q here and minus Q here, aligned in the field, making an angle theta, and this is our electric field. Okay, so the work done in rotating the dipole through a very small angle, the theta is going to be given by, so we have the small amount of work done to rotate the dipole through a small angle. The theta is torque times the theta, so this is a small amount of work done. The work done equals torque times d theta. So there we go. Okay, but we also know that the torque is given by PE sine theta. So I substitute for that. Therefore, we'll have d work done equals PE sine theta d theta. This means that the total work done is basically going to be the integral from 0 to W. Integration basically means adding up the very small elements to form the total amount of work done. Also here we're integrating PE sine theta d theta. In this case we'll have the total work done, let me call that W. Here we'll have negative PE cos of theta. Okay, there we go. As you notice, the work done is the same as the electric potential energy, which is given by negative PE cos theta. So that means our electric potential energy of the dipole is negative PE cos theta, which is also the same as negative P vector dot E vector. This is a dot product. So there we go. The negative sign here shows that negative work is done to rotate the dipole, since since we are applying this work against the electrostatic field. So we are applying the force against the field in order to rotate the dipole. So we do the field does negative work in that case. Okay, you should consider watching my video about negative work and positive work. That will give you a clear picture of why this is negative. I will leave a YouTube card or a link in the description. The work done in rotating the dipole is negative since we are doing work against the electrostatic field. So the work done by the electrostatic field is negative, or the work done by the electric force is negative. In this case, the dipole, as you can see, the dipole has minimum energy. The dipole has minimum energy. The dipole has minimum energy when theta is equal to 0 degrees, since in that case the electric potential energy will be P times E. There's a negative here. Remember, energy is a scalar quantity, so negative PE is actually the minimum value. That's it. There we go. And this occurs when the dipole is parallel to the field. Okay, let us now find the electric field intensity at a point P along the axial line of a dipole. So we want to find the electric field intensity due to a dipole. We begin with a simple case where we look at a point P which is located along the axis of the dipole. So let's sketch this kind of dipole. Okay, there's our dipole. It has a negative charge, let's call that minus Q, and a positive charge, let's call that plus Q. This line is the axis of the dipole. Okay, just make that more straight. This is the axis of the dipole. Let us consider any point P on the axial line of the dipole. So this is the axis of the dipole, and we have a point P along the axis. So we want to find the electric field intensity at this point P along the axis of the dipole. We have two charges, negative Q and plus Q. All of them will contribute to the electric field here. So before we do that, let's indicate the distances. We know that the distance from one charge to the other, let's call that 2a. For simplicity, we don't want to have half a, so let's have 2a. So this is the middle part. That means we have a here, okay, and we also have a here. Also, let the distance of the point P from the midpoint of the dipole be given by a distance r. So there we go. The electric field intensity at P due to minus Q is going to be pointing to the right. So let's call that E minus. Let's call it E minus the electric field intensity due to the negative charge. Also, the electric field intensity, that's going to be E minus, will actually point in this direction. Yes, because electric field intensity means we've placed a charge of +1 coulomb here, so it will be attracted by the negative charge. So the electric field intensity due to the negative charge is pointing in this direction to the left, and the electric field intensity due to the positive charge is pointing to the right. So if we want to find the electric field intensity at this point, we have to get the electric field intensity due to the positive charge in vector form, of course, plus the electric field intensity due to the negative charge. Let's go ahead and find what the electric field intensity due to the positive charge is. So let's call that E plus. That's going to be Q divided by, or finding the magnitude, divided by 4 pi epsilon naught. So these charges are placed in air. Now the distance from the positive charge to point P, the distance, let's indicate that clearly, from here up to here, that distance is r minus a. So can take off that. So there we go, r minus a squared. That's our electric field intensity due to the negative charge. Then the electric field intensity due to the positive charge, the magnitude is going to be charge divided by 4 pi epsilon naught into the distance from the negative charge to the point P is r plus a, because we have this distance a from here to here, then we have the distance r. So just take off that. So we have r plus a squared. As you can see from the vector diagram here, the electric field intensity due to the positive charge is pointing to the right, and the one due to the negative charge is pointing to the left. So to find they are pointing in different directions. To find the resultant electric field intensity, I must subtract one from the other. Looking at these two electric field intensities, the electric field intensity due to the positive charge will be greater, since it has r minus a at the bottom. It has a smaller term down here. So our resultant electric field intensity is going to be Q over 4 pi epsilon naught r minus a squared. It doesn't even matter which one is subtracted from which. After all, you're dealing with vector quantities. Okay, this is 4 pi epsilon naught r plus a squared. There we go. So we have some common terms here, Q over 4 pi epsilon naught, then we have 1 over r minus a squared minus 1 over r plus a squared. There we go. So this is Q. Just try to make that better. Okay, this is going to be Q over 4 pi epsilon naught. Let's do some algebra inside the brackets here. See what we've got. We will have r plus a, okay, just a little bit, r plus a squared minus r minus a squared. Down here we'll have r minus a into r plus a, all this squared. Okay, hope that makes sense. There we go. This reduces to, if you do the math here, you'll have Q over 4 pi. This is Q over 4 pi epsilon naught. Inside the brackets, you'll have 4 AR divided by R squared minus S squared. That's the difference of two squares inside here. Squared, that's the square outside here. But as you can see in this diagram, every time we talk about electric dipoles, this distance A is much smaller than the distance R. So there we go. In the limit where R is much greater than A, so A is almost insignificant down here. A squared is approximately 0, and so our electric field intensity becomes Q over 4 pi epsilon naught. Okay, there we go. Open brackets, 4AR divided by, now if I make this 0, then we'll have R to power 4. R to power 4. There we go. Okay, let's see. This is going to reduce with this, so we have Q. Just choose another color here. We have Q, not Q actually, 4AR Q. Before we reduce, 4AR times Q divided by 4 pi epsilon naught R to power 4. But as you know, the electric dipole moment, we've discussed this already. The electric dipole moment P is equal to 2 times A times Q, the distance between the two charges in the dipole times the charge. So I substitute for that here. Just have more space here to finish this up. Okay, so just follow this up from here. In this case, our resultant electric field intensity is going to be 2 times P, because if I substitute for 2AQ here, then we'll have 2 remaining times P divided by this R reduces with R to power 4, so we have 4 pi epsilon naught R cubed. So this gives us the electric field intensity at any point along the axis or the actual line of the dipole. There we go. The electric field intensity at point P is given by this formula here. As you can see, it's inversely proportional to the cube of R, so that means the electric field intensity falls more rapidly than that of a point charge. Okay, let's take this one step further. We have only considered the electric field intensity at a point along the axis. Let's consider the electric field intensity at a point on the equatorial line. So the electric field intensity at a point P on the equatorial line. We'll see that in a moment. Equatorial line of the dipole. So let's see this. We have our dipole. There we go. We have a minus charge, and we also have a plus charge here. So this here is going to be our axis of the dipole. So the equatorial line of the dipole is going to divide the axis into 2. Just make that a little shorter. So that's our equatorial line of the dipole, and there's our point P. So we want to find the electric field intensity at this point P due to the dipole. So notice in this diagram that this is a positive charge, so the electric field intensity is going to point away like that. Let's call that E plus the electric field intensity due to the positive charge. Also, due to the minus charge, the electric field intensity is going to point towards it, so that's E minus the electric field intensity due to the negative charge. Let's suppose this angle here is theta, so if we draw, just to make our resolving of forces much easier, let's draw this line here. That means we have an angle theta here and an angle theta here. Okay, we'll consider that in a moment. In this triangle, this is isosceles. This distance here is A and this is A. To make the whole distance 2A, we have considered the distance 2A to be the separation of the charges in the dipole. Okay, let's make this more clear by extrapolating it outwards to see exactly what forces are acting on the unit positive charge placed at P. The exact electric potential, electric field intensity at that point. So there we have a force diagram. We have E plus in that direction, we have E minus in that direction, and then we have, okay, just to make this visually good, we have an angle theta here and theta here. Just make this bold. That's our x-axis. So the component of E minus here will be E minus sine theta, and this is going to be E plus sine theta in the vertical direction. In this direction, we'll have two components, E minus cos theta plus E plus cos theta. So as you can see, the component E plus sine theta and E minus sine theta are actually equal, since E minus and E plus are the same, because these charges are the same, are equal in magnitude. So the vertical components will cancel out. So here, a small note here is that vertical components cancel out. So we only remain with the horizontal components. The horizontal components of this direction, E minus cos theta plus E plus cos theta. So our resultant electric field intensity E is going to be E minus cos theta. This is not actually E minus down here, cos theta, okay, plus E plus sine theta. That's going to be our total electric field intensity. Okay, let's go ahead and find what this is and what this is. Is this called, that's supposed to be cos theta. Okay, so let's see. Our E minus, the electric field intensity due to the minus charge, is going to be Q, the magnitude of the charge, divided by 4 pi epsilon naught. Okay, let's see what's the distance between negative Q and P. Well, I'll go for simplicity, let's consider this to be R, the distance between the middle point of the dipole and our point of consideration here. So yeah, that makes things easier. This distance here will be R plus R squared. Okay, this, using Pythagoras theorem, you can see that if I call this distance, say x, so we'll have s squared plus r squared equals x squared. So the square of the distance down here is going to be s squared plus r squared instead of having x squared there. Also, the electric field intensity due to the positive charge is going to be Q, that's the magnitude, divided by 4 pi epsilon naught r squared plus s squared. That's the distance here. The distance here is square root of s squared plus r squared. That's the same distance here, square root of s squared plus r squared. So that's how we come up with this. If I square the square root, then I get this. Now let's substitute these two equations in this to find the resultant electric field intensity. So we'll have our electric field intensity equal to, so we have Q over 4 pi epsilon naught r squared plus s squared times cos theta. Okay, there we go, plus the same Q over Q divided by 4 pi epsilon naught r squared plus s squared cos theta. So we have some common terms here, Q over 4 pi epsilon naught r squared plus s squared. That's common. I think everything is common here. This is just the same, so I'll just have 2q and then cos theta. Okay, that's nice. Looking at this diagram, you can see that cos theta is actually a divided by square root of s squared plus r squared. So that's our adjacent and that's our hypotenuse. So cos theta is that. Let's substitute that here. We have the electric field intensity as 2q divided by 4 pi epsilon naught r squared plus s squared times, where there's cos theta, we have a over square root of s squared plus r squared. Okay, so keep this in mind. I'll try to move this to find more space here. Okay, there we go. So our electric field intensity then becomes 2aq divided by 4 pi epsilon naught. Now this is to power 1, this is to power a half. If I add the 2, I'll have r squared plus s squared to power 3 over 2. Now using the previous assumption, we know that the distance between the two charges in the dipole, the distance r is ideally much greater than a, because from the definition of the dipole, the two charges must be separated by a very tiny distance. So in the limit that r is much greater than a, so a is going to be approximated to be 0. In this case also, notice that 2 times a times q is the dipole, the magnitude of the dipole moment, the distance between the charges in the dipole times the charge, that's the dipole moment, its magnitude in this case. So our electric field intensity is going to be given by, in this case, P divided by, just write that better, P divided by 4 pi epsilon naught r cubed, because the square cancels, so we remain with the cube. There we go, the square cancels, then the cube remains. So this is our electric field intensity due to, the electric field intensity at a point P due to the dipole. Okay, so there we go. At this point P, the electric field intensity is P over 4 pi epsilon naught r cubed. Still, you can see that the electric field intensity decreases more rapidly, r cubed, so it decreases more rapidly than that of a point charge. So this is reasonable since we have two equal but opposite charges and they are separated by a very small distance. Let us calculate the electric potential due to a dipole. The electric potential at any point P, due to a dipole So let's draw our dipole. Here we have our dipole. Let's have this as our positive charge plus Q, and this as our negative charge minus Q. And let's suppose point P is at this point here, at this location. The distance from the charge plus Q to point P, let's call that distance R, plus the distance between the positive charge and the point of our consideration, point P. Also the distance from the negative charge to point P, let's call that R minus. The distance between the two charges in the dipole, let's call that 2A. So essentially that means if this is the midpoint, this is the midpoint of the dipole, then this is a distance A, this is also another distance A. So this is the axis of the dipole. Let's take this angle to be theta. That's good for our calculation. So we take that angle to be theta. Looking at this diagram, this is the negative charge, this is the positive charge. So the dipole moment P acts in this direction from the negative to the positive. Okay, so let's find the electric potential at point P. We will consider the charges plus Q and minus Q individually and then add up the resultant potential. So the potential due to the positive charge, I'll call that V plus, is equal to Q divided by 4 pi epsilon naught, assuming the charges are placed in space, R plus. This is similar to the electric potential due to a point charge plus Q. Also, the electric potential due to the negative charge is negative Q divided by 4 pi epsilon naught R minus. Remember, electric potential is a scalar quantity, so the negative sign has to appear here. Okay, so the resultant electric potential, the resultant electric potential is equal to the potential due to the positive charge plus the potential due to the negative charge. Since this is the principle of superposition of electric potentials, we just add up the electric potentials, the individual sum, algebraically. These are not vectors, they're scalars. So we have Q over 4 pi epsilon naught R plus minus, plus minus, so that's minus Q over 4 pi epsilon naught R minus. Have some common factors here, Q over 4 pi epsilon naught 1 over R plus minus 1 over R minus. Okay, so this is our electric potential, but of course we've got to simplify this and make it more easier to read, since the distances R plus and R minus are generally difficult to calculate. So we have to express them in terms of other quantities that are easier to calculate or to measure. Okay, let's go ahead and do that. Let's begin with the distance R plus. So if you look at this triangle here, just draw a sketch of that. Have a triangle of this sort. Okay, just make like that. So this is the angle theta. This is a distance A, just this distance from here to here, and then this is a distance R plus, and this is a distance R. Forgot to indicate that the distance from the center of the dipole to the point P that is under consideration. So it's easier to measure distance R since it's a general distance, but R plus and R minus are quite difficult to measure. So let's take R to be the distance from the midpoint of the dipole to our point P. So if you use the cosine rule, the cosine rule, you'll see that using the cosine rule, R plus squared is actually going to be S squared plus R. Okay, let me begin with R squared just to make this easier. R squared plus S squared minus 2AR cosine of theta Let's see what that becomes. If I factorize out r squared, then we'll have 1 plus s squared over r squared minus 2a over r cos theta. There we go. So r, also notice that s squared over r squared can be approximated to be 0, since this is so because a is much less than r, so this assumption can hold. So r plus squared is equal to r squared into what do we have inside here, 1 minus 2a divided by r times cos theta. There we go. Let's take square roots on both sides. So r plus, because we only want r plus, not r squared, this will be r times 1 minus 2a cos theta over r. There we go. This is the power a half because we take square root on both sides. So if I take reciprocals on both sides, I'll have 1 over r plus equals 1 over r into 1 minus 2a over r cos theta. This becomes negative a half. Okay, this is just some bit of algebra. I'll use the binomial expansion at this expression here. You know that if I have 1 plus maybe nx, 1 plus x, and that's how the expansion goes. The binomial expansion for any index, I'll have 1 plus nx plus n into n minus 1 over 2 factorial, that's x squared plus many other terms. So I'll expand this only up to the second term. Guess that will be enough. So we have 1 over r plus equals we have 1 over r. So if I expand this using this binomial expansion, only the first two terms, I'll have 1 plus I guess that will be 2, a over r. The 2 will cancel with the 2 down here, and then cos theta. So this is 1 over r plus, and we'll substitute that here. Okay, let's go ahead and find 1 over r minus using similar technique. So create more space here. Let me sketch, begin by sketching the triangle that represents this. So we have, from our diagram, this is what we have. This is r, this is a, this is 180 minus theta, this is r minus. Okay, I'll give you a look again. So here we go. We have, if this angle here is theta, so the remaining angle is 180 minus theta. This is r minus, and there's our point P here. So this is reasonable. So let's go ahead and find r minus. Okay, what's that going to be? Let me use the green color this time around. So still using the cosine rule. Using the cosine rule, we'll have r minus squared. It's going to be r squared plus s squared minus 2ar cos 180 minus theta. If you just follow the same steps, this is r squared. Factorize this out to make our calculation easier. Sorry about that. So we have 1 plus s squared over r squared. Okay, this is going to be plus. If you expand this, I'm not going to do that. Hopefully you can expand 180 minus theta. You'll actually get 2a over r. Yeah, that's over r. If you expand cos 180 minus theta, that's going to be positive cos theta. So there we go. Let's take this to be 0, because since a is much less than r, then s squared over r squared is going to be so negligible. So we'll have r squared equals, so this is r minus, equals r squared, open brackets, 1 plus 2a over r cos theta. There we go. So we have If we take square roots on both sides, we have r minus equals r into 1 plus 2a over r cos theta to the power half. Go ahead and get the reciprocal. 1 over r equals, this is r minus, equals 1 over r, in brackets 1 plus 2a over r cos theta to the power negative a half. Okay, just to create more space here. So moving forward from this, let's see what we have here. If I expand this using the binomial expansion, something we did previously, we'll have 1 over r into, just up to the second term, we'll have 1 minus, what's that going to be, a over r cos theta. Yeah, that's it. So I have the expression for, just to show you what we derived previously. So I have the expression for 1 over r minus. I also have the expression for 1 over r plus. I'm going to substitute all that to my original expression here. Okay, just take a look at it. Also take a look at this. Those are the most important conclusions. Also this here. Okay, let's begin now. Let's do that. We have that the electric potential is q over 4 pi epsilon naught 1 over r plus minus 1 over r minus. Okay, there we go. Let's do the substitution. Q over 4 pi epsilon naught. Let's open a big bracket and do the substitution. 1 over r plus is actually 1 over r into 1 plus a over r cos theta minus, okay, just a little bit space here, minus, what do we have, 1 over r into, I'm putting this, sorry, this 1 over r minus, that's 1 minus a over r cos theta. Okay, there we go. So the electric potential is going to be q over 4 pi epsilon naught. Okay, if you see, I could factorize out 1 over r from here and also from here. So I could have 1 over r outside here. Inside I'll have, that's, what's that? Okay, maybe not. Let's do this the easy way. 1 over r minus 1 over r, that's going to cancel. So we'll have inside, we'll have 2ar, is it 2a over r cos theta? This negative and this negative is going to be plus. Okay, I think this is squared because r times r also here. Okay, this is better. So there we go. We have q over 4 pi epsilon naught, and inside here we have 2a. So let me put that here. Oops, that's 2a times the cosine of theta. Okay, there we go. And then r squared down here. But we already know that the electric dipole moment, okay, it's a little bit of space there. We already know that the dipole moment, we call that dipole moment P, is given by the distance between the charges times the magnitude of one of the charges. So you can see that the potential is actually equal to the dipole moment, the magnitude of the dipole moment times cos theta, magnitude of the dipole moment times cos theta divided by 4 pi epsilon naught r squared. Now we can play around with this. This is actually complete, but we could play around with it to make it a little bit more general. We could, for example, say P. Okay, we could just say P r cos theta divided by 4 pi epsilon naught r cubed. Notice we've added one r here and another r here, which is good because now P r cos theta is familiar to us. That's the vector P dot product vector r. So r is the direction of the electric field of the dipole, and then P is the dipole moment. So our electric potential due to the dipole at point P is going to be vector P scalar product vector R divided by 4 pi epsilon naught R cubed. This is also another common general formula for electric potential at any point. Okay, let's just have a quick recap. So this is a long way of doing this. I'll actually show you a simpler way in a moment. So there we go. We began with our diagram here of the dipole and the point P. Then we applied some, this is the basic concepts of electric potential due to a point charge. We came up with this. Then we applied some basic trigonometry on these triangles to find what 1 over r plus was and 1 over r minus. Don't forget we also used some little bit of binomial expansion, and there we had our electric potential due to the dipole at point P. So let's do this using an alternative method, and this method is rather I think, in my opinion, easier to use, but sometimes depending on what you may like to use. So let's begin with the dipole. Once again, we have plus q here, we have minus q here. So that's what we began with. Then we have our point P here. Okay, I intend to make this a straight line. Okay, that's better. We have our distance as r minus and r plus, and we have a distance r in the middle here. This is the line joining the, so that's distance A, and this is an angle theta. So as you notice here, since A is much smaller than r, it turns out that r minus is actually almost approximately equal to r plus. And so the path difference, if I could just draw this, okay, that's better. This is at 90 degrees. So the path difference, the distance between this, is that good enough? Okay, the distance between here and here is, if you actually draw this triangle here, and then you have this as 2a, and you have this angle as theta, because these lines are almost the same. So you have this as theta, then you have this as, okay, this is 2a, this is theta. So this line here is going to be 2a cos theta. Okay, so that's what we have here, 2a cos theta. And this is the path difference, the path difference of r minus r plus. Okay, let us now find the electric potential. Let's go ahead and do that. So the electric potential due to the positive charge, which is another color, V plus is Q over 4 pi epsilon naught R plus. Also the electric potential due to the negative charge is negative Q over 4 pi epsilon naught R minus. So the resultant potential is going to be obviously V plus minus V minus. There we go. We already did this. We'll just have, if we add the two, we'll have Q over 4 pi epsilon naught R, okay, not R, rather 1 over R plus minus 1 over R minus. So you notice that this is the same as Q over 4 pi epsilon naught. If I do some algebra here, then I'll have R plus R minus, and then I'll have R minus minus R plus. So looking at this diagram here, the path difference R minus minus R plus, this is not actually a negative sign, it's just a R minus, it's a distance. The path difference is actually 2a cos theta, and also since R plus is approximately equal to R minus, then R plus R minus will be approximately equal to R squared, So there we go. I put these two assumptions into my expression here. The electric potential becomes Q over 4 pi epsilon naught. So I have 2a cos theta over r squared, which then becomes 2aq cos theta divided by 4 pi epsilon naught r squared. And let's see what happens here. 2aq is the dipole moment, P. Okay, good that. Well, so this is the dipole moment, P. So our electric potential is actually P cos theta over 4 pi epsilon naught r squared, which becomes P vector P scalar product vector r divided by 4 pi epsilon naught r cubed, as we have previously showed using the other long method. So this method involves making use of these two approximations on the distances r plus and r minus. Okay, that's it for this video. I would appreciate if you like this video. Also comment below for future videos. Don't forget to subscribe. I'll see you sometime.